Hello friends, and welcome to this course where we will jump straight into realization of networking technologies, primarily focusing on Cisco products. I might also add in other vendors' equipments to make it multi-vendor networking course. I have already got one course on Juniper, which is an excellent introduction to Juniper networks, but that is more focused on GNCIA certification. Now, as far as basic networking concepts are concerned, you really do not need much hardware for that. Like for CCNA certification level knowledge, a couple of switches and routers are more than enough to get you through. But when you are talking about large networks exceeding 5 networking devices, then definitely not everyone likes to buy them all. Besides the purchasing cost, even if you are going for used ones, the noise and heat from them all would be enough to make you sweat in your pants. And by the end of the month, the electricity bill would be enough to make you visit ICU. For that, we can emulate the devices using different programs available in the market. Now, you must be familiar of GNS3 routing switching emulator program, freely available from GNS3.com, which works using Dynamips engine to emulate the actual iOS images of Cisco. Its later versions do provide integration with VirtualBox based virtual machines, and you can also use it for QEMU based virtualization. I tell you, it's a great piece of software and I highly recommend it to you in order to help you implement concepts. However, there are many aspects where GNS3 alone is not enough. For example, GNS3 cannot emulate Cisco switches, so you cannot really implement VLANs, STP, Ether channel based layer 2 network scenarios. Since GNS3 is based on Dynamips, it consumes heavy CPU, and although you can tweak CPU throttling, but sometimes it just does not help. Moreover, GNS3 is focused primarily towards Cisco with additional support for Juniper products as well, but there are many more networking products from other vendors which are widely used in enterprise environments like Alcatel, Extreme Networks, Palo Alto, Palo Alto, or even Checkpoint. Now, Cisco has this product known as IOU or IOL, which stands for iOS on Unix or iOS on Linux. These are iOS images built with native Unix support, so you can execute them straight from the command line. They are fast to execute and consume very less CPU cycles. There was a product known as IOU Web, which provided a nice graphical web interface to connect these IOU routers, which now has been replaced with UNL. So you cannot really find this product IOU Web anymore. Its developer has changed it to UNL or Unified Networking Lab, which is essentially a virtual machine that you can use to emulate multi-vendors environments on Linux as well as on Windows. In the upcoming videos, I'll show you how you can use these products, so stick around and I'll see you in there. Hello guys. So in this video, I just wanted to show you regarding GNS3 or Graphic Network Simulator as we call it. If you already know about it, it's a good thing, but for those who are unaware of it or who do not know how to set it up or certain parameters regarding its functionality, let me just take you quickly through these setups. So first of all, you need to download it. It's freely available from GNS3.com website. You just need to create your login by giving it the username and password, and you can straight away download it. So once it gets downloaded, I have already one with me, which is 1.3.3, and the latest version available at the moment is 1.4.4. so you can download that one as well. With different versions, the developers change certain options and add in certain functionalities as well. So you just need to double click it and it will get installed. It's pretty straightforward setup, and you can't really go wrong with that. So once it gets installed, you come on to its executable, and this is the interface that you get once you install it. And this is the main working area. Over here in this space, you create your own topology, and let me just show you some quick preferences. You come on to miscellaneous and maybe disable that project dialog at the startup. You can also disable this automatically screenshot when you are saving the project. Maybe disable the updates if you want to regarding the send crash reports. It's really up to you what you want to enable or disable. You just need to go through with these options and set them up according to your own desires. What console application you want to use. I'm using Putty at the moment. This is by default included with the GNS3, and these are the paths where you can save your work. Also, you can change the style. I like this one. This is the legacy style, some colorful icons. And the important thing is that from here, this is the area from where you can add the devices. These are the interfaces. Once you get your devices connected, this gives the console, start button, stop, and you can also add in these figures to kind of group together certain devices, or maybe you can use ellipse or circle so that you can encompass different devices and colorize them if you want to make them appear in a single group. Just for presentation purpose, it does not have any significance with the actual working of the devices. Likewise, you can write some note if you want to. So let's just remove this one, and let me show you the important thing regarding adding the image. So once you have got Cisco iOS, actual iOS, you come on to preferences, and over here you click on iOS routers, click on new, and whatever iOS image you have got with you, you need to put it over here. So if I click on browse and go to the desktop, then this is the image that I can use. You can also use binary. I have converted that binary into image so that it gets executed quickly, because if you have got binary image, then they first get decompressed once you lost them. So I have skipped that part. I have already converted them into image, and if I click on open, it asks me that if I want to copy it into the location that GNS3 has set itself for the iOS image. You can choose yes if you want to, but no as well. It does not really make much difference. So click on next. From here, you can change the name if you want to, and the platform if it has got options. Like over here, it is giving me certain options that I want to change. So let's just leave it default that at the time being it is using 3725 model of 3700 series routers. You can also select this option to install or make this appear as an Ethernet switch router. So I do not want it. I just want it regular router. I click on next, and this is the default RAM that it has selected for us. Let's just leave it there. 128 is more than enough for your working. Go ahead, and from here you can add certain interfaces that you want to. By default, it has got fast Ethernet installed, so we cannot select it. This will always be there by default, and I believe it has got 2 fast Ethernet interfaces. If you want to add more interfaces, you can select from these drop down options. This fast Ethernet, these are 4 serial interfaces, and this is 16 port fast Ethernet switching module. It does provide some functionality regarding switches, but not all the functionality that a switch provides you. So let's select the serial interfaces, click on next, and from here it gives us some more options regarding WIC modules if you want to add. Again, interfaces if you want to add in, let's just leave them, click on next. And this is the important option over here. This says that what idle PC value you want to set in. Now what really happens that if you do not do that in the earlier versions of GNS3, this option was not part of this wizard that we are seeing at the moment. We needed to set it up manually by ourselves by hit and trial methods. So if we do not set this idle PC value, what it does is that even if you add in a couple of routers, and you turn them all at the same time, then they tend to consume all the CPU resources, or I should say that your CPU will go up to its maximum value. So you cannot really work with larger topologies. So this idle PC value, what it does is that it keeps your CPU threshold to a minimum value. So in these later versions of GNS3, they have added this functionality in the setup wizard. You just quickly click on this idle PC finder and it will automatically find the best idle PC value for this model of 37125 series router and set this value as well. So you do not need to do anything manually. So just click on it and let it find the idle PC value. So this is the idle PC value that it has found for this particular router module. I click on OK and it has already set this value. I click finish and this is the template that is generated for our use. I click on apply, click OK, and now I can simply select this router and drag it over into the working area space. I can also connect this router with virtual PCs by dragging this virtual PC over here. Click on its configuration and maybe if I want to change the console port, but let me turn this on and let's just try to connect this one with this router interface. So once it gets connected, I can turn this PC on, and it's just a simulator. It's not a real PC. It's not a VM machine. It's just the simulator that these GNS3 developers, they have put this in for our use. So once we have this window and you want to see that what options are here, what command options, so we can check the ARP table of this simulated PC, or we can select the DHCP options. We have the ping functionality, which is the most important one as far as connectivity is concerned, to if we want to see if the host is up or not, or if we are able to reach it or not. Likewise, trace route is also available. So at the moment, and we have also this show command to see what options we have set up with this PC. So if I type in show, we see that by default it has got no IP address. To set the IP address, I need to type in IP, press enter, and it gives us the options that how we can set in the IP address. So if I type in IP using this method which is over here, this one, let me just highlight this one. So I type in IP and whatever the IP address that I want to type. So let's just say that 1.1.1.1 with a subnet mask of 30, and let's just also give it a gateway of 1112. Once I do this, it should take these settings, and we should be able to ping ourselves our own IP address, which was 1.1.1.1, which we do. So now let's come on to the working area, and to turn on the router you simply need to click on start. Once it gets started, we can choose to connect it with console, and just give it a while so that its boot sequence gets completed. Once the router has booted up, we can quickly go into configuration mode and that particular interface that we have connected our host with, and do a quick IP address configuration by giving it the IP address and subnet mask. Bring the interface up and try to ping the virtual PC which we had configured earlier by the IP address of 1111, and ideally we should see that we should have the connectivity, which we do. So you can add in more number of PCs if you want to, like just select them and drag them in the working area and connect them all together as per your own requirement and topology, if that whatever you practice on with. To turn off the devices, I need to simply click on this red button. And let me also show you that how you can add a loopback interface so that you can connect your devices, like these devices over here, to your actual host machine. Like the moment that I'm working on is the Windows 7 machine, how you can do that for Windows environment. So the way to do that is, first you need to create a loopback interface by going into the control panel, and from control panel you can go to System, Device Manager. The procedure might change a little bit with respect to the Windows version that you are using, but I believe for Windows 7, Vista, and even XP, I'm not sure about Windows 10, I have not used it, but for these versions the procedure will be more or less the same. So from here, Device Manager, you can go to Add Legacy Hardware, click on Next and choose the hardware manually from the list. From here you can come on to Network Adapters, which is over here, click on Next, and from this menu select on Microsoft, and from your right pane you can select Loopback Adapter. Now once you do that, click on Next, it will get it installed, and you will have this option over here. Now sometimes what happens is that once you do it and you try to use this loopback adapter that I'll just show you in the GNS3, does not work. And what really happens is that you can restart your machine to make it work. And other thing you need to be careful is that your WinPCAP or the packet capturing program or service should be running at the boot time. That gets automatically installed once you install the GNS3 software. It also installs the Wireshark, which is packet capturing software. So make sure that that service is running. So if it does not get started or does not work while you're connecting this interface with your GNS3 appliances, then you need to restart your machine. So once you have got this loopback interface over here, you can come on into the control panel. Let me just close this one, and from control panel you can go to the area where you can enable or disable adapter settings. So this is the adapter that I had created earlier, which is the loopback. It is written that it's a Microsoft loopback adapter. I click on its properties, and I can give it the IP address whatever I want to. So let's say that the IP address is 2222, and now the problem is that how we can add this into our topology over here. So you need to go to and click this cloud option, drag this cloud into the working area. You can also change its symbol so that it reflects your thoughts. Let's say it's a PC, and from here we need to configure it and select that particular interface, which was by the name of local area connection 0, local area connection 2. This is the loopback connection, if you remember that from here, local area connection 2, which was a loopback adapter that we had created. So select this one, click on add, click on apply, and OK all the way. Now from here you can add the interfaces by selecting this icon, and let me see if it is okay. So from here select this interface and connect it with the particular router. So once it gets connected, sometimes it does not work. So what you can do is that it really depends on the GNS3 version that you are using. What you can do is that you can put in these generic Ethernet switches in between and connect this wire through this switch, and this switch in turn gets connected with the router. So once you turn on this router, let's say if we turn this on and wait for a while since it gets this boot sequence completed. So once we have the prompt, I can quickly go into the configuration mode and the interface that I have connected with, give it the IP address 2.2.2.3 let's say, and an IP address of or subnet mask of 8, do a no shut, and now ideally we should be able to ping the loopback interface of our host machine whose IP address was 2222, which we can. And from host machine, if I come on to start menu, and from here I can select this command prompt. So our own IP address is 2222 and the router that we are connected with is having an IP address of 2223, which we have just configured. So I should be able to ping this router Ethernet interface from my host machine, which we can. A couple of more options as far as adding of appliances is concerned. You can come on to preferences, and if you have got virtual machines, like earlier if you needed to add in GNS image, you could do that using virtual machine or using these Keymoves options, but now Keymove option does not have the support for adding the GNS image. You can only add in the GNS image if you have got the virtual machine for that GNS image, and you can get that virtual machine imported into VirtualBox, and from VirtualBox you can reflect that over here by selecting that particular option that you had created with whatever name. For ASA firewall, which is Cisco Adaptive Security Appliance, you can come into Keymove, and from here you can select on new. These are the default templates that GNS3 offers us. You can select in ASA 8.42. If you have got that with you, click on next. This is the name that you want to set in, then click on next, and 1 GB RAM, this is sufficient. Do not change these settings, these are by default and they work well. Click on next, and from here you need to give the two files if you have got them with you to make the ASA work. I have put them on the desktop. One is the init file, which is over here, and the next one is kernel file, which we need to select as well. Once they get selected, I can finish the setup and it creates the template for us that we can use for our working. Now I can select on this firewall and drag this firewall in the working area. To start it up again, I need to click start, and once it gets started, I can choose the console to connect it with. So just give it a moment and the process should be started. So we have it booted up, and it is taking just a bit of time. It has, by default, it has got 4 Ethernet or gigabit Ethernet interfaces, but you can change the settings by going into preferences and go to particular Keymove. From here you can edit it, and from here you can select the, or you can enhance the number of interfaces, but by default it supports 4 gigabit Ethernet interfaces, this ASA firewall. You can also capture the interface traffic by clicking on that particular interface, right click on it and do the start capture, so that it starts the Wireshark program, and from that program you can really see that what packets are moving and what layer, it's layer 2 information, layer 3 information, or even application level information. So do use this product. It's very good as far as emulation environment is concerned, and you can really practice around your concepts, and before you do the actual deployment in the on your job. And there are certain scenarios that you can really not implement on the job. because of the things that they might jeopardize the configuration of your actual working environment. So it's a good product. Do use it, and I hope you have found this video informative. I would like to thank you for viewing.
Hello friends, in the previous video we had a quick look at the GNS3 and how we can use it to emulate different topologies, and in this video I will show you that how we can use IOU or iOS on Unix or Linux as well. It is also known as IOL, and in my previous videos I talked about that IOU is the iOS which has got native Linux support, so it consumes pretty much very less CPU and very low memory consumption. So if you are to build large topologies, then as compared to Dynamics based or GNS3 emulation, this IOU really helps you a lot. Now you can search it around our internet, and I may also maybe put up a link in the description of these lectures, or maybe as an added content, so that you can go over there and download it by yourself and practice it. So it's just not that difficult. There is nothing to be set up. You just let me show you. Let me just remove this one and bring up the where I have copied those some of the images. These are the switch images, and this one is layer 3 images or for router 1. And the way to run it is that you just need to execute these files. But before execution, you also need to have a license, and license file is kind of particular belongs to that particular host that you are working on, so it's specific to your machine. And the way to generate that license is using this keygen.py, or is the Python script that you run on your machine, and it generates a number that you can put in this particular file. So let's see how we can do it. Let me just bring up the window and get into that particular path, which is desktop and in IOU. So once I'm over here and I do a list, by the way, since it was natively for Linux, so it will not run on Windows, so you need to have a Linux machine, and if you are already familiarized with the Linux or Unix environment, then it should be a pretty much walk in the park for you. So over here I need to type in Python first to get started and to generate the license file, and after that this Python script, which is keygen.py. After that I press enter, and these are just the 2 lines that I need to add into a file by the name of IOURC, which is over here. So if I open it up, or maybe I can show you the contents of this file right away. If I type in cat and IOURC, and these are the contents of the file that I have copied in there. Now after this is done, and also this license file, it has to be on the same path where your images are running. So if I've got images that I need to run on in this path, which is desktop IOU, then of course I need to put this license file in the same very folder. Now to run the image, I simply need to execute it. Let's say if I want to run this layer 3 image, which is the router one, so I type in I86 and L3, and after that I need to give a space, and after that I need to mention the machine number. For example, if I type in 1, 2, 3, 4, 5, whatever number I want to type in, that will be considered as the machine number. And why it is significant, I'll show you in a while. So just at the moment, let's go along with this number 1. Now once I do that, we see that the image is booting up, and by default this image has got 8 Ethernet interfaces with 8 serial interfaces. So just give it a while it gets booted up, its sequence gets completed, and once it gives us the prompt, I'll show you the command line. Alright, so it's booted up, and it is asking me whether I need to enter into the initial configuration. I can type in no and auto terminate the auto install process, and just hang in for a while. It takes a bit initially, but then it's really quick. Alright, here we are. I press enter and I go into enable mode, and if I type in show version, it shows us that the system image file is the one that I had executed. And if I bring it up, then it says that this is Cisco IS software, Linux software, and this is the version number that we are running at the moment. And if I go into, let's say, conf p, I can do pretty much all the configuration that is supported by this particular image that I am having. Now it's all good. I mean, you are running a router, but what's the use of running one router when you cannot, or you are unable to connect it with other machines, or you have no way to do that, right? So there is a way to do it. And for that, you need to create a file with no extension. Just the name of the file should be netmap, all in capital. And if I show you the contents of this netmap file that I have already created, is pretty much very simple. This is the one that is of significance value. Remember the router image that I have turned on or I have executed, I had appended a 1 at the end. This one shows that number. So if I had used 2, I would have put in 2 over here. It says, this line says that for router number 1 and its 0/0 interface, which is Ethernet in this case, it should be connected to router number 2 with router number 2's 0/0 interface. So it's pretty simple. Likewise, router 1 0/1 interface should be connected to router 11 0/1 interface. So it's kind of, you do not have a graphical view of the topology, but you can make a topology by hand or on a drawing pad, or maybe in some graphical software that you are using, like in Windows, it's a paint utility. Likewise, if I am using this tablet over here, I can simply show you that I can generate something like I've got a router over here, or maybe this is connected in this Trika, and these are interfaces, let's say 0/0, 0/0, 0/1, likewise 0/1, and say 0/1 should be connected to 0/0. So just these 3 routers I can generate, or I can write that nmap file in this way, that router number 1, 2, and 3 interfaces should be connected in this manner, the way that I am showing you right over here. So just give the router number a full colon and then the interface number to be connected with the other router's interface number. Now, a while back, I reckon a year or so, it's February 2016 at the moment, and I reckon back in 2015, by mid of 2015, there was a product by the name of IOU Web. So in fact, this guy developed a web interface where we can make this topology, and we would have been able to execute these IOU softwares. Now this product is no more supported by the developers. This has been replaced by UNet Lab that I might show you in the upcoming video. But you can still find this IOU web software, and I might be able to upload it in the repository of these lectures, or you can search it around by this particular name, and I'm sure you will find it through the search engines. Now, what it really has, let me just remove this one. And so this is the package that is for Debian. Its only size is 3.8 megabyte. It has got nothing heavy in it, just a couple of web pages, I would say, and symbols to really help us in making our topology. So these are the etc, and in order to run it, you need to have Apache software on your Linux machine. Like I'm using Ubuntu at the moment, and I have got Apache server, so I just need to run it, and this will be executed. So since it's a Debian package, I just need to double click it using my software center, Ubuntu software center, and it will get automatically installed in the system on those particular paths where they should be placed. And after that, when I execute the Apache server to run it, then I should be able to access the web interface through my web browser. And let me just show you how to do it. So I bring up my terminal, which is here, and since it's a service, I need to execute this command using root privileges. So I type in sudo service and the service name, which is Apache 2, and after that I type in start so that I can start the service. I give in my password, and once the service is started, which says that Apache 2 could not have it does not really matter. The point is that it has given me the OK output, which means the service has started. And if I type in, let's say, if I want to find the status of this service, I see that Apache 2 service is now running. Earlier it was not running. So now I open up my browser, which is here, and I simply type in localhost or the IP address of my local machine. So I type in localhost, and this is the interface of this IOU web. So these are a couple of labs which do come along with the software, but these are the ones that I have built myself, this BGP and these test ones. But to create a lab, you need to click on this icon over here, which says, just hang on for a while, it says add new lab. You can also create your own folder, and in that folder you can create many labs. So let's click on lab. So once I click on this lab, it says me that what name I want to give to this lab. So let's call it maybe my lab. And after that, if we want to give any description, so let's say call it my lab 1 maybe. Let's leave it my lab. And now if I bring it down a bit, if you want to add any additional info, you can write it over here. I do not want it at the moment. And this is the key point. This is the netmap file that I had told you about earlier, that you need to put in the parameters over here, and it will automatically generate a netmap file related to this particular lab that you are trying to create. So let's say that I want router number 1 to have its interface 0/0 connected with router number 2 interface 0/0, and router number 2 interface 0/1 should be connected to router number 3 interface 0/1, while router number 3 interface 0/0 should be connected to router number 1 interface 0/1. So once that part is done, I come down all the way and I click on add. Now once that is added, this file, it has generated me these parameters that I need to put in the device. These are the IDs. These have been taken up from these values 1, 2, 3. And now I can name them so that once they are shown on the topology in the graphical view, it is easy for me to pick the names up. So I can simply type in R1 maybe, R2 and R3. And from here it is asking me what images I want to use for these particular devices. So let's say I want to have layer 3 images for all these 3 devices. And after that, any RAM or the Ethernet or serial interfaces that if I want to add or change. So let's just leave these settings at the default, and if I type in save or click save over here, once it is saved, we see that we have this lab over here by the name of my lab. If I click on it, it takes me right through the lab, and I can move these icons around to look it more sensible and more presentable. Now I can save these positions so that once I come back to this topology, I see that my symbols are not jumbled up like they were earlier. Now to run the devices, you can come on to devices over here, and from here you can run any of the device or all of the devices that are in here. It is also supported by Wireshark, which is packet capturing software. But if I come on to diagram and maybe click on it one more time. So if I click on R2, and from here over here, alright, so maybe the options are up here, I cannot really see them, but let me just pull it down like this. And from here I can stop the devices, but I cannot really start one, so I need to go to devices, and in the devices, let's just say I want to start R1. So once it gets started, you see the symbol gets green from red, and likewise if I come to diagram, we see that the symbol has turned from red to blue. Now how to connect this device? If you point your pointer on this router, and let me just grab my pen. If we point this pointer over here, we see that we will see a value at the bottom somewhere here. Let me just write it clearly. So if I bring my pointer over here, you see the value which is localhost and the port is 2001. So I need to telnet on this port and I'll be able to access router number 1. So let's see if we are able to do that. Let me bring up my console and maybe this one. Okay. So I type in telnet is the protocol that I want to use to connect to, and localhost, and after that the port which was 2001. So we see that I'm able to get connected to this router, and it was also displaying over here the name of the router which was R1, which is over here, and just let it complete boot sequence. So we are in. Likewise, we can connect to other routers as well. If you bring your pointer over here, we see that the port is 2002, the port for this router is 2003. So really a very good piece of software. It's not available anymore. I mean, it is available, you can search it around through the search engines, but it has been modified into a better product, and that better product is now called as UNet Lab, and the way it has been done is just that it's just a virtual machine. So all these functionalities have been put into virtual machine, and now you can use it on your Windows machine as well as on Linux machine, while in this case this was only supported on Unix environment. So I'll talk about that later, but over here I'm gonna end this video, and I hope this has been informative for you, and I would like to thank you for viewing.
Hello friends. Well, in the previous lectures we have seen how we can use GNS3 to emulate iOS images based on dynamic server, and we have also seen iOS on Unix functionality, or as we call it, IOU. Well, what GNS3 developers did is that they integrated these IOU features with GNS3, and the great benefit that we get out of that is that we can emulate and practice switches functionalities and commands within the GNS3 topologies. Of course, there are limitations of IOU layer 2 images that I talked about, but still for CCNA, CCNP, and for your actual deployments in your ISP, most of the functions are available, and it's really a good feature that it has been integrated in GNS3. So let's see how we can get this functionality achieved in GNS3 with support of IOU images. The first thing that you need to have is the GNS3 virtual machine. It's an over file that you can get downloaded from internet, from search engines. If I show you over here, the one that I've already downloaded is this one, GNS3 IOU VM version number 1.3.3, and also make sure that the GNS3 version that you are using as an overfile or virtualized machine, it can only be imported or used with the GNS3 version of the same number, that is GNS 1.3.3. So my point is that if you are using overfile of, let's say, 1.3.4 and GNS3 version maybe 1.2, then they would be incompatible, they would not work together. So make sure that these two are of the same version number. I have searched on the search engines and I found that these two 1.3.3 are best suited for this type of configurations. So try to get the same. Now once you get this OR file downloaded, you can get it imported into Oracle VirtualBox, which is over here. I have already imported this file and I have not changed much as far as settings are concerned. I've just gone into settings, and the one change that I made, you can leave the setting into host only adapter, or maybe it's up to you. Change it, leave it to host only adapter. And also, if I show you the preferences of the VirtualBox itself and in network, I have given the IP address of this host only adapter which is connected with the VirtualBox, and I had given it the IP address of 56.100. Also, if you need to access this virtualized machine through your computer or PC or whatever you are working on, you can create a loopback interface and assign it the IP address of the same class that this VirtualBox is on. And the way to do that is if you go into Windows Device Manager. At the moment I am working on Windows 7, so let me just pull up control panel for Windows 7, and in that I click on System, and in System I go into Device Manager. Over here, let me just click it yes because it requires administrative privileges. Over here, if I click on the name of the machine and manually add legacy hardware, click on next, then search the hardware through the available list. I click on next, and over here let's bring it down to interfaces or network adapters. Click on next, and after here click on Microsoft, and from Microsoft sub list you can select the loopback adapter. You click on next and it will install the drivers, and you will get this kind of, let me just expand it, this kind of adapter in your network settings. And you can, just like going into the, let me just bring it forward. So I go into control panel, and in control panel, after adding that loopback adapter, you come into network and sharing center, and from here I click on the change adapter settings. This is the loopback adapter that we have added. Simply click on it, change the settings, and assign it the IP address of the same class that you had used for your IOU virtual machine. I have given the IP address of 56.1 to this laptop. The IOU virtual machine is residing at 56.101, and there is a reason for that. You can change it, of course, there is no problem with that, but by default it's 56.101. So if I click over here, and if I show you that how we can add that IOU virtual machine, first thing you need to come on to server. Now local server is enabled, that GNS3 will start its local server as well, but also add on a remote server. And remote server is the GNS server which runs in the virtualized machine or in the VirtualBox that you have imported. Now by default this entry is here, 192.168.56.1.101, and a port 8000 TCP port. Once you click it add, it appears over here. So you can change this IP, but make sure that the IP that is over here, it is reflected in the virtual machine as well. So these are significant value that you need to match on both sides. So coming back to VirtualBox IP addressing, let me click on File, Preferences, and Network, then in Host on adapter, and click its IP address setting. So this is the IP address of the VirtualBox for this particular machine that I am trying to configure. I have given it the IP address of 56.100 because the machine itself, which is over here, this one, it is running, I believe, Debian operating system, And once we open this machine or log into this machine, we will give it the IP address of 56.101, which we will be using in GNS3 setting that I have just shown you. So let's now try to start the virtual machine. Just give it a second. Once it gets started, it will give us the prompt for the username and the password, and just hang in there for a while. So once it gets booted up, we get the login prompt. The default login is the root is the username and the password is Cisco. So once you do that, you get logged into the machine, and over here this is GNS3-IOUVM is the name of the machine. You need to remember this thing because it will be reflected later in this lecture. And for your own configuration as well, do remember that you might need to keep it the same as this, or you might need to change it because this is used once we are using the license file for IOU images. So host name is very much important. Now coming on to the interface configuration portion, you type in ifconfig, and we see that at the moment Ethernet 0 is not configured with any IP address. We need to assign it an IP address. You simply give the command ifconfig Ethernet 0 and then the IP address 56.101 and also add a subnet mask of 24. Now once you do that, this virtualized machine, it should be accessible from your PC or laptop through loopback interfaces. Now if I come over here and if I try to ping this IP address, I can access it. So we have the connectivity. Now what you need to do is that you need to open this machine into a web browser to add the IOU images into this virtual machine. Of course you can do the same using let's say FTP protocol or even SCP protocol, secure copy protocol, but you can use the web functionality as well, which is built into this virtual machine. So you simply need to pop up the browser like this one I have, and if I give the IP address, let's just say 192.168.56.101 and port is 8000. I click or type enter and we see that we are presented with this information. I click on upload images, and over here I have already uploaded these images. You can repeat this exercise on your own. Simply click on browse and give it the path of IOU images that you have got. Also make sure that you select the IOU license file and upload the images and the license file into your virtualized machine. Now, like I said earlier, that you can create your own license file using the script that I had shown you and we have discussed about it, or maybe you can use this particular IOURC file for this very host name, which is this one, GNS3-IOUVM. You simply need to search the web and you will find the corresponding license file against this host name. So once you do that, you upload the IOU images and the license file. Come on to GNS3 in preferences, and in iOS on Unix, give the path of the license file. You can get this path from here. Once you get the license file uploaded, you see the path where it is residing. Simply copy this location and put it in the path of GNS3 license file location. To add on IOU devices, the procedure is the same. Click on IOU devices. I have already added one, but does not make any difference. You simply click on new, and over here you click on next. Just click on OK, and over here give the name whatever you want to assign. Let's just type some garbage name, and over here you again need to define the image name. And from the web browser, once you get the IOU file uploaded, you see that this is the path that you get. So simply copy this path, like I have copied using Ctrl C and put it over here. And once you click on finish, your image will appear like this one over here. I just added one layer 3 image. It does not I do not need to show you how you can add more number of images. It's just the same function that you repeat for each and every image that you want to add on to this IO device template. So once you get the images uploaded and the important file, which is the license file, you should be able to run your IOU devices, and not only IOU devices, but also you can get the IOU devices connected with your Dynamics based Cisco iOS emulated softwares. So let's say if we have got this device over here, and if I pull up another device which is over here, and let's try to connect these interfaces. Now these two devices that I have added. You can simply change the symbol at the moment it is showing it as a switch. You can change its symbol to make it look more clear, as this is the layer 3 image that I have used. So I have changed it to the symbol of router. Likewise, change this one to router symbol as well, which is over here. And let's try to connect these using Ethernet 0 interfaces. If you have got dynamic based images of Cisco devices, you can simply add them as well, and they will just get connected through to IOU images. So it's a very good functionality that IOU and dynamic based images run in the same very GUI interface. Now simply click on run these devices and open up the console. So once these devices get booted up, we should get the prompts for both of them, which we do. This is the router number 1. You can simply change its name to router number 1 or whatever name you like to have, say R1. And over here, if I get into the particular interface, which is Ethernet 0/0, and give it the IP address of 1.1.1.1, subnet mask of 8, do a no shut for this interface, and likewise click on the other router that we have just added, change its host name to make it look like R2 or router number 2, then get into the interface which was Ethernet 0/0, give it the IP address from the same subnet range with the subnet mask of 8, do a no shut, and ideally we should be able to ping the router's interfaces of one and other. So if I come on to router number 1 and try to ping the interface of router number 2, which is 1112, we should have the connectivity, which we do. So a great product and feature that you get through GNS3 with embedded IOU support. Do practice around with this one. I hope you have liked the video, and I would like to thank you for viewing.
Hello guys. So in previous lecture I told you about IOU and also IOU web, and in that very lecture I mentioned about this product which is now known as Unified Networking Lab, because IOU web is no more supported by this developer who is the author for IOU web, and now the renamed product, and this guy says, and I believe that it's like that this Unified Networking Lab, although it has been called as the upgrade version of IOU web, but it has this application UNL, it has been written right from the scratch. And what it really gives us is a end product which is a virtual machine that you can use in maybe VirtualBox or in you can say virtual VMware workstation. So VMware workstation support is there. VMware client you can use it in, or you can also use it in Citrix servers. You can use Zen server if you want to, or in ESXi server. So a broad range of programs that you can run this virtual machine in. Now the true beauty of this program, it comes in not only because of this virtual machine, but because of the number of platforms and appliances that this new virtualized environment supports. So this is the website of this wonderful product, which is unetlab.com, which you can see over here. And if you click on docs and on images, then if I scroll it down below where it shows me the detail of the images, then really look at this one. Look at the supported images on UNL. We can use Dynamics, which is the default for GNS3 that I had shown you earlier. It also supports IOL. So same platform supports multiple types of images. It also supports QEMU based images, like we can see that it supports Cisco ASA firewalls or ASA virtualized firewalls. It also supports access controller servers, IPS or ISE devices from Cisco, which are Identity Services Engine. It also supports high-end Nexus operating systems, Titanium. And if I bring it down, look at this. You can emulate Alcatel services if you are able to find the right firmware for this service router. You can emulate that router in this platform, in this virtual device. You just need to have that particular software version that this product is supporting. Likewise, you can use Aruba network security devices, which is ClearPass. You can use Brocade, or if I come it down below, you can even use F5 products. You can use Juniper, of course, then Palo Alto. So a complete range of devices and specifically their models that this product supports. And it was released in 2015. Earlier than that, it was IOU Web that I have already shown you. But since then, it is still in the development phase. So if you are kind of stuck somewhere, I would recommend that you explore the forums that are down below or the user posts down below, and maybe you can find your answer, because this is not still the finished product. The developer is still working on it and trying to improve it with each and every day. But still, it's a wonderful product, and the great feature is that it's free and supports multiple platforms. So if you need to use it, you simply need to come on to the download link. You click on the download, and if I bring it down below, it says me that these are the two options that we can download from. So you just click on it, and once you get the image, you should have something like, let me just show you the image. So this is the image size, and I believe its size is around 500 something. So yeah, so 560 megabytes. This is the OVA file. You need to import it in the platforms that I had already mentioned. So once you get it imported, which I have done over here, this is the imported OVA file. There are not any particular settings that you need to be aware of. If I show you this, I have allocated it 2 GB of RAM, but if you are having more RAM, the more is better, of course. Some of the guys that have commented on this forum, they say that they have used this wonderful product in their ESXi softwares, which is a virtualized environment from VMware, and they have allocated even 64 MBs of RAM. So higher the RAM, the better it is, so that you can emulate many devices in one big topology. Likewise, if I show you the processor, I have enabled physical address extension, and I have just allocated one CPU for making of this video, just to give you an idea that how you can use this product and how you can build upon to make large and complex topologies. Just need to give it physical resources so that it can work well. Likewise, for storage, I did not need to do anything. I simply imported this device, and it has got this disk in it. For networking, I have binded this networking adapter of this device with the VirtualBox interface that I have created with the name of VBoxNet0. I am working on a Linux environment at the moment. It's Ubuntu, but for Windows, the things will be more or less the same. You just need to maybe tweak in a couple of things with regard to Windows. And of course, if you come on to the website itself, they show you that how you can download and install the particular product. For example, if I come over here and click on how to, and once the page gets opened up, if I bring it down below, so it says that if you need to follow this procedure if you are doing installation of VMware player or VMware workstation. For ESXi, you need to follow this one. So if you get stuck somewhere, which I really doubt, because it's pretty simple and straightforward procedure to get this product up and running. I had difficulty in importing this device because I did not use 64-bit architecture. So specifically I created Ubuntu machine with 64-bit architecture, and now it's running good. So if I show you over here, you can see that the operating system Linux and the version is Ubuntu 64-bit. So what I'm going to do is now power up this device and take you inside that what options we have in there. So let's just power it up, and once it gets started and completes its boot sequence, we should see a UNL logo and its interface in this window, which is over here. So let's boot it for a while, and let me just hang in here for a while. This is, by the way, Ubuntu server, Ubuntu customized version that is running in here. So once it gets booted up, you get this prompt, and this is the important thing where it says that default root password is UNL. So I type in root, and the password that it has already shown us is UNL. So once I do that, I see that I have entered into the machine, which is Ubuntu server, which is written over here as well. You can see that welcome to Ubuntu. My cursor is not coming over here because this is the terminal that is kind of default, comes in with the VirtualBox for Linux environment. So, and one more setback of this terminal is that there is no scroll bar on the right. So once the command or the output goes up, I cannot really see what has gone missing. So what you can really do is that you can SSH to this device using terminal. If you are using Windows, you can use PuTTY or any other terminal program that you are comfortable with, which supports SSH protocol. You can do an SSH and log into this device. So let me just show you. Let me bring up my terminal, which is over here, and I'll just telnet this IP, which is 100.1.1.2. But before I do that, I showed you that the network interface was connected with VBoxNet0. So if you are in Windows environment and you have created a loopback interface, maybe, or if your VirtualBox that or maybe any virtual machine device that you are using, and you are having its interface which is having a different IP address, so you need to set that IP address of the same class as this IP address, which is 100.1.1.2. So if I come over here and show you the IP addresses, at the moment this VBoxNet0, which is the interface connected with this virtualized device, is having an IP address which is different than 100.1.1.2. So really there are two options: either I change the address on my device, or I change the device, or I change the IP address in the virtualized device. So let's change it on my side. Let's quickly do an if config, and the name of the interface, which is VBoxNet0, and then the IP address. Let's just say that 100.1.1.1 will submit mask of 24. So now it is asking me for my password, which I do provide it, and now I should be able to ping these virtualized machines interface, which is 100.1.12, which I can. So next step, I can simply SSH this device with root login and putting in the IP address. It asks me the password is UNL. So once I logged in, you can clearly see that now I am in the UNL device, and now I can really scroll up and down and show you in a better and comfortable way. So let's just minimize this one, which is the default window for VirtualBox, and from here the things are more or less the same that I told you about for when I was doing the lecture on IOU, that you need to have a license file in case you are going to use IOU images in this virtual machine. This machine also supports dynamics, but you need to put in the images at those particular locations. Like if I take you to that particular location, which is CD, you change directory, then OPT, and show you the available options. Then we see that I have got unit lab, and if I do an enter over here and show you the contents of this particular directory, we see that we have got an add-ons, data, HTML, labs, wrappers. So important ones is add-ons, and of course every directory is important, but from the perspective of this video that I am making at the moment, this add-ons is where you put on your images, your actual iOS's or IOL images or Juniper images or any other Chemo images that this particular platform is supported. You need to put them in here. Likewise, these labs, these will contain the data that when you create a lab, that lab information will be saved over here. So let's just go into this add-ons folder and let me show you that what we have got in here. Now I've got Dynamips folder, IOL folder, Chemo folder. This Chemo and IOL, I believe, are there by default, but if they are not, you need to create them. You create them as they are created over here. And if you are trying to use something which you may not find in this video, then I would recommend that you have a look at that particular website that I have shown you, that which is unitlab.com, and find specific information about the firmware that you are trying to use. I have used Dynamips and IOL, also Cisco Chemo, so I have created or one of them or maybe all of them. I am sure that I did create Chemo folder and Dynamips a couple of weeks back before when I was testing this product to make you familiarize as well. So for Dynamips, if I show you the contents of Dynamips, we see that we have this image which is for router 3725 series. The image is Advanced Enterprise Class, and this image is supported by this VM machine. So you need to be careful while putting in images, that only putting those images which have been mentioned in that list and which are supported by this platform. Likewise, if I show you the contents of IOL images and maybe bin, then these are the images and this is the license file for this particular machine, because I told you that license file needs to be created for that particular machine as it takes into account certain parameters, and one of those parameters is the machine host name. So the procedure will be the same, that you can generate the key for that particular machine and create a file by the name of IOURC and put that generated key in that file. And these are the two images for layer 2 switches, and for layer 3 that I have put in here. Make sure that for Dynamips the extension is image, and for IOL the extension is binary or bin. Similarly, I can show you the contents of Keymu folder residing in add-ons, which is over here. This is the ASA folder that I have put in, and in that folder these are the default, I believe, default 5 images, or maybe I need to put it like this. So HDA QCow2 and HDB QCow2, they relate to the ASA firewall. And if you want to add Dynamics image, what I did and what you can do as well, you can simply use FTP protocol or SCP protocol. So since SSH is already running on this virtual machine, by default, you do not need to enable SSH in this machine. Likewise, secure copy is also by default enabled on the machine. So if you need to securely transfer the files into the machine, you simply come to your terminal or whatever client you are using to access that particular machine. And for example, I can use SCP command, which securely copies the data. So if I type in SCP and after that space, and the syntax is whatever your particular device is supporting. So over here I can use it like I have a file by the name of 1, and then I need to type in the credentials to log into that machine, which is the root username, and I can type in the IP address, and after that full colon and the name of the file that should be, while it is copied onto that particular virtual machine, what name should it carry while it is being saved on that machine. So I keep the name same, which is 1, matching with this one which is on my machine, and I press enter, and after that I need to give in the root password of this virtual machine, which is UNL. So once I do that, I see that the contents have been copied and the contents are placed in the root folder. So if I come on to this virtualized machine console and I type in cd and tilde sign, I press enter, I go into the default folder of the user root, and over here if I type in ls or list to show me the contents of this folder, I see that I have got this file which is 1. Now just like that, you will need to copy the images that you want to emulate in this device, and then from here you can move them around into those particular locations. Like for Dynamics based images, you need to put them in Dynamics folder. For IOL based images, you need to put them in the directory add-ons that I just showed you, add-ons, and further in binary folder. Likewise for Keymu, you need to put them in Keymu folder, and similarly for other images which are supported by this particular platform. So continuing from previous video, once you get your images copied into the virtual machine, and if I come on to the website and show you that if you want to add in Dynamics images, which is the portion of documentation over here, sometimes what really happens is that while you have added the images, it does not get booted up. So and the problems could be because of the wrong permissions that are associated with those particular files. Since this is the Linux environment, so we need to be careful about the permissions that what programs are authorized to execute those files. So to fix those permissions, there is a script in the virtual machine. You just need to execute it, and this is over here, that in opt unit lab wrappers, and you need to execute this file, which is unl wrapper -a fix permissions. So that should really take care of the permissions problem as far as configurations and adding of images in the virtual machine is concerned. For Dynamics, you can also use this portion of the documentation which says that you can calculate the idle PC values for your particular routers. So really just need to follow along with this. It's not that difficult. Once you follow it, it will become pretty much easier. So let me just come back to the console of the virtual machine. So I have already edited the dynamics image which I have shown you, and a couple of IOL images that I just showed you, that one was for L2 or switching and the other one was for L3. Also the license file has been created. Now how to access this and how to run the images. The good thing is that you do not need to install anything or any client. You just need to open up the browser and access the interface, which interface IP address that I had shown you earlier, which was 100.1.1.2 for my machine, which I'm using at the moment, and just point your browser to that particular IP address. So if I come over here and try to open it by typing in the IP address, you see that I have opened it, and the username and password is admin and UNL, same as root. So once I get logged in, this is showing me the system status, that how much CPU is being used, how much memory is being used. Since I'm not running any virtual machine, so it's not taking any memory uses at the moment. If you are using, this is important, if you are using a SAR firewall and you have allocated, let's say, one CPU for this virtualized machine, then a SAR firewall take, I would say, around 80 to 100% of your CPU. So make sure that while you are trying to emulate a big topology, you give them enough resources. So to create a topology, you need to click on labs, and you can create a folder over here as well by clicking on the actions and maybe add a new folder or add a new lab. I have already created a folder by the name of test. So if I click on it, it shows me the lab which I just prepared before the making of this particular lecture. It has got nothing. I just needed to add a few images and show you that how we can do it. So in order to add an image, you need to click on actions, and whatever the lab that you had created, of course it is showing me these three images, and one of these two routers are connected as well. But when you open your lab, it will have nothing. So you need to edit this lab, click on this one, and now it is in editing mode. So to add a node or a network, that for me is the wires or the link that will be connecting those particular nodes, you need to click on actions, and let's click on nodes. Now once I do that and I pull down this menu, look at this. Look at the options that you can select over here, provided you have got the image for that. So let me see if we can have Cisco 3720, because this is the image that I have already got in my folder of this virtual machine that I have just shown you. So let's select this one, and the number of nodes to add, let's just say that I want to add one node, and the RAM that I want to allocate it to, which is 256, and the RAM is 128, and the slots or the interfaces that I can further add into this. So by default, this Cisco 3725 model, if I do not add any interface, it has got two Ethernet interfaces. So you can add in further interfaces if you want to. So I just click on add, and we see that now we have this node. Earlier this was here. I can remove this one, or maybe, so click on right click and edit, and then delete. So the node gets deleted. This is the one that we have just added. You can move it around as per your requirement or whatever gives you the visual righteousness as far as topology is concerned. So let's just try to link this router, which is IOL, I believe. Let's just try to add another node and maybe remove these ones. So remove this one and remove this one as well. So now we have got only one Dynamics router. Let's try to add another one. by clicking on nodes and select the same one with same parameters. So once it gets added, now we see that we have got two routers. We can name them by doing an edit, and let's just call it R1 on the left side, and this one which is on the right side, let's just call it R2. So you can even change the symbol if you want to. Now to connect these devices, you need to go into Actions and click on Networks, and from here you can select the number of networks or the number of links that will be used to connect the two interfaces. So I am going to use only one network because I am just going to show you that how to connect two interfaces of two devices. And the type of the link can be bridge. Primarily the bridge will be used because that's the link type which is used to connect to Ethernet interfaces. These are the virtualized link types that you can use. So I click on bridge and add. Now the link is created, or the network type is created, but is not being shown. So if I click on R1, right click and click on its interfaces, it says that it has got two default interfaces, FA00, FA0.1, which are in disconnected state. I can get them connected to the interface that I just created, which is that since these I had created earlier, so it is showing me these as well. But you can remove them if you want to. So let's just click on net and click on save. So we see that this is the net or the network type that was created, and we see that it's one of the interfaces connected with R1 fast Ethernet 0.0. It is looking a bit odd, I can clearly tell, but let me just show you that when I connect this particular network with R2 interface, it will look very much better. So let's just click on interfaces and select that particular network, and now you see that it's a lot more better, and you can move them around as your personal liking. Now once you are done editing with the lab, you can open this one, and now it's in a mode where you can start or stop the particular devices. So to start it, just right click on it and click on start. Now it also gives the message that node started. Again, to access this, you can see in the left bottom of the screen that says that you can access this device by doing a telnet to this particular IP address, which is the virtual machine's IP address, and then the particular port, which in this case is 32,770. So let me just pull up the terminal and let's try to telnet 100.1.1.2 on port number 32770. So I am able to telnet it. It has already booted up, and you can see the version is Cisco 3725 platform, and the version is C3725 advanced IP services. So from here it's the same thing like any other Cisco device. You can execute the commands and you can do the topology. Now to run the second device, I simply need to click on it, click on start. Once the node gets started, I need to see that which port it is connected to. It is 32769. So if I bring up another terminal window and telnet it on that particular port, which is 32769, and I can access that device as well. So both the routers are accessible. I can do the configuration. Let me just quickly do the interface configuration and see if we are able to ping the interfaces of each router. So the interface is fast Ethernet 0.0 and the IP address, let's just give it an IP address of 111. Do a no shut, and likewise if I come on to router number 2, going into the interface configuration mode and giving the IP address of 112, the subnet mask of 8, doing a no shut, and from here let's see if we are able to ping the interface of the router number 1 with IP address of 111. So we can access it, connectivity is there and devices are working properly. Now just like these dynamics images, I can also add in IOL images. I just need to go to editing mode of this lab, and from here I can click on loads, and this time I need to select in the Cisco IOL type of images, and these are the images that I have already added, and I have shown you that one was layer 3 and the other was layer 2. Make sure that the images names are exactly the same as that supported by this virtual machine or as they are mentioned on the website of Unit Lab. So once you do that, I click on add, and we see now that we have another router which is an IOL router. So let's try to connect this one. Its port is 32771. So let's again first open this lab, and from here let's try to turn this router on. So let's just hang in there for a while, and once it gets on, we see that symbol has also changed from stop to play. And if I come over here, and maybe I can get out of this. Okay, so I cannot because it has made the session, so I can really, it does not matter, I can really pull up another terminal, and from here I can try to telnet to access this router on that particular port, which was 32771. So let's give it a while so that its boot sequence gets completed. The connection has been established. In the back end, the boot sequence of this particular IOL image is running, which takes a while, and once it will get completed, we'll see the same prompt regarding auto install, which we'll do. So let's just terminate this one and give it a while. So if I get into the enable mode and type in show version, it shows me the image location that I had shown you, OPT unit lab from where this file is being read, and also the image which is over here, Linux image, and it's for advanced enterprise services. So a really cool piece of software, I would say you must try it. It seems like a bit of for advanced users and for users who have a little bit knowledge about Linux, but if you do not, even if you don't have that, you can simply follow the instructions that I have given in this video, or if you are using another image that has not been covered in this video, you may go to that particular docs section of this website, and I'm sure you will be able to find the particular help for your image. But of course you need to have, first of all, you need to have the image with you to run it. So do try this piece of software, and I hope you have learned from this video. Thank you for your watching.
Hello guys. So here's the scenario that I have built for you so that you can practice it on your own, and this kind of scenario that you can encounter in many of the small or medium footprint enterprises and organizations. And I have tried to cover as much protocols in here and as much variations as far as routing is concerned so that we can do it all in one big figure. But definitely we will do the configuration in steps. And before we do the actual configuration, let me just take you quickly through this topology, that what we have here and what we will be trying to achieve. So considering this portion, let me just draw here. Consider that this portion onto the left side or onto this side, this is the organization portion, and these two routers are outside the organization, or you can also consider them that they belong to different organization or maybe different ISP. Maybe they are providing us uplink connectivity for internet services. Now coming back to these routers, these 5 and 3 8 routers, what I have done here is that this red, I'll be running RIP protocol, or we can consider that this is a remote office which is connected through maybe gigabit Ethernet interfaces to this R5. This R5 and along with these routers, they can be considered as belonging to the headquarter. And this R1 and R2, they may be belonging to the remote office. But these might be of lower end routers, and they may not have the resources as far as CPUs or memory is concerned to run other higher end routing protocols. And besides that, we really do not need much complexity in this network, so we decided to run RIP protocol over here. Likewise, onto this side we are running EIGRP. We have only Cisco routers over here, and we'll be running, and they are of that much capacity that they can handle EIGRP. So we are assuming that this is another branch or a remote office, but it is of somewhat high value and has resources which are able to run EIGRP protocol. So we'll be doing that. And likewise, these routers are connected through R5. You can assume that via Ethernet links. Now within headquarter, where we have got 4 routers, I have configured, or we will try to configure these routers R5, 6 and 7 interfaces, where this green circle is connected. Those interfaces will be considering that these interfaces are in OSPF area 0. But over here, this R8, let's assume that this is a branch location, or maybe a location where it may not be a branch, but an office within our main building, where we do not require to be part of all these 3 routers, because then if any change happens within these routers, then whole SPF calculation will need to be provided over to this area as well. And likewise, if a change happens onto this side, like maybe we have other routers connected over here, then if any change happens in area, if they had been in one area, then all these routers would need to get their routing table and update it by running SPF calculations. So we are trying to break the SPF domain into 2 areas, area 0, which is the backbone area, and area 1, which we will see that what we can configure them as we go along with these videos. I will show you that how we can configure area 1 as stub, where stub area would block the routes that are being sent from external sources or from organization which are outside our organization, or we can also say that protocols which do not belong to OSPF. So any routing information which does not belong to OSPF protocol will be considered as coming from an outside source, or these routes are marked as external routes, either E1 or E2, depending upon how we are redistributing the metrics into the OSPF. So just remember that E1 and E2 type routes are marked to show that the routes are coming from an external routing protocol. It could be BGP or EIGRP or RIP or maybe even static routes. Now, as far as this connectivity is concerned, we will be running a BGP session between R6 and R9 to emulate that if we are connected with an ISP, which is R9. And likewise, R9 and R10, they will be connected among one another using iBGP protocol, which is nothing but a variation, or I should not say a variation, rather a mechanism by which we run BGP within the same autonomous system. So another important thing is that this, I will be assuming that this is one autonomous system. Let's call it autonomous system number 1. And this will be another autonomous system. Let's call it autonomous system number 2. So a pretty common scenario that you can build by yourself as well, and that you may encounter while you are on the job, that you have to connect different branches using different protocols and provide them connectivity, central connectivity for internet resources. So now let's go ahead. I hope you have got the idea about the topology, and let me just quickly also mention over here before I move on about the IP addressing scheme. This is also very important. I'll be using let's say 10. Let me just point over here. 10.1.1.x network /24, maybe not 24. In fact, I need to break this down, so I'll be using 0/30 onto this segment, and then onto this segment over here I'll be using 1.4/30, 10.1.1.4. Likewise, if I come onto this side, I'll be using 20 network .1.1.0, so 0/30, and over here I'll be using 20.1.1.4/30. Onto this side, I'll be using 30 network, likewise broken into /30 subnets, and over here I'll be using 40 networks, and maybe another 40 over here, or maybe we'll be using 50. I have not planned that. So just watch out that while we'll be doing configuration onto this side, I'll be using 10 over here, I'll be using 20, then 30, then 40. So if you need to write them down, the IP addressing scheme according to this topology, you should go ahead and do it right now, because then you may not be able to understand when I'll be doing the configuration that which IP address scheme belongs to which router. So now let's get ahead, and let's first start off with these two routers and this R5, and let's just quickly try to configure RIP protocol so that these three routers have visibility of their networks with one another. So here we are. I have started these three routers R1 to 5, and let's bring up R1 console and let's start with the configuration. Right now it's just default. If I show you the running configuration at the moment, we see that we have no IP address and no protocol rated configuration. As such, is just a default configuration. So let's quickly try to configure it by typing in configure T, and the first thing that I like to do is first configure the console line so that we can get this synchronization while we have these pop-up messages that come up onto the console. So I type in login synchronous, and also I can type in execution timeout so that the console never gets timed out. Then after that, I also like to do IP domain, or I should say no IP domain lookup. Now let's come on to the interface, which is FA0/0, which is connected with R5. I am configuring R1 interface at the moment. So I come on to FA0/0 and just double checking this one, and I type in the IP address, which is IP address 10.1.1.2. let's say we'll be doing 10.1.1 on R5 interface side. So, and the IP address is, give it a subnet mask of /30. Do a no shut. Likewise, configure the other interface, which is connected with R2, by typing in the interface and then the IP address, let's say 10.1.1.5, and do a no shut over here as well. The next thing, we need to enable RIP protocol onto this router, and specifically version 2 of RIP, and then give the network as 10.1.1.0. It does not really matter how I define it, because really what RIP protocol does is that whatever network I define over here, it will automatically start the RIP process or RIP updates, send and receive on all those interfaces which will fall under this network command. So if I do specifically 10.1.1.2 and then 10.1.1, or I should say 10.1.1.0 and 10.1.1.4, it will automatically summarize them and show them in configuration as a single statement. So we can do that just to show you that the first network is this, and besides that I cannot really define subnet mask in RIP protocol. So I just type in network and the network number, and also the other network is 10.1.1.4. So if I try to show you that what configuration do I have at the moment by typing in show running configuration, so we see that it has kind of summarized it just to show us by one classful address. Also, I'm going to type in another command which is no auto summary, so that when it is sending updates to other routers, it should not summarize them into class full addresses, rather send them along with their subnet masks. So I type in no auto summary. Now let's come on to router number 5 and do the corresponding configuration for RIP protocol. So I quickly go into line con 0, logging synchronous, then no IP domain lookup, then interface FA0/0, and the IP address was 10.1.1.1 with a subnet mask of 30. Do a no shut, and now come into RIP process with version number 2, and in here I define the network which is the same, which was 10.1.1.0, and no auto summary. Now once that part is done, let's bring up router number 2, which is over here, and do the RIP related configuration in this router as well. Let me just quickly configure the console parameters and also disable the IP lookup. Now coming into the interface, which is FA0/1, and typing in the IP address, which was 10.1.1.6, because 5 was on router 1 side, so I'm giving 6 on to router 2 sides, and the subnet mask of 30. Do a no shut, and let's also configure loopback interfaces onto this router, so that we will try to emulate that we have got some other networks connected with this router, and the networks that we can add over here could be 1.1.1.2, and also let's say 1.1.1.21, 22 and 23, so that we will be assuming that these are 4 different networks that are connected with R2, and we will be redistributing or not redistributing at the moment. We will be sending those networks via RIP updates to R1 and R5, and they should be learning about those particular networks. So let's do that. Let me bring up the R2 interface one more time, and let's just type in interface loopback 0, and then IP address 1.1.1.2 with a subnet mask of 32, and then IP address loopback 1 with an IP address of, let's say, 1.1.1.21 and /32 loopback 2, and likewise loopback 3. So once all these interface related configurations have been done, let's run RIP protocol on R2 as well. It's version 2, do a no auto summary, and then add the networks that we want to add in, which are 10.0.0.0 and also 1.0.0.0. So if I do a show run, these are the interface related configuration parameters or loopback interfaces, and this is the RIP protocol related configuration parameters. Now at the moment what will really be happening is that RIP protocol will be sending routing updates onto loopback interfaces as well, which we do not really need to this router to do that, because these loopback interfaces are not connected with other routers, so there is really no point in sending updates over there. So what we can do is that we can define these interfaces as passive interfaces, so that these interfaces will be included in the RIP updates going to other routers, but RIP updates will not be sent out to these particular loopback interfaces. So the way to do that is the command passive interface and whatever the interface we want to restrict, like loopback 0, loopback 1, loopback 2, loopback 3. So once that is done, now let's quickly come on to R1 and see what R1 routing table shows us by typing in show IP route, and if I type in RIP, it will show me the routes which it has learned from RIP protocol. So we see that it has learned all the loopback addresses and the connected interfaces are already there, and since the connected interface has higher administrative distance as compared to RIP, so we are not seeing the 10 network like over here, which is like over here this 10 network, or if I come to R2, this 10 network, which is although being advertised through RIP protocol, it has not made its way into the routing table of R1 because that network is already directly connected. So directly connected networks have higher administrative distance, that's why it is not being shown into the routing table, and only indirectly connected networks, which are the loopback addresses of R2, have been learned in R1. Likewise, if I come on to R5, since it is RIP protocol, which is like routing by rumor, so router 1, whatever it has learned, it will forward it to R5, and we should really be seeing the not only loopback addresses of R2 but also this segment address, as it is also being advertised via RIP protocol. So I type in show IP route and then the protocol that I want specifically to have information from, and we see that I have got all the 4 loopback addresses and also the subnet 10.1.1.4 that I was talking about, which is in between router number 1 and router number 2. Now at this point, basic configuration regarding RIP protocol in this branch has been completed, and we have not done anything yet because I'll be doing other configuration that we want to like restrict certain routing updates from being sent to R5, or maybe other things, route optimization that we'll be seeing in upcoming videos. But let's just conclude this RIP related video regarding this topology over here, and in the upcoming video we'll be doing the EIGRP configuration onto R4, R3 and R5 routers. So let's head over there. So here we are. I have started these 2 routers R3 and R4 as well, and I've just configured the console rated parameters on both of these routers. So now let's quickly configure the IP addressing and routing protocol, which is EIGRP. So this interface is 01, which is connected to R5 side. So if I type in interface FA0/1 and then the IP address, which is 20.1.1.2, .1 will be assigning on R5 side, so let's give it 2, and a subnet mask of 30, do a no shut, and likewise on interface FA0/0, which is connected with R4 router, and give it an IP address of, let's say, 2115. Do a no shut over here as well, and then jump into the EIGRP protocol, giving it autonomous system number 1, and then defining the two networks, which is one is 20.1.1.0 with a subnet mask of, or wildcard mask, as I should say it in terms of EIGRP 3, and likewise 21.1.4 and wildcard mask of 0003. Also issue a no auto summary command so that it should also not summarize the routing updates while it is sending them onto other routers crossing over another classful boundary network. So I type in no auto summary, and now let's head over to R5 router, and its interface is, I believe, F0/1, which is connected with R3. So I type in interface FA0/1, and IP address is 20.1.1.1 with a subnet mask of 30. Do a no shut, and also start a EIGRP process onto this router as well, giving it the network which is 20.1.1.0 with a wildcard mask bits of 3. So we should be seeing that neighbor adjacency comes up regarding EIGRP protocol, which it does. So now head over to R4, and let's also configure it with EIGRP protocol. So I first assign the IP address to its interface, which is FA0/0 or interface, and then the IP address, which is 20.1.1.6. .5 was on R3 side, so this is 6 with the subnet mask of 30. Do a no shut, and also define one loopback address onto this router as well to emulate as if another network is connected with this router, and give it an IP address of, let's say, 1.1.1.4 with a 30, or I should say 32 subnet mask. Now come on to EIGRP routing process, EIGRP, and first do a network command for network 20.1.1.4 wildcard mask bits, and also for 1.1.1.4 and wildcard mask bits of all zeros. Also issue no auto summary, and likewise on R5 I missed no auto summary command, so let's do that as well. These are good practices. If you follow these, they save you a lot of time in case you are stuck up in some configuration, because sometimes when you're doing configuration on many routers and you miss a little step, then and you end up in some missed configuration as far as designing of the network is concerned, like you have classful addresses in between other classful addresses, like a broken classes, you can say. So, and if you miss out these no auto summary commands, then really it takes kind of some time, and you get frustrated that why things are not coming up, and at the end of the day it comes out that there was just one command that you forgot to install at the time of configuration. So it's always good practice to start off with the good design and then the best practices that are recommended. So once it is done, let me see if we are learning about the loopback address of R4 interface in R5 via EIGRP protocol. So I type in do show IP route, and then protocol is EIGRP. So we see that I am learning about the loopback address of R4 and also the network which is in between R3 and R4, that is also being learned through EIGRP routing protocol. Now that pretty much covers the basic configuration regarding EIGRP protocol. We have not done much complex configuration at the moment. If we had, let's say, multiple links in between R3 and R5 or maybe between R3 and R4, like maybe this is the branch that it has got multiple, let me just remove this one, which has got higher importance. So we have hired multiple connectivity mediums, maybe satellite, maybe optic fiber and through cable or maybe DSL. Then we can, depending upon our requirements, we can do load balancing on unequal cost path links using variance mechanism that EIGRP provides us. So since at the moment there is only one link, so definitely there is no point of load balancing, but you can have, if you are not familiar with variance, you can have a look at it, or you can, I've discussed this thing in a lot more detail in my CCNA course. So if you want, you can, and if you are already registered in there, you should revise it so that it makes sense to you that what I'm talking about. So in the next video, I'm going to stop EIGRP configuration over here, and in the next video we'll be doing the OSPF configuration onto these 4 routers so that internal routing configuration of our organization gets completed. So let's head over to next video. Welcome again. So here we are with the same topology, but this time we'll be doing the OSPF configuration on routers R5, R6, R7 and R8 according to this configuration that I had mentioned earlier, that these 3 interfaces will be, or these interfaces which are belonging to this green eclipse will fall into area 0 and these one will fall into area number 1. So let's head over to R5, which is over here, and let's start let's first configure the interface, because I believe I have not configured that, which is interface FA1/0. So I type in the IP address, and this time the configuration or the IP addressing scheme is 30, as I mentioned in my earlier video. So I type in 30.1.1.1 and a subnet mask of 30. Do a no shut. Now let's start the OSPF routing process and enable OSPF on that particular interface. I can give the command network over here, but I can also go into that particular interface and enable OSPF process on that particular network. So let's do that by typing in interface FA1/0 and IP OSPF process number 1 that I had used over here, and then the area that I want this interface to belong to, which is area number 0. Once that is done, let's head over to R6 and do the first interface related configuration. IP address is 30.1.1.2 and 30 subnet mask. Then start the OSPF process and go into that particular interface and enable OSPF process for that particular network. This one is also in area number 0. We should really be seeing these 2 routers become neighbors, and their adjacency or neighbor relationship should come up in a moment. So once that is done, now let's also configure interface related information on R6 that is to be connected with R7, and also enable OSPF process on that particular interface as well. So I come onto the console and type in interface FA. Let me just check this one. Which one is this? FA 0/0. This is 0/0 between R6 and R7. So I type in FA 0/0 and let's just give it IP address of 30.1.1.5 with the 30 subnet do a no shut, and also enable OSPF process on this router by putting it in area number 0. Now once that configuration is done, let's head over to router number 7 and configure its two interfaces in area 0 and area 1 respectively. So first, going into interface FA 0/0, giving it the IP address which was 30.1.1.6. 5 was on R6 side, so this one is 6, and subnet mask of 30. Do a no shut. Also assign the IP address on 0/1 interface which is connected with R8 by giving it IP address of, let's say, 9. Do a no shut over here as well. Start the OSPF process, and now heading back to the interfaces. First one was FA 0/0, IP OSPF 1 area 0. This interface, which is FA 0/0, this is in area 0. While the other interface, which is FA 0/1, this is in area number 1. So I type in area number 1. Also we can see that this adjacency has come up between R7 and R6. So the last router that is need to be configured for our internal routing domain is R8. So let's head over to R8 now and do the respective configuration in there as well. So I type in interface FA 0/1, give it the IP address 30.1.1.10 and 30 subnet mask. Do a no shut. Start the OSPF process. Go into that particular interface one more time and bring this interface into OSPF area number 1. Its adjacency has also come up. Now pretty much all the configuration regarding OSPF has been completed, and if I come on to router number 5, which is, let me just get my pen, which is over here, we should be seeing information about this network and about this network as well in here. And we will be seeing that this information which is on this network, which is network number 30.1.1.8, this network will appear in router number 5 and even in router number 6 routing table related to OSPF as inter area, because it is coming from a different area. Likewise, the information regarding these two networks will be coming into our R8 routing table as inter area. So let's head over to routers and let's see their routing tables to confirm what we have configured so far. So if I type in do show IP route and then the protocol, so I see that this information, this network, which is area number 1 over here between R7 and R8, it is being appeared in router number 5 routing table as inter area and accessible via R6 fast Ethernet interface. Likewise, if I come on to let's say R8 and do a show IP route OSPF, I see that both the networks between R5, R6 and R7, since they belong to area 0, an area which is different to our area, which is area 1 for R8, they are being shown as inter-area, OSPF inter-area routes. Let's also configure one loopback interface on R8 as well, just to emulate another network on which might be connected with R8, and also keep that network in area 1. So let's configure a loopback address on R8 by giving it IP address of 1.1.1.8 and 32 subnet mask, and bring it in OSPF area 1. So if I come on to R5 now, we should be seeing this particular loopback address that we have just configured in the routing table of R5 learned via OSPF protocol. Now that pretty much covers the basic configuration regarding all the 3 routing protocols that we have seen so far, which first one was RAPE over here, then EIGRP, and then OSPF. We have not done any configuration except the configuration of areas and basic EIGRP neighbors relationship and RAPE. Now in the next video, we will see that how we can translate information from one routing protocol into another routing protocol. So let's head over there and see how it can be done. So here we are, where we have configured 3 routing protocols in between our branches presumably and the head office. And you might imagine that pretty much everything is done, but it's not, because you see at the moment what is really happening is that we have 3 routing protocol domains, EIGRP, RAPE and OSPF, and this router number 5, which is in between these 3 colored, as you can see, which I'm representing for 3 different routing protocols, this R5 has got connectivity with all the 3 domains. So this R5 can reach to R8 loopback interface, to R4 loopback interface, and to R2 loopback interface. Now let's try to check that connectivity by bringing up the R5 console, which is over here, and I press enter, then go into the enable mode, and after here that I type in show, let's say IP route, to see the complete routing table of R5. So I see that I have learned information about the loopback address of R4, which is over here, and also I have learned about the loopback information regarding router 8 via OSPF, and also the loopback information about R2 via RIP protocol, and also other loopback addresses on R2 which we had configured to emulate as multiple networks. So if I try to ping, let's try to ping the loopback IP address of R4, we see that we have the connectivity. Likewise, loopback address of router 8 can also be reached via R5, and the loopback address of R2 is also accessible via R5. So R5 is all good. It can reach to all the networks, and all the routers in those particular routing protocol domains can reach to R5. But the problem is that neither R6, not the routers which are connected with, directly connected with the other routing protocol domains, like if I talking about R6, then R6 cannot talk to R1, R2, R3 or R4, because the routing protocol information which has been shared by these routing protocols, EIGRP, RAPE or OSPF, they are only, I would say, they are only visible to R5 for all 3 of them at the same time, but no other router. This R6 is only part of OSPF protocol. It does not have any information regarding routes learned via EIGRP or RAPE. But R5, yes, it does have information about all the 3 routing protocols, but it is not sending the information which it has got in its routing table into other routing protocols domain. So we have a dilemma. Although we have connectivity, we have configured the IP addresses, we have done much work, try to configure these routing protocol domains, but it is useless. These branch offices, they can communicate to this router, but not to other internal resources. So the thing that we are to do is that somehow make the protocol rated information go from one domain into another, and that is where the concept of redistribution comes in. So what we will be doing is that let's just say that let's try to redistribute these RIP related routes into OSPF domain. So this redistribution will be done at R5 because this is the key router which is connected with all the three routing protocols domain at the same time. So I come on to R5 and I go into global configuration mode, and over here I go into OSPF protocol by typing in router OSPF1, and over here I type in redistribute RIP, and also not only redistribute RIP but also along with its subnets. So once I do that, I should be seeing, if I come on to R8, that now router 8 will have information about the RIP rated networks, and they will be shown as external routes in the routing table of R8. So if I come on to R8 and do a show IP route OSPF, I see that now I know about the loopback addresses of R2 and also the networks, which is this one and this one, which are external to OSPF protocol because this belongs to RIP protocol. I can also see those networks via OSPF as type E2. Now quick word about E1 and E2 type routes while we are doing redistribution into OSPF. E2 are the routes that are having the metric information as it is sent by the ASBR. Let me remove this one and bring this window. So E2 routes are the routes which are being seen by these OSPF domain routers, which are having a metric or as it is sent by this R5, or as it is called as ASBR, or Autonomous System Boundary Router in terms of OSPF. So whatever cost this OSPF router over here, this ASBR is seeing to reach to these networks, it sends them over to the internal routers of OSPF, and these routers do not take into account the cost that it takes to reach that particular route. Like let's say if we have a route which is this one over here, then R8 is not taking into account the cost to reach to R7, then to reach to R6, then to reach to R5, and then whatever the cost was advertised by R5 to reach to this particular network. In case of E2, this is not counted. Only the metric information which is sent by R5 is taken as granted to reach to that particular network. But in case of E1 routes, these routers, they add to the cost that is sent by the ASBR, the cost which is to incur to reach the ASBR itself. So in case if it were E1 type of redistribution, if I had done E1 type of redistribution, then this R8, it would add in the cost of these particular links as well to reach to that particular network. Now at the moment this is one-sided distribution. We have just redistributed RIP rated routes into OSPF domain. So OSPF routers can see RIP networks, but RIP networks or RIP routers cannot see OSPF. So it is a one-way redistribution, which is of course no such benefit at this point. So let me just remove this one, and now let's head over to R5 again, and let's also redistribute OSPF learned routes into RIP protocol so that these routers can reach to one another. So heading over to R5, and now going into RIP protocol, and now I type in redistribute OSPF and also the process number that we want to redistribute. We can also define metric if we want to, like what metric value we want these routes while they are being redistributed starting from 0 to 16. Let's just leave it at its default value. And now if I come on to R1 or R2, which is over here, if I come on to R2 and have a look at its routing table and specifically the routes learned by RIP protocol, I see that it has not learned any OSPF route, and the reason is because we have not defined the metric. So now you should know that metric is a mandatory parameter for redistributing routes into RIP protocol. So let's say that I want it to carry a metric of say 3, so that these networks will assume to be at a hop count of 3, or maybe we can even give it a value of 1. So let's just keep it 3, and now let's head over to R2 and have a look at its routing table one more time. And now this time we see that this router has learned about the loopback IP address of router number 8 and also the network addresses that are in between the OSPF domain, which is this one, and this one, 30.110, 30.114 and 30.118, which are over here. So essentially at this time we have the bidirectional redistribution of routing protocols between two routing domains, RIP and OSPF, and their respective routers should be able to reach one another. So if I try to ping the loopback address of router number 8, I should have the connectivity, which we do. Now just like what we have done for RIP and OSPF, we also need to do redistribution between EIGRP routing protocol domain and OSPF so that these routers can also see one another. So heading back to R5 once again and going into, let's say, OSPF protocol process and doing a redistribution for EIGRP whose autonomous system is 1, and also do a redistribution along with its subnets. Before entering this command, let me come on to R8 and if I do a show IP route for OSPF protocol, we see that we are not having any loopback addresses or 20 subnets into the routing table of R8. But once we will do the redistribution of EIGRP, we should have those networks as well. So coming back to router number 8 and repeating the command, now we see that I have the loopback address of router number 4, 1114, and also the 20 subnets which we have learned through OSPF protocol. But again, this is unidirectional redistribution. We need to do a bidirectional. We also need to redistribute OSPF routes into EIGRP protocol. And the way to do that is we need to go into EIGRP routing process and redistribute OSPF protocol whose process number is 1. And now we need to define the metric for EIGRP. The first parameter is the bandwidth. Since this is the lab environment, you can configure it up till the values that most suit you if you want to redistribute. But let's say that I want it a bandwidth of, while it is redistributing, a bandwidth of 1, and then a delay of let's say 1 microsecond, and also the reliability 1, then load value of 1, and then MTU value of 1. Now based on these 5 values, the metric will be calculated and the routes, OSPF routes, will be redistributed into EIGRP protocol. So once we are done with that and heading over to R4, and if I do a show IP route EIGRP, we see that we have got external routes of EIGRP domain, including the loopback address of router number 8 and also the networks which are belonging to OSPF domain. So essentially right now I should be able to ping the loopback IP address of router number 8 through router number 4, which we do. Now so far our head office is talking to our branches, but the branches cannot talk among themselves. Now from security point of view, you might want to implement this scenario, but for your understanding point of view, what we also need to do is that redistribute this EIGRP into RIP and RIP rated routing information into EIGRP, and this will also be done on router number 5, because if I come on to R2 and have a look at its routing table, then we do not have any route to reach to EIGRP network or specifically to reach to the loopback address of router number 4. So heading back to router number 5, and we are in EIGRP routing process. So let's just quickly redistribute RIP, and with a metric of, let's say 1 dot, or I should say 1 1 1 1 1. Now once that is done and coming on to router number 5, we should be having the RIP protocol related networks into our routing table, which we can see that we are learning about 112 and also the 3 loopback addresses of R2 and the 20 network which is running over the RIP protocol domain. Now again this is unidirectional, so let's quickly come on to R5 and jump into RIP routing process and redistribute EIGRP into RIP protocol by giving it a metric of, again, let's say 3. So now heading over to, let's say, R2 and having a look at its routing table. Now we see that we know about the networks which reside in the EIGRP routing domain, which was 1 and 20. And if I come back to R4 again, we know about the 10 networks which belong to RIP protocol. So coming on to R2, I should now be able to ping the loopback IP address of router number 4. So at the moment, what we have achieved is we have got full connectivity between our head office and our remote locations or branch offices, which are running 3 different routing protocols, and they can access resources of one and other, which we have achieved through redistribution. Now you see we have to do a lot of redistribution in this scenario. In the next video, I'll show you some of the route optimization techniques from a practical point of view that you can do to lower the routing table related information in these SPUR network routers. So let's head over to the next video and let's see how we can do that. Welcome back. Now the first thing that I want to show you regarding the route optimization is you see we had configured router R2 with multiple loopback IP addresses with 111, 21, 22, 23 and also 1112, and all this information is being sent up till router number 5, and also this information is being fed to other routing protocol domains. What if we want to restrict, let's say, some of the routes that is being sent to R5? How about that? Let's say I do not want those routes to be, all of those routes to be learned by router number 5 because I want those routes to be contained in this routing domain only. So we can filter those routes using either access lists or prefix lists. So let's see how we can do that. Let's head over to R1. Let's do the filtration on R1, that while it sends the routing updates to R5, it should filter them. So first let's come on to R5 and see the routing table one more time by typing in show IP route and RIP. Now we are seeing all these routes. Now let's say that I want only these two routes, and or maybe 121 and this network. Let's say that I want only this one and none other. So the way to do that is I come on to router number 1 and I define a prefix list by typing in IP prefix list, giving it a name or a number. Let's call it 1, and then the networks that we want to permit. Prefix list work more or less the same way as that of access control list, that whatever you want to permit or you want to allow, you define it, and rest everything is explicitly get denied or implicitly get denied. I correct myself. So I type in permit and the network that I want to allow. So let's say 1.1.1.21/32 should be allowed, and also network let's say 10.1.1. maybe 4/30 should be allowed. Now we have defined just two prefix lists. It does not mean anything if you do not implement them. So head over to RIP process and type in distribute list, the name of the list, and then in which direction we want it to be distributed, and then the interface on which this should filter the routes, whether while sending updates onto this interface or onto this interface. So we want it to filter these updates while they are getting out of fast Ethernet 0/0. So I type in fast Ethernet 0/0. Now if I come on to R5, which earlier had this routing table, now we have implemented the filter. Now let's see what are the results. Let's repeat the command one more time. Okay, so let's see if it is not implementing. Maybe we have done something wrong with the configuration. So in the command we have defined the prefix list, and I believe this is the access list number. This is not the prefix list number. Let's see the syntax one more time by typing in distribute list, and oh yeah, so prefix was the keyword that I missed. So let's negate this command and retype it by typing in prefix keyword before the number. So now we should see the result of this by going on to R5. So again, it is not implemented yet. Let's see if we are doing something, if we are missing something. So let's have a look at the running configuration, and we are distributing prefix list 1 in the outward direction on fast Ethernet 0/0 on R1, and we have defined the prefix list to only permit these two networks. Alright, so now it has taken into effect. It took some time. You see now it is showing that once it has not received any routing table periodic update from router number 1, now router 5 is assuming that probably those networks have gone down, which we are filtering on R1. So we can see over here that it is saying that this is probably down. This is all good because we are sending these routes in the RIP updates. Likewise, this one is also down and this one is down, but this one is all good because we are only advertising these two networks via RIP updates. So let's just give it some time and it will ultimately flush out as it has. So now we are only learning about two networks in router number 5 routing table regarding the RIP routing protocol domain. So that's one way to filter the routes or route optimization, so that router number 5 does not necessarily have to learn about all the networks if it does not need to. Like we need to contain all the routing information up till router number 1 and not send all the routes to router number 5. Maybe there is no need for that. Maybe those are internal network and we do not need those branch networks information to be unnecessarily advertised to router number 5, or maybe as a matter of fact to other routing protocol domains. Now, just like what we have done for RIP protocol domain, we can do distribution list and on R3 and filter certain routing updates to be sent on to router number 5. So it's just a replication of what we have done on RIP. You can do it yourself for EIGRP protocol, so that certain networks which we do not want to be propagated to R5, they should be filtered out. So let's head over to, and let's do one more thing. You see, if you look at this configuration closely, you will see that the networks which are EIGRP and this RIP, they do not have any redundant link to this R5 or maybe to our head office routers. So essentially these are only one links and no other redundant. Maybe if this routing, let me just change the color. If this EIGRP had one more router over here and they were like connected via this, then that would provide the redundancy for EIGRP domain. And likewise, in case of RIP, if we had another router over here connected with R5 and they were like connected in this fashion or maybe in this fashion, then yes, essentially there were two possible paths to enter into the RIP routing protocol domain. But at the moment, this is not the case. So essentially what RIP routers need to send their traffic out of this RIP domain is just one link, which is via this. So why? I mean, this is the key point that I want to tell you, that why do we need to send all the routing protocols or routing domain related information into the RIP protocol when there is only one way out? So let's say if we have got 20 networks for EIGRP or 30 networks for OSPF or maybe other hundreds of thousands of networks for our internet, then these routers, these R1 and R2, they should not really be bothered about learning those networks, because what we can do is that tell R5 to advertise a default route into RIP domain so that these routers should send their traffic out to R5 no matter what is the destination, isn't it? So that their routing table becomes small. Let me just show you the routing table of R1 or maybe R2. So let's head over to R2 and let's see its routing table, which it is learning via RIP protocol. Now essentially it does not need to know about all these networks because it has got only one way out via R1 and R1 has got one way out via R5 to reach any of these networks. So we can send a default route into R1 so that all the information that wants to get out of the RIP domain use that default route. So let's head over to R1 and let's just remove the distribute list which we had configured earlier. So I type in no distribute list prefix 1 and I also need to type in out. Let's quickly have a look at the running configuration. So this list is still here. Why didn't it remove it? I also need to give an interface. Let's have a look at it one more time and okay, now it's removed. but still route number 1 is learning about all the do show IP route about all the other networks. So let's head over to router number 5, where we are actually doing the redistribution and disable that redistribution. I come on to the global configuration mode, then in RIP protocol, and I type in no distribute, or I should say no redistribution OSPF 1, and likewise no redistribution EIGRP 1, and now do a show run with section RIP. So there is no redistribution, and now router number 1 should not be learning about any of other networks except the networks which belong to the RIP protocol domain. Now this router cannot reach to any of the networks. So what we can do is that we can send a default route to this network so that it can send the information out of the RIP domain. And the way to do that is, if I come on to router number 5, and over here I type in default information, and after that I type in the keyword originate so that it distributes a default route into the RIP domain, and I press enter. And now if I come to R1, we should see a default route that has been generated by router number 5, pointing it to the router number 5 fast Ethernet interface, so that now router number 1 and also router number 2 have that information so that they can send the traffic out on the other networks. Now this does not mean that let me just bring this figure over here one more time. Now the thing that we have done so far is not hampering the RIP related information to be sent out onto EIGRP or OSPF. What we have done so far is that the information which belong to OSPF and EIGRP should not be sent into RIP. So the routing tables of these two routers should get smaller in size. So essentially we should have the connectivity between end routers between, let's say, R8 and R2. So if I come on to R2 and if I try to ping the loopback address of router number 8, although we do not have the loopback address information over here, if I do one more time show IP route, but we should be able to ping it using this default route information. So let's try to ping it, ping the loopback address of router number 8, and we see that we have the connectivity. Now let's head over to OSPF domain and let's see what we can do over here. So at the moment, if we have a look at the R8 routing table, we should have routes from area number 0 with a tag of inter area, and also we should be having external routes from RIP and EIGRP. Now again, in this scenario, router 8 or maybe other networks or other routers that might be connected with router 8 belonging to the same area, they only have got one path to reach to out of the OSPF domain, or maybe to reach to area number 0. If they had multiple paths, then that is a different story. But since at the moment R7 and R8, which are belonging to area number 1 and providing the connectivity between area 1 and area 0, have got one connection. So what we can really do is that somehow restrict the routing information to be sent over to R8. Now there are two ways. One, and no, I shouldn't say two ways. In fact, if I talk about specifically regarding OSPF, then there are two types of link state advertisements that we can block or we can control based on the definition of the areas. Now at the moment, this area number 1 is a regular area, so it is learning about all the routes. If I make this a stub area, it will block the LSA type 5 or external LSAs or all the routes which are not belonging to OSPF will be filtered. So RIP routes will be filtered and EIGRP routes will be filtered via R7 router so that they are not sent on to R8. And instead of those routes, a default route will be sent over to R8 so that it can reach to those particular networks. And what I can also do is that restrict this R8 or maybe other routers connected with this router to not learn about any other OSPF related areas, maybe area 0 or maybe area 2, 3 if there had been any more areas. And instead of all those, it should really have just one default route being sent from R7 to reach to those areas. So that will be LSA type 3. LSA type 5 belonging to external networks and LSA type 3 belonging to external areas. We can restrict these type of LSAs by defining the area type on routers belonging to those particular areas. So let's head over to first router number 8 and see its OSPF routing table. So I type in show IP route OSPF and we see that we are learning about the external networks belonging to RIP and EIGRP routing protocol domains. So I head over to the global configuration mode and into the particular OSPF process, because I need to configure this R8 to be belonging to a stub area so that it should not receive external routes. I need to configure R8 and R7, both of these routers, to be belonging to the same area type, which is of stub area type. So I come on to R8 and I type in area 1, which this interface belongs to, and just call it stub. Now likewise, I need to come on to R number 7. Now since area types are different between R7 and R8, R7 assumes that that area 1 is a regular area, but router 8 has been configured with area 1 as type of stub. So we see that adjacency has broken. So I come on to router number 7 and into global configuration mode, then into OSPF protocol, and over here I type in area 1 as stub as well. So now the neighbor relationship should come up again based on the area type as stub. So once that is done and we come on to router number 8 to see its routing table learned via OSPF protocol, and now we see that we are having these inter-area routes and also this default route, because at the moment we are not doing total filtration. We have not made it totally stub in terms of Cisco, but just stub. So it is only filtering the LSA type 5 advertisements to be sent over to router number 8. Router 8 can still reach to router number 2 or router number 4 via that default route that we are seeing in its routing table. Let me just bring it back up, which is over here. So if I type in, let's say, loopback IP address of router number 2, we see that we have that connectivity. Now, what if I want to remove these routes as well? I do not want to learn about these inter-area routes, because essentially, again, these networks which are connected between router 6.7 and router 5.6, they are again reachable via router number 7. So why, if there is only one link, why do I need to learn about those routes? I do not need to. So I can filter them as well by going into router number 7 and typing in area 1 stub and then no summary. Now what this will do is that it will filter the summary routes as well, or it will filter the not only the LSA type 5 but also LSA type 3. So once I do that and come on to router number 8 and have a look at its routing table one more time, we see that now it has only one default route to get out of its area, and we should still have the connectivity to other routers in other routing domains. Like we can access 1112, which is the loopback address of router 2, and router number 4's loopback address as well. Welcome back. So now that we have seen the redistribution and route optimization specifically for RIP and OSPF, we can also do the same for our EIGRP routing protocol. At the moment, if I come on to router number 4 and do a show IP route, or maybe show IP route for EIGRP protocol, I see all these routes. Now essentially, if I again want to optimize it, I do not need to learn about all these networks which we are redistributing into EIGRP. I can filter them and maybe just inject a default route for instead of all these networks. So again, coming on to router number 5 and going in onto its, now there are a couple of ways that we can do this optimization or injection of default route into EIGRP domain. We can define a default route, point it to some interface, maybe null interface, and then use the network command to propagate that into EIGRP domain. Or maybe we can use a summary address command which we specifically issue on the particular interface so that it summarizes the address that we want to advertise through that particular interface into EIGRP domain. So let's see how we can do that. If I come on to router number 5 and let's head over to that particular interface which is connected to R3, which is FA0/1. So I type in FA0/1 and then I type in command IP summary address and then the protocol for which I am going to summarize or send the summary address, autonomous system number, and after that I need to give in the IP address that I want to summarize. In this case, I want to use the default, and then after that I can also define if I need to assign it some administrative distance. So let's just keep it at a default value, press enter over here, and now if I come back onto router number 4 routing table and see that now we have got just a default route as we have summarized it. If I repeat this command, we see that now we have got only default route. So now based on this default route, this R4, or as a matter of fact this R3 as well, if I come on to R3 which is over here, so if I type in show IP route EIGRP, we see that we are learning about the loopback address of router number 4 and just one default route to reach to networks which are outside the EIGRP domain. So coming back to router number 4, and now let's try to ping the router number 8 loopback IP address. We can reach that, and now let's also try to reach the loopback address of router number 2 which is in RIP protocol domain. So essentially what we have achieved is that we have not only done the redistribution, but we have also seen that if there is no requirement to learn about all the networks residing in the other routing protocol domains, then we can essentially optimize the routing tables and the processing on the routers by doing some route optimization and just advertising default routes instead of sending all the routes in all the routing protocol domains. For our branch office connectivity, we can have a scenario where we might have, let me just change the color. We might have another router over here, or maybe another router. Maybe we have got 3 routers, and this R4 is connected to all three of them and they are connected with R5. So in that case, we know that EIGRP does load balance up to 4 equal cost path by default, and we can also make it load balance on unequal cost paths by using variance that I had mentioned earlier. Likewise, if we are talking about RIP protocol and we had some other routers connected with R5 and these were in turn connected to R2, then and we had been injecting routes on all three of these links, or maybe default routes on all three of these links, then we know that RIP protocol by default for Cisco platforms, it does load balance on equal cost paths up till 4 links. It has the capacity to go up to 6, but by default it uses 4 paths. Likewise, for OSPF, we can go up to 16 equal cost paths, but by default we use only 4. So now that we have configured our internal routing domains, different IGP protocols, let's head over and try to configure the internet access or maybe BGP protocol for these particular routers so that our organization can have access to the external routes, maybe internet routes via BGP protocol. So let's go ahead and let's do it. Welcome. So let's head over to R6 and R9 and do BGP related configuration to emulate as if this R6 is connected to the internet provided by router number 9. So let's head over to router number 6. Let me just bring up the terminal, which is over here, and typing in enable, then going into that particular interface, which is interface FA0/1, I believe, which is this one connecting R6 and R9. So I type in the IP address, which is let's say 40.1.1.1 and a subnet mask of 30. Do a no shut, and now let's do the BGP related configuration. So we head over to the BGP routing protocol process stanza, and this is the one which is the autonomous system number for our organization. And now we need to tell the router number 6 that what is its neighbor BGP router. So I type in neighbor, the IP address of that neighbor which we will form relationship with. Let's say it will be 2. We need to configure it at the moment. We have not configured it yet. And the remote AS of our neighbor, let's say, is 2. So that's all which is required. Now let's head over to router number 9. Just let me get the console and bring it over here. And I also, since I believe it's in default state, if I type in do show run, yes, in default state. So let's quickly configure the console line and spell check. Let's also disable domain lookup. And now let's head over to fast Ethernet 0/1 interface, give it the IP address which was 40.1.1.2 and a subnet mask of 30. Bring this interface up and head over to BGP process, this time autonomous system number 2, and over here I type in neighbor which was 40.1.1.1 and its remote AS was 1. So once this configuration is done, we should be seeing that these BGP neighbors will form eBGP peer relationship with one another, and the TCP session will come up so that they can further exchange the NLRI or network layer reachability information or routing information with one another. And it's up, as we can see on route number 9, and likewise on route number 6 as well. The neighbors have come up. To see if the neighbors have come up or what is the neighbor state, I type in do show IP BGP neighbor command, and maybe do show IP BGP summary to give us a shorter view. And I can see that from router number 6 we have the neighbor, which is the IP address, then the version number, the autonomous system number, how many messages were received and sent, and if we have shared any prefixes with them or if we have received any prefixes from our neighbor. Likewise, if I go over to router number 9, which is supposedly the uplink provider, and over here I type in do show IP BGP summary, I see that we have the neighbor relationship with router number 6, and so far we have not received any prefixes. So let's send some prefixes. Now before doing that, let me tell you one thing, that if we have a look at the routing table of router number 6 by typing in do show IP route, this is the router that we will be using to provide connectivity into our organization, that is traffic which is coming out from the organization. Or let me just bring up this window. So this is the router which will say to the router number 9 that, hey Mr. Router number 9, these are the networks that you can have connectivity through me, and those networks will be this 30, this 10, and this 20 over here. And not only that, also the loopback addresses of all these routers. Now router 6, if we have a look at the routing table, router number 6, it will have all the specific routes related to these networks. Now essentially what we can do is that we can advertise all those routes to router number 9, but that is not a recommended practice. We really tend to do what if we are connected with internet routers to advertise the networks with at least 24 subnet masks and not greater than that, so that these core routers, which are internet routers, they should not have their routing tables burst up because of these more specific routing updates. So what we can do in that case is that we can kind of summarize the routes on router number 6 and send those summary routes towards router number 9. Now one way to do that is we can generate static routes in router number 6 against these networks, and then instead of advertising those specific networks like this or these or maybe loopbacks, we will just be sending those static routes which will make less overhead as far as routing table of router number 9 is concerned. So let's head over to router number 6 and let's see how we can do that. So essentially, if we want router number 9 to learn about all the networks, we need to advertise all these networks, which does not make much sense as far as practical scenarios are concerned. So let's head over to global configuration mode, and over here I type in IP route, let's say 1.1.1.0 with a mask of 255.255.255.0, and let's point it to null interface. Likewise, if I do the same for 10 network, for our 20 network, for our 30 network. Now once that is done, I go into the BGP routing process, and over here I type in the network related commands, which is network.1.1.1.0, and I also need to define the mask for it. So the mask is 24. Likewise for 10, for 20, and for 30. Now if I head over to router number 9 and if I again repeat this command, we see that we have received a prefix, and if I type in do show IP route, we see that we have received so far one network, and if I repeat the command, we see that we have received all the networks that we had advertised from router number, or is there one missing? One is there, 10, 20, or alright, all four are there which we had advertised from router number 6. Now the reason that I did that, let me just bring it back. I did a summarization or a default route on router number 6 is that because BGP by default it would not advertise any route which is not in the routing table of that particular router. So if I had done just these statements and not these, I had not defined these routes, because these are, you see, these are not specific routes. These are, I would say, they are kind of summarized routes for these particular networks. If I had not done that and only issued these commands, network commands in the routing table, then this will have no effect, because BGP will first have a look at how it can reach to these networks. If it hasn't got any route to reach to these networks, it will not advertise those networks further out. So we really needed to do this specific routes, or I should not say specific route, rather these entries for routing tables, so that they can help BGP in advertising these routes further out to its neighbors. Now let me just remove this one, and let me also show you. If I type in do show IP BGP, then it shows us the BGP table of router number 6. Now these entries they only pop up once BGP has got valid routes against these networks, which we provided it via these commands. If these had not been in there, these networks would not have appeared in the BGP table of router number 6. Neither they would have been, if they had not been here, of course they would not have been transferred or advertised to router number 9, which are over here. So essentially at the moment we have successfully configured route number 6 to send our internal routes out on the internet, so that these routers or other routers on the internet, they know that hey, how they can send the information back to those, for those particular networks. But on the other hand, these networks, or R6 specifically, they do not know that how they can reach to other networks which are outside them. We have not shared any routing information with R6 as far as R9 or maybe other routers, R10 or other routers, maybe internet routers concerned. So the one thing that we can do, which is usually not the best practice in small to medium scale enterprises, if you have got only one link with one ISP, and that is that we share all the hundreds and thousands of internet routes with our organization router. Because you see, essentially again it's the same case. If we have got only one link out to reach to the internet, then what's the point to advertise all those routes to R6? There is no need for that. We can simply issue a default route from R9 to R6, so that R6 and all the other routers in our router domain know that how they can reach out to the internet using the ISP router. So let's see how we can achieve that functionality, and let's head over to the next video before I do that configuration, because it takes a little bit more time to do it, because we need to make sure that all the routers within our organization can reach to the internet. So let's head over to the next video and see how we can achieve this default route advertisement configuration for BGP routers. Welcome back. So heading over to router number 9 to generate a default route for our organization. We go on to router number 9 and I go to specifically the BGP routing process by typing in, I'm already in there I believe, because it's just BGP routing process that is running on router number 9 at the moment. So over here, if I need to generate the default route towards router number 6, I can type in neighbor, then the IP address of that neighbor, and then default originate, which is the keyword, so that it should generate the default route. Now before I do that, let me come over to router number 6, and if I type in show IP route, which is over here, we see that we are learning about all the internal networks that we are part of and no other networks. So if we have, like, we need to send the traffic out on the internet, maybe other IP addresses 100, 2, 3, 4 or such like that, we have no route to reach those networks until unless we are specifically advertised about those networks via router number 9, or we may have a default route. So coming back on to router number 9, I press enter over here and now come back to router number 6 and do have a look at its routing table. And now we see that we have learned a route which is default route via BGP routing protocol. This BGP indicates that it was learned via BGP. So router 6 is all good. Router 6 can send this traffic out on the internet. But what about other routers in our organization? How about router number 7 or maybe router number 5? Can they send the traffic out on the internet? Let's come on to router number 7 and have a look at its routing table. So if I type in show IP route, we see that it can send the traffic out via 30115, which is over here I believe on route number 6. And if I come on to router number 6 and do a show run, maybe I have already issued that command. Let me just, okay, so this is the reason that I wanted to show you that. Let me just remove this command. Let me just remove this one by typing in and going into the OSPF protocol configuration mode and remove this command. So once that command is removed, now if I come on to router number 7, we should be seeing that we can only reach to those networks which are internal for our organization. Let's come back to router number 6 and do a show IP route. Do a show run one more time. Coming down all the way to OSPF, this default information originate is still there. I removed this one. So let's quickly remove it again. Why didn't it take into effect? So I type in no default information originate and coming back to router number 7, have a look at its routing table. Alright, now it's gone. So what I wanted to show you is that once we had advertised the default route from router number 9 to router number 6, now router number 6 knows about how to reach out on the internet, but not these other routers, not router number 5, not router number 7. You see router number 8, as we had configured for OSPF, router number 8 was put into totally stubby area, so that if it doesn't have any route to reach to networks which are outside of this area, it should simply pass on the traffic onto router number 7. Likewise for router number 2 or router number 1 which were residing in RIP, they can simply pass the traffic onto router number 5, as this is the default path to get out of the RIP domain. Similarly, for router number 4 and router number 3, to get out of the EIGRP, we had used a default route which we originated on the interface so that these networks can send the traffic out of their EIGRP domain. But now coming over to router number 6, this router number 6 knows about the default route, but not router number 5, neither router number 7. So we need to make them learn about the default route. Now one way could be that we can redistribute BGP into an IGP, which is really not a recommended way, because right now we are only having one route. If we had having all the network table which is beyond 600,000 routes, we do not want our internal routers to have all that routing information. So what we can really do is that I can generate a default route on router number 6 for OSPF protocol and advertise it onto router number 5 and router number 7, so that these routers also know that how they can reach out of their OSPF domain or how they can reach out of our internal organization network. So let's head over to router number 6, and the command is the same that I had just removed, which is default information originate, and we can append the keyword always, which means that even if this router does not have a default route, it should always be originating or advertising this default information to its neighbor via OSPF LSAs. So once I do that and I come on to router number 7 and have a look at its routing table, we see that we have a default route in router number 7, and also if I come on to router number 5 and do a show IP route, we see that we have a default route. But now here's a catch. Look at this. This information is saying that this default route is pointing towards null 0. So essentially what it means is that if I come on to router number 7 and try to ping these interfaces, let's say try to ping 40.1.1.2, which is connected with router number 9. So if I try to ping from router number 7 40.1.1.2, we should have the connectivity. But if I come on to router number 5, although we advertised the default route via R6, but R5 will not be able to reach 40.1.1.2, and let me just show you that. If I try to ping 40.1.1.2, we see that we cannot reach it. Why? Because default route is there, but this default route is pointed at null 0 interface. And why is that? This default route was originated when we issued that summary network command for our EIGRP domain. Let me just show you the configuration stanza. If I type in show run and come on to that very specific interface, which is FA0/1, this is the interface which is connected with router number 3 and over here. And this is the command that we had used. IP summary address EIGRP1, this is the autonomous system number for EIGRP process, and then this is the default route that we had originated to be sent into the EIGRP domain. Now based on this command, and you see that we have not configured any static route. Based on this command, this router automatically generates that static route and points it to null interface. So since it has got, this was statically configured, let me show you one more time. Show IP route. Since this was statically configured, so it has got higher preference as compared to the route which is being learned from OSPF protocol. So in this case, what we really need to do is offset this configuration regarding this default route origination for EIGRP domain and do a little tweak so that we can have the connectivity that we want to achieve. So let's quickly head over to the configuration stanza of EIGRP, and if I bring it up a little bit, we can see that we are distributing RIP and OSPF. So OSPF will be there, but we need to remove this RIP configuration. So I come on to the EIGRP configuration hierarchy and I type in no redistribute RIP, and after that I can also do a no redistribute OSPF, but we really need to do it afterwards. So let's just remove this one as well. Now no redistribution is being done. So essentially this EIGRP domain, it neither can access internal networks nor external networks. If I come on to router number 4 and have a look at its routing table by typing in show IP route for specifically for EIGRP, we see that we have got just one default route. And if I come on to router number 3 and quickly have a look at its routing table as well for EIGRP protocol, it has also got one default route. Now coming back to router number 5 and do a show IP route EIGRP. This is the summary address which is pointing to the null zero interface, so we need to remove this one. If I show you the running configuration, this is the command which is generating this default route, but because of this default route, this router number 5, it itself will not be able to forward traffic out on the internet. So I come into that particular interface which is FA0/1 and I type in no and then this particular command. So once that is done and coming back to router number 4, we should be seeing that this default route will no longer be there. So now let's head over to router number 5 quickly, and what we really need to do is that we would be needing to redistribute the OSPF protocol into EIGRP, but only the default route we need to advertise into EIGRP. So the way to do that is that I can define a prefix list, let's call it 1, and in that just permit default route. Now once that is done, I can define a route map. Let's call it default and permit 10, and in that I just need to match IP address and prefix list 1. Now once that is done, I can recall this route map in the redistribution which we will be doing in the EIGRP process, so that based on this route map, this prefix list will be called in and only this entry will be matched to send the routes out on the in the EIGRP domain. So I type in router EIGRP1 and after that I type in redistribute OSPF1 and metric 1111. Now you see if I press enter over here without any route map, then all the OSPF learned routes will be redistributed into EIGRP domain, which we do not want. I just want a specific route which is the default. So I type in route map and then the route map name that we had defined, which was default. So I press enter over here, and just before that, let me show you, if I come on to router number 4 and its routing table. We do not have any default route entry. So now I press enter, and essentially we should be seeing a default route entry in router number 4, which we do. And also, if I show you the routing table of router number 5 by typing in show IP route, we see that we have connectivity to our default OSPF route, which was advertised by router number 6. So all the routers essentially at this time have got connectivity to the internet with optimized routing that we have configured. Now, if I try to ping from router number 5 to the interface of router number 9 Ethernet or fast Ethernet over here, we should be able to reach it, which we do. And likewise from router number 4, which is the end router in EIGRP domain, we should be able to access the fast Ethernet interface of router 9. Likewise, coming on to router number 2, if I type in ping and 40.1.1.2, we have connectivity. And similarly, from OSPF domain's last router, which is in totally stub area, I type in ping 40.1.1.2, and we see that I can reach it. So to summarize it up, what we have configured in these videos is that we have taken a practical scenario where we had assumed that this is our head office. It is connected to the internet via router number 6, and it is also connected with its branch offices which are running EIGRP and RIP protocol. And we have covered redistribution and route optimization and also connectivity to the internet. Now I will end these videos, these particular scenario videos over here, and I hope you have learned from these videos. Do practice with these scenarios, because that's how things are implemented in real life examples. I hope you have learned from this video, and thank you for watching.
Greetings everyone. In this video we are going to see how we achieve redundancy on our LAN segment. This is a typical topology that I have made up in GNS3, and we are going to use Cisco routers in this. This is a server, this is a Linux machine, and it's a plain layer 2 switch. This could be layer 3 with multiple VLANs, and this could be multiple switches, but for the demonstration of this video it does not really matter. What we are interested in is the gateway for this LAN segment, which is represented by this server machine, which has got 2 NICs in it. So the problem is that on the router side, on layer 3 devices, you have got routing protocols. You have different routing protocols, including RIP or ISIS or OSPF. They provide the required connectivity within the network. So even if one of the side goes down, you can have redundancy from the other side because you are running the router protocols. But in case of LAN segment, that is not possible. These machines, workstations or servers or your desktops, they do not have as such router protocol unless you use some third-party software. So they need to get out of the your enterprise network or any of your campus network and reach to the internet. But for that, they need to have a gateway, like in this case. So the problem is that if there is one gateway and that gateway fails, or it kind of induces some problem, or the connectivity breaks down, then whole of your network goes down, this complete network. So what we can do is that we can introduce multiple gateways. But the problem is that once you have multiple gateways, how can you assign multiple gateway IP addresses to the server? It's simply not possible. So here comes the concept of first hop redundancy protocol. First hop redundancy protocol. In fact, this is not a protocol at all. This is just an acronym, but it does represent certain protocols. First one is, I would say, HSRP, Hot Standby Routing Protocol. This is Cisco proprietary protocol. Another one is VRRP. This is a Virtual Router Redundancy Protocol. This is IETF standard based. And another one that Cisco uses is GLBP, which is Gateway Load Balancing Protocol. In this video, we are going to see VRRP, that how to implement it, because it's standard based. And a brief working of this protocol is that once you run these protocols onto your prospective gateways, specifically these interfaces which are pointed to the LAN segment, they provide you a virtual IP address. So for this server, there will be one IP address, but that IP address will be mapped on both R1 and R2. And not only that IP address will be mapped, against this IP address, there will be a MAC address as well. So that once this server or these machines, they want to start communication and they do the ARP to get the MAC address against the IP address, against the gateway IP address, they would get a MAC address, and that MAC address is also available on both of these routers. So what happens is that, let's say this is the primary one. In our configuration, we are gonna make R1 to act as the master server, as the master gateway, and this one R2 as the backup gateway. So what happens is that, let's say if master interface goes down, or master router, complete router gateway goes down, then router number 2 or the backup router, it will take the role of the master and will start forwarding the traffic. Otherwise, it will just stay in the backup state and will not forward any traffic. How they communicate? They send the protocol related, like in this case, VRP related packets to each other using multicast address, and once backup stops receiving the multicast packets from router 1, it will assume that there is some connectivity issue and it will assume the role of the master. We are also going to see that how we can leverage IP SLA feature to provide support in making this operation, making this more beneficial for our environment. Because what happens is that we'll see in the coming minutes that there are scenarios that if we have cable cut in the other segment, like this side, not on this side but this side, then these routing protocols, they will of course help, but not in the optimum way that we want. So let's just remove this one. Let's fire up these routers and the server machine, and let's just configure this. Okay, so machines are now in the on state, and let me just quickly tell you about the IP addresses. The server has got 2 NICs, and the IP addresses are like 10.1.1.10 and 10.11.11 with a subnet mask of 24. For router number 1, Ethernet's 0 IP address is 10.11.21, and R2's Ethernet 0 IP address is 10.1.1.22. And we are going to assign the virtual gateway IP address as 10.1.1.1. For this segment, R1 to internet, the IP address is 20.1.1.0 with a subnet mask of 30, with 1 being on this side and 2 on being the internet router side. And on this segment is 20.1.1.4/30 with 5 on router number 2 and 6 on the internet router side. So let's just quickly configure OSPF in this domain so that at least our routing elements have the full connectivity, and then we'll see how to configure VRRP. So let's do it. Let me just remove this writing first. There we go. And also, before we do the actual configuration, let me just show you the IP addresses which are configured onto the server. So I do if config, and these are the IP addresses: 10.1.11, and the other one is 10.1.1.10, which I told you that we have got 2 interfaces. And if we have a look at the routing table, we have got 2 default routes via the same gateway, which is 10.1.1, which is not yet configured. We have to configure it. So first, let's quickly come on to router number 1, and first just let's configure routing protocol. So I'm going to configure a router OSPF process 1, and just configure routing protocol for all the interfaces, including loopback interface. Let me just also quickly tell you here that I've also configured loopback interfaces on all these 3 routers. For router number 1, the loopback interface is 1.1.1.1. For 2, it's 1.1.1.2. and for internet router it's 1.1.1.3. So we are considering that from server number 1 we should have connectivity to this loopback address, even though there is network breakage on the LAN segment. So let me just bring back the configuration window and put in the wildcard bits for all the interfaces and put this in area 0. Come on to router number 2, do the same configuration here as well. Network available on all interfaces and put it in area 0. And similarly for our, what we consider that is the internet router. So router SPF1 network 0.0.050 and the wildcard bits and area 0. Of course, in real world, this router, internet and your enterprise router, they might not be running OSPF, they might be running BGP, but since this lab environment, it does not matter much. What we are just having is that a complete routing connectivity within this domain. So let's see if we have got full OSPF relationship between all the 3 routers. We see that 1.1 is up. So this has got full neighbor relationship with both the routers. So we'll have this is connected with 1, but again we are waiting for it to have full relationship with the internet router. Okay, so there we go. Now we have it, and on internet router as well we can see that we have got both the neighbors, that is router number 1 and router number 2. Now the next thing that we are going to configure is come on to router number 1 and we do the VRRP related configuration, and we'll do the VRRP configuration on that interface which is facing towards the LAN side, which is this interface for router number 1 as well and for router number 2 as well. So come on to interface Ethernet 0/0, and the command to configure VRRP is VRRP and then the group number, it ranges from 1 to 255. So I'm going to use the group number 1, and then the IP address, which is the virtual IP address for that group, or we can say that what will be the gateway for our LAN segment, which we talked about that we are going to use 1. And we see that immediately it has started to work and change its state from init to backup and then backup to master, because at the moment this is the only router. Also, we can configure the priority for VRRP group, but if we leave it by default, then by default it will take it as the 100. And we can check it. We can do the show command, show VRRP and summary or brief. And this is the priority that I'm talking about. By default it's 100. So I'm going to go to router number 2 and we are going to reduce its priority to 90 so that router number 1 stays as the master router. Come on to router number 2, go into interface Ethernet 0/0 and then VRRP1 and priority as, maybe it will not let me configure it because I have not configured the IP. Okay, it has let me do it. So VRRP priority, first we have configured the priority so that it immediately takes the role of the backup instead of first checking and then flipping over. And the IP address is the same as we configured on the master router, because we will have the same IP address but group IP address, so that once master goes down the backup takes on that IP address and start working. So once we do that, we'll see that it immediately went into the init state and then to backup state. And if we show the status of VRRP, we show VRRP brief, we see that its role is the backup role and the master is 10.1.1.21, which is the R1 router. Okay, so once that part is done, now let's come on to router number, come on to server, and let's try to ping the internet IP address, which we said that is the loopback address of router number 3. So let's try to ping its loopback address, which is 1113. We can ping it, and let's do a trace. Trace path is the same as trace route, but on this I have not installed trace route. Trace path it gives you more options, so we are going to use that. -n is just for do not resolve the IP address to the name, and 1.1.1.3, and we see that it is going to router number 1. This is the IP address of router number 1, and then to the internet router Ethernet interface. Now what we're going to do is that I'm going to shut down the interface. Let's just do a ping, continuous ping. I'm going to shut down the router 1 Ethernet interface and then see what happens. Ideally, we would see two changes. Once that, of course, we'll not be seeing that change over here because we will shut down the physical interface. But if there's a cable cut, we'll see that router number 2 will assume the role of the master. Right now it's backup, but since it will stop receiving the packets from router number 1, it will assume the role of the master and will start forwarding the traffic, and we'll see very minimal droppage in the ping packets. So let's come on to router number 1. Its interface Ethernet 0/0, which we are already in, and just shut down this interface. So this goes down, and we see that immediately it has gone from backup to master, and the ping drop is probably here somewhere between 45 and 48. So 3 packets got lost. Now come on to the figure. What happening right now is that earlier traffic was going from server 1 to router number 1 and to internet. Since we shut it down, the IP address now being served, the gateway IP address now being served by router number 2, and the traffic is going via this path. Now what I wanted to show you is the leverage of IPSLA facility. That what will happen if we shut down this interface. Let's just first see what happens. Let me just remove this one, and let's get back to the configuration portion. Bring back our interface on router number 1. We see that it has gone back to backup state, and it will automatically come back to master state because VRRP by default has the preemption function available. It means that if the priority of router number 1 or any router is higher than the other routers, then it will automatically become the master, which in this case router 1 has. So what I'm going to do is that I'm going to come to the Ethernet 0/1 interface, which is facing towards the internet router, and then shut it down, and then see what happens. We'll see that OSPF relationship will break between the two routers, but since it will not impact the VRRP group, we'll still see that traffic will try to go to router number 1 first and then to the other router. So let's see what we have here. Ping is going on, ping is alright, but let's do a trace path to router 113. Check one more time. Okay, ideally what happens is that what I wanted to show you is that since we changed our interface status onto this side, ideally what will happen is that in many cases that this stays up because we have not changed the status onto this side, and router 1 will still have the priority or the master role for the network segment. And what happens is that traffic, instead of going to this side, because it will not go because router 1 is still the master, traffic goes to master. And since we are running routing protocols, because of that, master has got the idea that now 1113 is not via, let me just draw this, that 1113 is not available via this route, but because of OSPF, it is available via router number 2, and the traffic is passed on to router number 2 and then to the internet. So we'll see that traffic first goes to router number 1, and then it goes back from router number 1 to router number 2, and then to the internet router, which is suboptimal routing. But here we are seeing that VRRP has already detected that there is a fault in the network, and it is already that the behavior of the protocol has already made router number 2 as the active router, and traffic is no more going to router number 1. In case of HSRP, if you configure, which is Cisco proprietary protocol, you would see that traffic would first go to router number 1, and then it will go to router number 2, and then to the internet router. But in any case, what you can do if you observe this kind of behavior, you can configure IPSLA feature which I talked about, so that the changes get detected onto the routers. First, just bring up this interface, Ethernet 0.1, and do a no shut. Let's just wait for a second. Okay, this one. And what we can do is that let's try to shut down on the internet side interface, and let's see how does VRP behave then. Okay, interface Ethernet 0.1 and shut it down. Okay, this is down, and do show VRP brief. This is still master, and if we come on to server 1 and do a trace, you see this is what I wanted to show you. That traffic is first going to router number 1, and then since router number 1 has no connectivity to the internet router, it is going to router number 2, which is 22, and then to the internet router. And if you do trace again, you will see that now it has detected that there is some change, and it has kind of taken the optimal path. But if that is not available, if let's say you have to configure HSRP, or it is taking some time, then to leverage the feature of IPSLA so that it switches over quickly, we'll see how to configure that. Let me just bring back this interface again, and now come on to router number 1. Into global configuration mode, we are going to type in IPSLA 1, and the method that I'm going to use is ICMP echo. The other end IP address is 20.1.1.2, and the source address that I want to use is the interface Ethernet 0.1, so the traffic gets out from Ethernet 0.1 interface. And I'm going to use the threshold value of let's say 1000. This is just a value which kind of once this threshold value is reached, whatever this value is in milliseconds. So once response is not received within 1000 millisecond or 1 second, then we can do certain monitoring parameters with that. But the important thing is this timeout. This is also in millisecond, and I'm gonna put the value as 1 second. Then the frequency, that how frequent this operation should run, how frequent should it send the ICMP echo packets. This value is in seconds, so I'm just gonna put in 1. And once that part is done, the other command, we have just configured the IPSLA, but it's not running at the moment. It's not doing anything unless we make it run. So to make it run, the command is IPSLA schedule it. This is number 1. This is the same number as we used to define the IPSLA. And then its life, for how long it should continue to run, I would say that run forever. And start right now. Now once that started, now IPSLA is running. And we'll see the status as well, that everything should be okay. If we do, let's say, do show IPSLA statistics, and we see that the latest operation return code is okay. If there is a failure, we'll see that this status changed to failed. Now the last thing that we need to do to bind this IPSLA is with the tracking function, which is track, and this one is a unique value. It does not have to do anything with the IPSLA version that we configured here. IPSLA 1 number, this is different one. So I track 1 IPSLA, and here we give the value that we defined for IPSLA, which was 1. Now once that is done, we go into the interface Ethernet 0.0, where we defined our VRRP protocol, and over there we define VRRP 1 and track. Now this track number is the same as we defined over here, this track number, track 1, so that now VRRP protocol will be tracking the IPSLA that we defined, that if there is a breakage, if it does not get the response, then it should decrement its priority by a number of 20. So once we configure that, let's just have a quick look at our configuration. Do show run. This is the tracking function. This is the VRRP rated configuration, and this is the IPSLA. So everything looks fine. Now let's come on to the internet router one more time, and before that let's do a trace. So it is still going from router number 2. So let's see the status of our VRRP. Do show VRRP brief. Sprite is 10. And do show VRP brief. This is 90. So it is saying that master IP address is 10.11.21 and this is the master IP address, which is 10.1.21, which is its own IP address. So it has assumed the role of the master and it has assumed the role of the backup. So now let's see if we come on to internet router and its interface Ethernet 01, which is pointing towards the router number 1, and do a check there. And let's see the status here. See, the tracking state has gone from up to down, and immediately we see that the VRP protocol, it has changed state from master to backup. So it is no longer serving as the master, rather router number 2 is now serving the traffic. And we'll see that on router number 2, the state has changed from backup to master. So what happening right now is that we brought down this interface and the VRP group IP address changed from router number 1 to router number 2. And once the link gets restored, come on to here, we should ideally be seeing that route number 1 should assume the responsibility of the pirate router. So do a no shut here. And once the interface comes back up, we'll see here the respective changes. Track interface changed state to up, and the state of the VRP protocol also changed from backup to master. So everything is perfectly fine, and primarily that's how we use VRP or first hop redundancy protocols, whether it is GLVP or HSRP in our enterprises, and that is also how we bind IPSLA feature to our first hop redundancy protocols. I hope this video was informative. Thank you for watching.
Hello guys. Now this is another topology that I want to share with you, and the idea here is to show you that if we have got an organization or even if there are multiple ISPs, then how typically routing is done between ISPs and how to control the routes. So basically its focus is to connect different ISPs together and to route packets between one another. In this example, I have put two organizations, assuming that these are dual homed with two ISPs. One is this one and the other is this one. And we'll also try that the routes of these ISPs should not traverse these organization routers, because you see, if the traffic for router number 3 networks, if we have got multiple networks connected with router number 3 and likewise with router number 4, there are multiple routers and there are multiple organizations, and the traffic uses our router to traverse the links to reach to R3 and vice versa, then definitely our bandwidth is going to get used, and the resources, that is CPU, cycles and memory on R2 will get used. Now we do not want that in case of organizations or end user customers. Users do not want their devices or routing platforms to be used for this kind of routing. So we will see that how we can restrict these kind of routing updates to traverse our router to make it as a transit router. We do not want that. If this had been an ISP, then it would have been fine. But since this is an end organization, likewise over here, we do not want that to happen. So now let's go ahead and see that in typically while we are doing configurations with ISPs in multi-homed environment, how we accomplish these features. So I'm going to just start the routers. This is I'm using in GNS3. All the routers at the moment are Cisco 3700 series, and I'm going to do the basic configuration with just the IPs and nothing else. I'm going to use the network of 10.1.1.0 onto this link with IP address of 1 over here, 2 over here. Likewise 1.4 10.11.14 with IP address of 5 with 6, and let's say use 20.1.1.0 with 1 over here, 2 over here, and 30.1.1.0 with 1 and 2, and likewise with 40.1.1.0 with 1 and 2, and we can do a network of 50 on two route between router 5 and route number 6 with IP address of 1 towards route number 5 and 2 towards route number 6. So let's go ahead and do the configuration as far as IP addressing is concerned. I'm going to pause the video over here and I'll get back to you once I do the interface level configuration for all these routers. Alright, so I've done the basic configuration of regarding IP addresses, and now I'm going to do BGP configuration between route number 1 and router number 2. Let's call it iBGP or internal BGP, and I'm doing configuration of eBGP between R2 R3. Likewise, let me just write it. Likewise eBGP between router number 2 and router number 4, assuming that these are two different ISPs, and likewise eBGP session between R3 R5 and an eBGP session or external BGP session between R4 and R5, and between R5 and R6 we will be doing configuration for internal BGP. So it will look like this scenario where we have got two organizations which are dual homed with two different ISPs, and we will try to control the traffic as it traverses through our routers, or also what kind of information we would like to be shared with the ISPs. So let's quickly come on to router number 1, which is over here, and let me show you the current configuration that is running at the moment. So if I bring it down all the way, you can see that I have configured the IP addresses. I have also configured one loopback address for router number 1. The IP address is all 1 with a subnet mask of 32, of course. And for the fast ether interface which is connected with route number 2, this is the IP address that I have configured. Besides that, there is nothing much that I have configured. So now let's quickly come to the BGP part, and I'm going to use the autonomous system number 2, which corresponds to router number 2. Likewise, autonomous system for this ISPs will be 3, for 4 it will be 4, and for this portion of organization, which is organization number 2, or maybe it could be another office of this organization, I'm using autonomous system number 5. So let's come on to our 1 and execute the command router BGP2. Then I configure for the corresponding neighbor, which is 21.1, and the remote AS is 2 as well, so that it will become an iBGP session. Now let's configure the networks that I want to advertise. First is the loopback address that I want to advertise, and the next one is the connected network with a subnet mask of 30. Pardon me. Now once that is done, let me show you the BGP table for this particular router. So since these two networks are available, these will be advertised once it's formed the BGP neighbor relationship with the other router, which is R2. So now let's come on to R2 and do the corresponding configuration. Let me just show you that at the time being there is nothing much except the IP addresses that I've configured on the interfaces. So I type in router BGP and autonomous system number is 2. Since R1 and R2 in the same autonomous system, I want to establish an iBGP session between them. And let's type in neighbor. The IP address is 21.1.2 for router number 1 that you can see over here. So a remote AS is also 2. And now put in the networks, which is 20.1.1.0 with a mask of 255 and at the end 252, or a subnet mask of 30. Likewise, since I'll be establishing eBGP relationship with router number 3 and router number 4, so let's do that part of the configuration as well by typing in neighbor 10.1.1.2. Since I'm going to use the network of, let me just write it over here, 10.1.1.0 over here and 10.1.1.4 onto this segment. So let's do that part of the configuration as well. And remote AS. This is the IP address that I have configured for router number 3 fast Ethernet interface, which is over here FA0/0. So remote AS is 3, and likewise remote AS is 4 for router number 4, whose IP address I'll be configuring as 10.1.1.6, or which I have already configured. The IP addresses are already there. I had told you about them. So once that part is done, also advertise the networks, which is 10.1.0 with a mask of 30 and also 10.1.4 with a mask of 30. Now let's have a look at the BGP table of router number 2. So you see that 1, which is the loopback address, it has been learned via iBGP. This I over here, this indicates that the route was learned via IGP, or in this case iBGP. On the other hand, this I indicates the origin of the route, which in this case we originated it using the network command on router number 1. Similarly, if you come down here and have a look at this network, which is not only being learned through router number 1, but also we have locally originated it since it was configured on the interface. So this one is the best one because it is locally connected. Now whatever routing information is available here in the BGP routing table of this particular router or any other particular router, as a matter of fact, it will be propagated or it will be advertised to the other BGP neighbors that it establishes its relationship with. So we will see that once we configure router number 3, which is over here, and router number 4, then these both routers will learn about all the network information which is in router number 2. So let's quickly come on to router number 3, and let me just show you the current configuration, which is nothing besides the IP addresses. This one is connected with router number 2 and this one is connected with router number 5, and besides that I have not configured anything. So let's quickly go to the BGP portion. Since this is router number 3, I am assuming that it is carrying an autonomous system number 3. Let's quickly configure the neighbors. First neighbor is 10.1.1.1 with remote AS of 2, and second neighbor is remote AS 5 since I am configuring router number 3. So this is the first neighbor and this is the second neighbor. And I need to remove this command and execute it one more time. The IP address for this one is 30.1.1.2 remote AS of 5. And also quickly configure the networks with a mask of 30, and likewise for 30 network as well. Now let's have a look at the BGP routing table. So it has learned about the 10 network because it is the origin of that network. It is these networks directly connected, and if we give it a bit of time, we will see that since it has already established the neighbor relationship, show IP BGP summary, this is the neighbor 30112 and the other neighbor is not up. So let me just clear the BGP session, or let's just have a look at the configuration if I have made any mistake or not. Do show run and section BGP. So neighbor, alright, so I need to establish the neighbor relationship with the other router. So let's do that, which is this one. (10.1.1.1) and remote AS of 2. So now we should see that it establishes a neighbor relationship with router number 2 as well. And if I come on to router number 5, maybe let me just fix this duplex mismatch problem on fast Ethernet 1/0. So I type in interface fast Ethernet 1/0, make it duplex full and its speed as 100. Also do a no router BGP 5, which I believe should already be there because I had removed that configuration. Let me just double check if there is any BGP related information in there. Apparently there is not. So the neighbor is up over here. You can see, let's see the BGP summary. So this one is down now because the state has gone to active, and this one is established and it has shared the prefixes, 4 prefixes it has received. So now let's see the BGP table of router number 3. Now we see that it has learned about the loopback address of router number 1. So this one is router number 3, and over here we have router number 1. So router number 1 loopback address has been learned by the router number 3, and also it has learned about this 20 network which is internal to organization number 1, which is over here. Likewise, if I come on to route number 4 and do the corresponding configuration for BGP by typing in router BGP 4 is autonomous system number, and the neighbor is 10.1.1.5, which is router number 2 IP address, and the remote AS is 2. Likewise, remote AS is 5, and the IP address is 40. So one neighbor relationship 10.1.1 is over to this side with router number 2, and for 40.1.1.2 is with router number 5. That's all the configuration that I've configured over here. Now let's also advertise the networks that this router is connected with. One is 10.1.1.4 with a mask of 30, and the other is 40.1.1.0. Now let's have a look at its IP table for BGP specific, or BGP routing table I should say, not the routing table, because routing table and BGP tables are different things. A router might learn different routes through different BGP neighbors, but will only install the best routes available in the routing table of the router. So if I type in show IP BGP, I see that we have learned about the loopback address of router number 1, and also the segments that are connected between router number 2 and router number 3, and this one is the segment which is connected with router number 1 and router number 2, which was internal to the organization. So all the connectivity and reachability of the topology so far is available. Like if I try to ping the loopback address of router number 1, we see that we have the connectivity. So what's really happening is that all the information with valid routes, it is being passed between the routers whether via IBGP or whether via eBGP. So now let's come to router number 5, and it has also duplex mismatch problem. So let's fix it. This is the other interface, I believe. So I type in interface fast Ethernet 1/0 and make it duplex as full and speed as 100. This is the link which is connected with router number 6 fast Ethernet 0/0 interface. So this should be fixed now, and maybe I need to configure this one as well. Router number 6, its interface which is fast Ethernet 0/0 by typing in duplex full and speed 100. So once that part is done, it should take care of this problem. Now let's have a look at the interface level configuration for router number 5. So all the interfaces have been configured and no BGP rated configuration is there. So let's quickly do that by typing in the neighbors. One is 30.1.1 with remote AS of 3. This is router number 3 that it's connected with, and the other is router number 4 with an IP address of 40.1.1.1. The last neighbor is an IBGP peer with an IP address of 50.1.1.2 and remote AS of 5 because it is an IBGP. Now once that part is done, let's quickly advertise the networks. First one is 30.1.1.0 with a subnet mask of 30. The second one is 40, and the last one is 50. Now let's have a look at its BGP table. So we see that it has learnt about the loopback address through two different sources. One is the 40 and the other is 30. Likewise, this network is also being learned through 40 and 30, but the best route is via 30 with this one because the segment over here, which is this one, is nearer to R3, so it will always prefer this one and not this one as per the BGP selection rule of shortest AS path. If I come on to router number 5, so we see that the autonomous system path or AS path via 30.1.1 for network 10.1.0 is 3, but in case of via router number 4 it is 4 then 2. So it has to traverse 2 autonomous systems to reach to this network via router number 4. So since this one is shorter, it will always prefer this path till the time this path is valid. Likewise, other networks have been learnt as well. So let's come on to router number 6 and do the last portion of the configuration, which is to configure, let me just see if I've configured the interface level configuration for this router. So it is there. Let's quickly configure the BGP by typing in the neighbor, which is 50.1.1.1 and remote AS as 5, and also the network configuration, which is 50.1.1.0 and a mask of 30. So we should see that IBGP session will become up and the neighbor relationship established between router number 5 and router number 6, and likewise all the BGP table and routes learned via BGP of router number 5 will be shared with router number 6. So if I type in do show IP route, we see that we have learned about these routes through BGP protocol. Alright, so we have configured the very basic BGP configuration between organization number 1 and organization number 2, and we have seen that all the routers have learned and are aware about the network data connected with the routers interfaces. Like we have seen that router number 6 now knows about the loopback address of router number 1, and likewise all the routers knows about all the networks that they are connected with. So the first change that I'm going to make over here is that, let's say, let me just grab the pen. Let's say this loopback IP address 1.1.1.1. Let's say we do not want, let's say this is the internal network, and we do not want this network to be visible to outside organization number 1. Now, in case of BGP, we can accomplish this in many ways, but let's try to do that through the use of community. And I'm going to use the well-known community, which is no export, which would make this route while it is advertised to router number 2, and let the router number 2 know that do not advertise this network to any of your external neighbors. If it had internal neighbors, it would export them to those internal neighbors, but if it has got only external neighbors, which are these one at the moment, it will not export them to these neighbors while using no export community. I can use no advertise community as well. If I want to, then this would mean that do not advertise even to its internal IBGP neighbors if it had any. So now let's do that. Now let's come on to router number 1 and do the corresponding configuration. We are going to accomplish that using route maps, and before route map I need to make an prefix list by typing in IP prefix list, give it a number, and then the permit whatever network should match with this prefix list. So this is the loopback address that I want to match with. Now let's make a route map with the name of let's say no export, and then permit, match it with the prefix list by typing in match IP prefix or match IP address, then prefix list number. And once the packet or the route gets matched, I need to set the community value to no export, that do not export to next autonomous system. It's a well-known community and it is acknowledged by all the routers that adhere to BGP protocol. So if I type in no export, and before I do that, let me also show you, if I come on to router number 2 and I type in show IP BGP for that particular network. At the moment you see that we are not seeing any community related information in the BGP routing table of router number 2. But once we are finished with the filtering configuration of router number 1, we will see that this one network, which is over here, it will carry a community string as well with no export value. So once route map is completed, we come on to the BGP portion of the configuration, and I type in neighbor, which is 20.1.1.1, and I also need to tell that you need to send the community to that neighbor. This is the important and explicit command that you need to execute to share the communities. Also apply the route map, which was no export in the outbound direction. Now once we do that, we will see that 111 network will be filtered, and also the 20.1.1.0 network will be filtered because I have not added any other route map permit statement. So let's quickly do that, and afterward we will add another route map statement so that other networks can be advertised. So if I press enter and let's have a look at this. Let's do a soft reset for BGP between these two routers by typing in clear IP BGP and the IP address of the neighbor and in the inbound direction, so that router number 2 asks the router number 1 about this BGP state or BGP table. Now once we do that and we see the BGP routing table for network 111, now we see that there is a community of no export. Now once this router number 2 receives this router number 2 knows about the network 111, but now it will not advertise it further to any other router. If I come on to router number 3 and do a show IP BGP, we see that network number 1 has gone. Likewise, on none of the routers, whether it is router number 4, 5 or 6, it will not be advertised to any of the other routers because router number 2 is blocking them based on that no export community, that it should not export them to its external peers. So if I type in show IP BGP or show IP route, it does not make much difference. We see that now there is no 111 network. And also if I come on to router number 3 or route number 2 and have a look at its show IP BGP table, we see now that 20.1.1.0 network, it is only being learned through locally and not via router number 1, whereas earlier it was being learned via router number 1. Since I had not added another route map statement to permit other networks, all the routes are being filtered. So now let's come on to route number 1 and execute that route map command one more time. This time make it sequence number 20. And we do not need to put in any other statement in there. All the routes will be matched via this statement. So if I come on to route number 2 and do a soft reset one more time, and let's have a look at the BGP table one more time. Now we see that 20 network, which was initially or earlier over here, which was learned via locally originated, now it is also being learned via router number 1. But again, this is not the best route because for the network which is locally connected, of course router number 2 is going to choose that one. One important thing that you need to be aware of while doing BGP configuration, specifically iBGP, is the fact if you look at the routing table entry for this route, which is 50.1.1.1, 50.1.1.0, pardon me, then you see that the next hop is 10.1.1.2. Now this one is not directly connected with router number 1. If we come over here, if I come on to the diagram and remove these lines, we see that route number 1 is learning about this 50 network which is over here, and the next hop that it is learned from or it is trying to send the traffic to is the IP address of R3. Now this is interesting because router number 1 does not know about the IP address of 10.1.1.2. Now at the moment it does know about it because router number 2 has advertised this network via iBGP to router number 1, but it has not changed the next hop information for 50.1.1.0 network. So what I mean to say over here is that once you are doing iBGP related configuration, do ensure that you have valid next hop reachability to those particular networks. Otherwise, the route will be in the routing table, but it will not be made part of the routing table of the router. The BGP table will carry it, but it will show it as the not usable route. because next hop is the mandatory parameter for a route to become active. So router number 2 is an eBGP router which advertises this network 50.1.1.0 via iBGP router number 1, but it does not change the next hop value. We can do that manually by typing in the command. Let me just show you. If I come on to router number 2 and let me just show you this one more time, that this is the network 50.1.1.0 and it is being learned via 10.1.6, which is the IP address over here. Router number 4 fast Ethernet IP address and via 10.1.1.2. So if I come on to router number 2 and do a BGP rated configuration by typing in neighbor 20.1.1.2 and then this is the keyword which is next hop self, so that for this iBGP neighbor, all the BGP rated routes that it advertises to this neighbor, for those routes it will be the next hop, so that router number 1 does not have any issue while trying to reach those particular networks or NLRIs, network layer reachability informations. So now once that is done, now let's have a look at the BGP table of router number 1, which is over here. So if I type in do show IP BGP, now we should see that for network number 50, earlier the next hop was 10.1.1.2. Now the next hop has become 20.1.1.1. If this network had not been advertised by router number 2, then this network would not have been reachable 50.1.1.0. But now even if I do not advertise 10.1.1.0 by router number 2, router number 1 will still have the reachability to 50.1.1.0, because now we are saying that to reach to this network you just need to send the packets to router number 2. Another important thing that I want to tell you about regarding this part of the video is the use of community that I have just done, is that I used well-known community no export, so that the router 1's loopback address does not get advertised to router number 3 or 4 because they belong to different autonomous systems. Now these are well-known communities and the routers that are adhering to BGP protocol must act upon those communities. But there are other communities or community numbers that you can use, and based on those community numbers, like when I set the community to by typing in the command in the route map, by typing in the command set community no export, I could have typed any value like maybe 2000 or maybe 20, and now once that community is set and that route 1.1.1.1 is received via router at router number 2, then based on that community I can tell router number 2 that if it receives a route with a community of 20, maybe it is receiving hundreds and thousands of routes with the community value of 20. Then instead of acting upon on those individual routes, I can act upon those particular community values. And based on community values, I can take certain decision, like I can move the traffic to a different interface or maybe set certain quality of service parameters. But it really depends on the administrators. If I had set the community to, let's say, 20 and send the route to router number 3, which is a different ISP, then this ISP may altogether ignore that community, change that community value. It really is not the mandatory parameter that this ISP1 or ISP2 need to adhere to. So just remember that you can set the mandatory parameters and non-mandatory parameters as well. But for non-mandatory parameters, do remember that it is the discretion of that particular ISP that how they treat your particular networks. Of course, if you have got good relationship with the administrators and the engineers on the other side, then you can coordinate how to move your traffic based on the community values. Well, continuing from previous video, we have seen that how we have controlled the routing information based on the communities. Like we had controlled, and let me just change the Alright, we had controlled that how the loopback address of route number 1 is to be restricted to be sent over or advertised to route number 3 and route number 4. But at the moment, what really happening, now this is the other thing that I want to show you, that how we implement BGP in ISPs. What is happening at the moment over here is that this network, we are advertising this network and this network, which is 10.1.1.0 and 10.1.1.4 via router number 2 through network statements. So router number 3 knows that this network, of course, this is directly connected, so it has no problem reaching to this network. But this network, it is being learned through by router number 3 through two different ways. One is via R2 and one is via this path. So let me just pull up the router number 3 interface, which is over here, and do a show IP route. And let's have a look at the 10.1.1.4 network. For that, the next hop at the moment is 10.1.1 because of the shortest ES path via this one. But if I look at the BGP table of route number 3, we should see that there should be two entries for network 10.1.4. One is via this path, which is this, and the other is via router number 2, which is this IP address. And this one is the best path. This greater than sign, it indicates that this is the best path. Likewise, if I come and have a look at the network reachability information regarding this network, which is between route number 4 and route number 5, and the network is 40.1.1.0, we see that route number 3 is learning about 40 network via router number 5 and again also via router number 2. So essentially what is happening over here, let me just show you that if this network goes down, let's say at the moment this is the shortest path to reach to 40 network, this one. But if this network goes down, then essentially router number 3 knows that it can reach to this network via this path. Now this is the organization or our organization that we do not want our R2 to be used as a transit router. We do not want that this traffic should use our bandwidth and memory and also the CPU cycles to send the traffic out or interface utilization. Now we can do that, we can restrict it based on multiple methodologies, but let me just show you one pretty cool thing that we use in ISPs, and that is known as AS path filtering. So if I come on to router number 2, which is over here, and if I go into global configuration mode, then I can type in an access list based on AS path, and let's name it 1, and then if I do a question mark, do a permit, then over here I can define a regular expression. A regular expression will kind of tell the router that how it needs to act based on that or on those values that are defined in the regular expression. A couple of things that you need to remember about that is that if I type in caret, then this would mean the start of the character. Like if I type in caret and then let's say 1, then it would mean that this statement should start considering the string value of the AS path starting from 1. And if I type in, let's say, $, then it would mean that it should end the string value with whatever value precedes this $. So if I type in like 2.2 space 2 and then dollar without any space, then it would mean that the end character should be 2 of the autonomous system path. I can also use dot sign like this one, and it would mean that it should match only one particular single character. So really cool things that you can use by implementing this regular expression. There are other values as well. For example, you can use brackets to define a range of character that should be appearing in the AS path. and based on that you can take certain actions. So what I'm gonna try to achieve is that let's try to block the networks of router number 2 that are being advertised to router number 3 to only those networks which are local to R2. So it should not advertise the network which is 40, or even if I come on to router number, alright, 50 is not there because 50 is only being learned through router number 5. So if I come on to router number 2 and try to block 40 network to be advertised to router number 3, let's see how we can do that. So I type in the regular expression that start off with caret and end with $, so that all the AS path information which are carrying certain characters should be stopped. You see, if I come on to router number, let me just show you. If I type in do show IP BGP and have a look at the BGP table of route number 2, then we see that router number 2 is advertising 10.1.1.4 through locally network related command, or through, because it is directly connected with that network, and through network command the origin is local, which this 0 indicates, and also it is being advertised via 10.1.1.6, and this is the path, autonomous system path. Now that command that I told you about, that if I type in caret sign and $sign, this would mean that the autonomous system path should not carry any number in between, while in this case we have 4. So if I type in this, that I want to advertise only those networks which are locally generated, then all the other networks which are having autonomous system path numbers in them, they will be blocked to be sent over to our router number 3. So let's try to do that. Let's type in IP AS path access list 1 and do a permit. Type in caret sign and then the $sign. Now once that is set, now let's come on to BGP configuration mode for router number 2 and implement this AS path filter for that particular neighbor, which is 10.1.1.2, or the interface IP address of router number 3. And over here I type in filter list and then the list of name and number of that particular list, which in this case is 1, and also in which direction I want this filter to be implemented, which is outbound direction. So before I press enter, let me just show you that at the moment 40 is being learned through 10.1.1, but once we do that, we will see that this will be blocked to be learned via router number 2. So let's come on to router number 2 and press enter, and now let's have a look at the BGP table of router number 3. Let's quickly do a soft reset by typing in clear IP BGP, the IP address of the neighbor, which is 10.1.1.1, and it should send in the updates of its routing table. Now we see that earlier it was learning about 40 networks via 10.1.1, but now the filter that we have implemented for AS path, that particular entry has been removed. And of course it is learning about 10.1.4 network because that was generated by R2 through the use of network command, or it was locally generated on router number 2, so that AS path filter that we have implemented, it will not block that particular entry. As I told you that it will only block those entries which have the AS path information in the BGP table of router number 2. So by doing this configuration, we have essentially restricted this 40 network to use this path to reach to router number 3. Now even though this path is valid and is up, if this network goes down, this router number 3 will have no reachability to reach to route number 40, which we intended to have, so that our route number 2 is not used as a transit traffic between these two ISPs. Now this is very much practical life design, that you want your organization routers connected with external ISPs to not to be used as transit routers. Welcome back. In this video, I'm going to show you that how we can manipulate the AS path information itself to control the network reachability of certain networks. We have seen that how we can make filtering decisions based on AS path, but this is very important aspect regarding AS path manipulation that we can employ, which is known as AS path prepending. AS path prepending. And almost all the vendors support this particular feature. Now what this really does is that you see, once you are making a decision to reach to a particular network via multiple options or via multiple paths, then one of the criteria for tiebreaker is shorter AS path. In Cisco, we know that the first criteria is the weight, then local preference, then origin, and then comes the AS path. Of course, weight is Cisco proprietary, local preference is the standard, and also origin is standard. So if the path is originated via, let's say, R1 and reaches from R3 and R4 to R5, then the tiebreaker comes out to be AS. But in this case, since both the AS are same, then we have other parameters which are origin code, then MED or metric or multi-exit discriminator, then we have path, and then we have router ID, which comes out to be the tiebreaker for that particular network. But if we are concentrating on autonomous system path or AS path information, then essentially what we can do is that make one of the networks to appear to be more suitable to route our traffic. At the moment, let's have a look at router number 5 routing table and BGP table and see that which path it is preferring to reach to this network, which is 20110. So let's come on to router number 5 and let's just type in show IP BGP. So at the moment it is preferring maybe let's just come over here, and I have shut down this interface. Let's just bring it back up, and let's just hang on for a while until this BGP relationship comes up with router number 4 and we have a stable network topology. Alright, so neighbor is up. This is the router 4's IP address. I had shut down this interface. Now I brought it back up, and R2 and R4 are in established BGP state now. So if I have a look at the BGP table of router number 5 now, we see that this network 20110 is accessible via 4111 or router number 4 and via router number 3 as well. And at the moment, router number 3, which is having AS path of 3 and then 2, is more preferable. So let's assume for the sake of discussion and this concept is that at the moment this is the primary path, right? And this is the secondary one. This is not used at the moment to send the traffic to this network. So what we can really do is that let's assume that this lower path, this is high bandwidth and low cost. So high bandwidth and low cost in practical example. Now, wouldn't you agree that you would like your traffic which is coming from this internet portion, maybe organization number 2, to reach to your organization. Let's say you have got multiple users, hundred of users over here, and they are browsing the internet. So the request goes out and the response comes back in, which is in fact carries the more traffic or consumes more bandwidth. So you would definitely like to consume or use that link which is having high bandwidth and costs you the least. So in this case, let's assume that this lower path is the one that has lower cost. This upper path, it could be a backup path, it might be a copper based technology, or maybe let's say a satellite based backup link, so that if primary path goes down, only then maybe we should use the upper path. But at the moment we are seeing that the upper path is the primary one, which we can confirm by having a look at the BGP table of router number 5, that router number 3 is the preferred part. So let's try to manipulate this, and let's try to make the feature which is AS path prepending available for this particular configuration, so that the 20.1.1.0 network should appear to router number 5 with more preference through lower path as compared to the upper path. So let's come on to router number 2, and over here let's create a route map by the name of, say, AS path maybe, and permit 10, and over here I type in set AS path, then prepend, which is the keyword, and I am prepending my own autonomous system path number in the advertisement that will be sent over to router number 3. Now once that part is done, I need to go into the BGP configuration mode, and over here I type in neighbor, point it to the neighbor which is router number 3, and then implement the route map which is AS path in the outbound direction. So what will this do is that once the BGP updates are sent to route number 3, they will carry this AS path information with them, so that these networks will appear to be at a higher or at a longer distance with respect to the AS path. So lower AS path information or paths will be preferred by router number 3 or router number 5. So once we do that, and I come on to router number 3 and do a show IP BGP, or maybe force it to update its table. Now let's have a look at it one more time. Now we see that 20.1.1 network is reachable via 10.1.1 with longer AS path. So at the moment what is happening is that 20.1.1 network is being learned through a shorter distance, which is in this direction as compared to this straight path. This is the more preferred path, as we are seeing through the BGP table of router number 5, which is over, or router number 3, which is over here. So if I come on to router number 5 and do a show IP BGP, we see that at the moment there is only one path which is being learned in the BGP table of router number 5, and that is via the lower router or router number 4. Now this is interesting. You might get confused over here that why we are not seeing two paths, although router number 3 is sending the information back to R5 that it has reachability to 20.1.1.0 network. But where is the problem? Our router number 5 does not have any path via R3. If you have a look at this, there is only one path via R4. So where the other one has gone? Well, the problem is that this comes when BGP split horizon rule kicks in, and the concept here is that router number 5, it has learned about the network 20 via router number 4 with AS path of 4 and then 2 and has sent it over to R3. So if you have a look at the BGP table of R3, you see that the preferred path for 2110 network is via router number 5. So since this is the preferred path, this route number 3 sends this information back to router number 5 that you can reach to this network via this path. But since router number 5 originally sent this information back to R3, it will not install that information in its routing table. But that does not mean that route number 5 does not have information, or it cannot have the reachability to 2110 network if this primary link goes down. If I come on to router number 4, which is over here, and go to that particular interface which is connected with router number 2, which is FA0/1. Let me just show you this one, which is over here, and bring down this interface. Then what will essentially happen is that router number 4 will take back the information regarding that particular network, which is 2110, and send an update to router number 5. And then router number 5 will install the routing information which will be coming from router number 3 regarding the prepended path information. So let's come on to router number 4. Let's have a look one more time at the BGP table of router number 5, and we see that only at the moment there is only one way that this router can reach to network number 20. So come on to router number 4 and do a shutdown of this interface. Now once that is done, and coming back to router number 5 and do a clear IP BGP, and then the neighbor, which is 40.1.1.1, and soft inbound, and have a look at its routing table one more time, we see that now 2110 network is accessible via the upper path through the appended AS path that we had configured ourselves. So once we had earlier looked at the BGP table, we had thought that maybe this network is not accessible via other route, but that was not the case. That was the case of BGP Split Horizon, that it was not installing the route that it had already advertised itself to router number 3. So in other terms, it's just like that R5 is saying that, hey, router number 3, you can reach to 20 network via me, and router number 3, since it has got best path available via router number 5, is again sending that information back to router number 5. Let me just remove this one, saying that you can reach to this network via me, which is of course is not the correct information, because router number 5 had earlier said that you can reach to network number 20 via myself. So in this case, BGP Split Horizon rule kicked in and stopped that particular information to appear in the BGP routing table. Now once we had brought down this interface and this information was retracted regarding this reachability path, the other information which was coming from router number 3 can now make its way into the BGP table of router number 5, as we are seeing over here. Now this was a typical case that almost all engineers used in their topology when they are multi-homed and they want to prefer one of the paths over the other to maximize the resources and make efficient routing. I hope you have learned from this topology many things that you can apply in your environment, and I would like to thank you for viewing. Alright, in this video we are going to see what is DM VPN and how does it work. First and foremost, I must tell you that DM VPN, as some of you might think, is a protocol, but it's not. It depends on two underlying protocols. One is MGRE or multi-point GRE, generic routing encapsulation, and the other one is
next hop resolution protocol, NHRP. So why do we actually require DMVPN? Just quick scenario that let's say if you have a hub site or your central office, let's say this is head office or headquarter, and you have multiple remote locations like in this fashion. These could be within the same city or maybe across the continents, and you would not be able to, or your organization would not be able to have leased line across the continents because that would be too costly. The cheapest solution and the most efficient one would be to have internet connectivity with the internet cloud, and then on top of that run whatever VPN scenario or whatever VPN technology implementation suits your organization. Now in this scenario, let's say if these sites want to communicate with the head office alone, they can implement GRE across the cloud. Let's say this is the internet cloud. So they can have multiple VPN across the cloud to the head office. But the problem with that is that, let's say if you want to add more sites in the future, or you have removed certain sites, then you would have to take the configuration at the central location. And similarly, the major problem would be that what if these sites want to communicate, these remote sites want to communicate with one another? Now for that to happen, you would need to create tunnels among themselves as well, and that would again lead to the problem of full mesh, which is like this much number of links that you need to configure between the sites, depending upon how many sites you have, including the headquarter. Now in these kind of situations, DMVPN comes really handy. This NHRP protocol essentially does a registration of these remote offices or remote locations with a central hub, which says that this is my, let's say, underlying IP address or the infrastructure IP, and let's map this one to the NHRP or the overlay IP or the tunnel IP or the VPN IP. So if this is this one over here, this is the public IP, I am referring it as the underlying IP, and this is the VPN IP or the tunnel IP, I am referring this one as the overlay IP. So this central location has got the mapping against all these branches, so that whenever a packet comes in from this location, let's say number 1, destined for this one over here, the headquarter or the central or the hub location will have a look at the mapping table and will immediately come to know that if the packet is destined for an overlay IP which belongs to here, it needs to send it to its underlying IP address, which would be over here somewhere. The second benefit of DMVPN is that you do not need to configure separate configurations for inter-remote or inter-spoke communication. They will automatically be communicating with one another using just a couple of commands to configure that. So it's just that these mappings which are being held with the central office, they will be kind of delegated or shared with the remote locations, so they will communicate directly instead of going through the hub router. So very neat and clean technology, and really helpful if you are implementing VPN spanning across multiple continents or maybe multiple countries. So now let's see how do we configure it on actual Cisco routers. Let me just pull up this topology over here. It's created in GNS3, pretty simple topology that I have put in, just couple of routers. This one, the one in the middle, I'm assuming that is the internet cloud, because obviously if you have direct connectivity between your locations, then there is no concept of VPN. You wouldn't like to add in the overheads of VPN. So in this case, we are assuming that this one R1 is the head office or headquarter, and these are the remote offices or the branch offices. And I have also configured the basic IP scheming over here. It's just that over here I have given the IP address of 10.10.10.0 with 1 here, 2 here. Over here it's the network of 10.10.10.4 with 5 here and 6 here. Over here it's the network of 8 with 9 here and 10 here. I've also done the basic BGP configuration, just the point-to-point BGP sessions. But one change that I've done is that I've used the autonomous system number 1 here, autonomous system number 2 here, but I've kept the same because I'm assuming that since it's the same organization, these 3 routers connected across the internet backbone, so they might have the same autonomous system, which is 1 here and 1 here. So just a reminder that once you are using the same autonomous system across different autonomous systems, so you would like to, once you have the peer relationship and you want the BGP updates to be incorporated into the BGP table, the statement that you need to give in the BGP router protocol process is that allow AS in. It's like the statement is something like neighbor, whatever is the neighbor IP address, and allow AS in. So that once R2 sends the BGP updates received from either R4 or R1 to R3 or the other way around, the router does not discard it, because otherwise if it finds its own autonomous system number in the BGP update, it will discard that. So that was just a quick overview of the topology that I wanted to give you. Now what we are going to do is that we are going to establish DMVPN across this backbone like this, in this fashion, and we'll see ultimately that the communication will be between R3 and R4 will go directly through the internet router and not via R1. I'll show you that how does it happen, and probably we'll also implement some security as well. So let me just remove this one and pop up the let me show you just first the configuration. I put them on hold, so turn them on and do show run quickly just to show you the configuration. This is the IP address which is connected to R2, and besides that this is the simple BGP configuration that I have just done prior to recording of this video. Likewise on R2 there is nothing much, simple BGP configuration. The same is true for R3 and likewise for R4. So once we come on to R1, let me just clear this one. We need to make this one as a hub router. So to do that, I come into R1 and I create a tunnel interface, interface 0, and I give it an IP address, let's say 20.20.20.1, and give it an IP address or subnet mask of, let's say, 24. Then the next thing that you would like to do is, since you're creating a tunnel, you would like to define the tunnel source, which in this case is the fast Ethernet 0/0, or from where the tunnel is originating. So tunnel is originating from this interface, fast 00. So here it is. And also the tunnel mode by default is GRE, but in this case we are going to use a GRE multipoint. So GRE and multipoint. These are the basic tunnel configuration. But for NHRP, first and foremost you need to type in NHRP and the network ID. This has to be matched on all the I would say network that is connecting to this particular hub. It has to be matched between them. If the network ID is different, then NHRP tunnels will not come up. So let's call this network ID, maybe give it a numeric number. We have got a range of 4 billion. So let's just use 5. And also the next command is IPNHRP map multicast and dynamic. What this command does is that it really tells this router that it will map the addresses dynamically. The addresses that I talked about, that the registration process, it will map them dynamically. That's all. That's all there is to it as far as the configuration of the hub router is concerned. So do a quick show run, and these are the 2 configuration commands related to DMVPN technology. Now to correspond to this, we come on to router number 3 and do the replica of that, but a little bit change in there. First create the tunnel interface and then give it the IP address 20.20.20.3 and subnet mask of 24. Then tunnel source. In this case, tunnel source is, let me just check it, 1/0. So tunnel source is fast Ethernet 1/0 and tunnel mode is GRE multipoint. Next is the NHRP related configuration, which is IP NHRP. First and foremost is the network ID, which we had configured on R1, has to be matched over here, which was 5. Then next hop server IP address, that has to be the VPN address that we had configured, or 20.20.20.1. We need to add in NHRP. Next we need to tell them that IP NHRP map multicast and then the IP address of the spoke or I should say hub router's tunnel interface, or the overlay IP address, which is 20.20.20.1. and also we need to tell it, my mistake, sorry, I need to undo this one, and it has to be the underlying IP address, so 10.10.10.1. and then how to reach to this next hop server using this one. So the command is IP NHRP map this overlay IP to this underlay IP. And now quickly do a show run so that you can have a look at the configuration of this NHRP. So this is the same as was on the hub side. This is the server which is telling this router that this is your next hop resolution protocol server. Now to reach to this server, we have mapped it to the underlying IP address of the hub router. Alright, so this is the configuration over here. And once you do the tunnel configuration, make sure that you, especially for DMVPN, make sure that you shut down the tunnel and then you do a no shut, so the tunnel comes up. Now once it does that, if I come on to R1 and I do show IP NHRP, we see that a tunnel indeed has come up. Dynamically learned spoke has come up. We see that this is the IP address and its type is dynamic because it has been done dynamically. There is no other. So once we configure router number 4, which is here, we'll see that another entry will be added in the output of show IP NHRP. So to do that, again the same procedure, IP rather first create the tunnel interface and then the IP address 20.20.20.4 and then the subnet mask of 24, and after that tunnel source is fast Ethernet 0/1 and tunnel mode is GRE multipoint. IP next hop resolution protocol NHRP next hop server is 20.20.20.1 and map multicast to the underlying IP address and map the overlay IP address, which was 20.20.1 to the underlying IP address. Do a shut of the tunnel and then no shut. So once we do that and I come on to R1, we should ideally be seeing 2 entries corresponding to router number 3 and router number 4. So is there something that I missed? Let's just quickly check the entries, do show run. Network ID statement is missing. You spotted it, network ID statement is not there, and it has to match the other 2. So IP NHRP network ID 5 shut down the tunnel and no shut the tunnel. I'm doing shut and no shut because sometimes when you do the configuration on tunnel interfaces, especially in the case of DMVPN, they do not get refreshed automatically unless you give it a bounce. So once you do that and come over here, let's just clean the slate. Now we have got two entries. One is for router number 3, dynamically learned, and the other one is against router number 4, again dynamically learned. So you can see here that we have got just two routers. If there are multiple routers, like tens of routers or maybe hundreds of routers connecting to the hub, you wouldn't have to do any configuration on the hub. All you have got to do is do the configuration on your spokes, and they will automatically be registered with the hub, and then they can intercommunicate. Now the next point that I wanted to tell you is that at the moment we have not run any IGRP or overlay protocol to communicate between these routers. So what we can do is that we can run OSPF or EIGRP or whatever you source you can run on the overlay network. So let's try to do that. Let's just configure OSPF protocol, and I want to show you one important thing in here, that let me just bring in R1, and in tunnel interface configuration mode, I'm gonna do IP OSPF 1 and area 0. I have put this one in area 0, and likewise if I come on to router number 3 and type in IP OSPF 1 area 0, and similarly IP OSPF 1 area 0. Now we see that the interfaces, not the interfaces, the adjacency of OSPF neighbors has come up, but we see that over here adjacency is being reset. It is being forced to reset. It is kind of this, the hub router R1. It is forming the relationship or adjacency with the R3, and then breaking it, and then forming with R4, then breaking it. So it is keeping a continuous cycle of that. Now the reason for that is because by default the tunnel interface is OSPF network type is point to point, while in this case it is not point to point, it is in fact point to multi-point. So once it establishes a relationship with, let's say, R3, and it receives an OSPF packet through R4 or from R4, it breaks that adjacency and tries to establish adjacency with R4. Once it does that successfully, it then receives a packet from R3, and then kind of considers that maybe it needs to, since these are point-to-point interfaces, so on point-to-point you cannot have multiple neighbors against one point, so it has to establish with any one of them at any given time. So that's why it is keeping on breaking and making adjacency with router number 3 and 4. Now there are multiple ways to do that, how to resolve this problem. One way is to change the, let's say, network type, OSPF network type to broadcast, but in that case you will have to then deal with the DR and BDR election. Normally you would like to have DR at the hub, but another way around is to change the OSPF network type to point to multi-point instead of point to point. So let me just quickly show you. If I come on to my hub router and do show IP OSPF interface brief, this is the gotcha that I'm talking about. That is, state is point to point. We need to change it to point to multi-point. So I type in IP OSPF network point to multi-point, and do the same on spokes as well. IP OSPF network point to multi-point. Similarly for here as well, on router number 3, IP OSPF network point to multi-point. Now once we do that, we'll see that we'll have consistent OSPF adjacencies between the routers. So do show IP OSPF neighbors, we have got these two neighbors, router number 3 and router number 4. Now if I come on to router number 3 and do a show IP route, we know about this IP address 20.20.21, which is of course the R1 or the hub IP, and we know about the network which is connecting to R1 and R4, this one. So here if I try to ping, let's say 20.20.24, which is the VPN IP address for or the tunnel IP address for router number 4, we are able to do it. And similarly we are able to do the IP address from router number 4 to router number 3 tunnel interface. Now important thing that I want to show you, that at the moment traffic is going through the hub router. How do we know that? Let me show you. These are the two routers, and let's do a trace. Do trace 20.20.20.4 n is that, do not resolve it, and do just one probe, and we see that the first packet goes to first 20.20.21, which is the hub router, and then to 4. No matter how many times you do it, it will remain the same. We want to eliminate this hop because we do not want this traffic to go through the I would say through the hub. Rather, it should go directly to the other end using the optimum routing possible. So as I had mentioned earlier, that this next hop server, it needs to share the mapping with these two. At the moment these are 2, but whatever the spokes are there. So to do that, one command needs to be entered on the hub side, which is IP-NHRP redirect. Am I in the right interface? Interface tunnel 0. IP-NHRP redirect. This command is not here. Okay, let's come on to router number 3 and type in IP-NHRP shortcut. Okay, so this version does not have this capability for this phase of NHRP, but in the later version of NHRP, these are just 2 commands. Let me just type in here: IP-NHRP redirect on the hub router, and IP-NHRP shortcut, IP-NHRP shortcut on the spoke routers. What we'll do is that eventually you will see that the first time that when the traffic passes, it will pass through the hub router, but from then onward, since the spoke routers will have the mapping received from the hub, they will use the optimum path and not through the hub router. Now, once that is done, what you would also like to do is, since this traffic is passing through the public network, you might want to implement some kind of security on top of your overlay network, so that if somebody is trying to eavesdrop or trying to sniff the net traffic, he should have difficulty in doing so. So to do that, let's come on to R number 1, and we are going to configure IPsec, and then we are going to protect our tunnel using that IPsec. So IPsec, as we know, has got 2 phases. First is the secure key exchanges, and then the actual data security features. So first is the key exchange phase, how it needs to be handled. So to do that, I'm going to type in crypto-ISAK-MP and make a policy. Let's give it a number of 5. And then encryption that this phase is going to use is AES, and the authentication is pre-share. Authentication is pre-share, and also the group is like how many which group of it is gonna use. Like if I show you over here, so we are gonna use Diffie-Hellman group number, let's say 2, depending upon the how many bits you want to use for encryption purposes. The next command related to security association related to key exchanges is crypto ISA KMP, and then the key in plain format, let's say key is 123, and then the addresses from where what are the eligible addresses which this router can receive the key from or can associate security associations with. So let's say if at the time being we say that it can have it received from any of the addresses. Now the next thing, these two commands are related to the two instances that I have just put in. These are related to the first phase or the key management of the IPsec protocol. Next is the actual payload security. So to do that, again crypto, but this time we are going to use the IPsec, and then the transform set, whatever you want to name it, let's just call it ABC, and after that give it the parameters of the transform set. We are not going to use the authentication header. We are just going to encrypt the payload, so encapsulated security payload and advanced encryption standard. That's what I'm going to use. Now once that is done, get out of here, or you can even mention that what kind of mode you want to use, either tunnel mode or transport mode. So over here you can type in mode is, let's say, transport, and next thing is map this into a profile, crypto IPsec profile, and the name of the profile is say security, let's say security, and then we need to mention that in it the transform set that we had just created earlier here. Let's set transform set, and the name which was ABC. Now let me show you how does it look like, because there is certain redundancy in configuration, but that's how Cisco has implemented it. We cannot do anything at the moment until they change something. We have just created transform set over here. Instead of creating a policy profile and then reflecting the transform set in here, it could have been a one-step process as well that simply reflect this transform set into the configuration, but that's how Cisco has implemented it. And this is the first phase of IPsec, which is for securing the keys. Now we need to reflect this name security into the tunnel configuration, that how to secure this tunnel using this profile. So go into the tunnel configuration mode and do set or tunnel protection using IPsec, and profile was security. Now the same configuration will go on to the spoke routers, because we have not changed as such anything. Addresses are the same, this one all addresses, and we are going to use the same key over there as well. So let's just copy this one, and we can also see that it has received a non-IPsec packet, so it is giving us log. So let's come on to router number 3 and paste this configuration and go into tunnel interface to map this IPsec configuration to the to protect the interface, and type in tunnel protection. IPsec profile is security, and similarly come on to router number 4, put this configuration and go into interface tunnel and do a tunnel protection IPsec profile security. Bump these tunnels just to ensure that everything is okay. Do a no shut over here as well. Shut this interface and then do a no shut. And now coming on to the hub router, let's see if our first of all, if our NHRP has come up, then OSPF protocol should come up, OSPF adjacency should come up with the two routers, and we should have everything set up. So do show IP NHRP. We have got two dynamically done tunnel points, 3 and 4. Let's see if we have got OSPF relationship. Oh, it is coming up. So third is up, and let's give it a couple of seconds till 4 also shows up. Now this time, this communication that is going on between these spokes and the hub, it will be a secured communication, secured through IPsec protocol. So, and the other one has also come up. So let's see, do show IP OSPF neighbors, and do show crypto IPsec security associations. So crypto endpoint 1 is 6, 10.10.10.6, which is router number 4, and the other one is 10.10.10.10, which is router number 3. So now we have successfully configured the DM VPN. Let me just quickly show you one more time the end configuration of IPsec. This one is IPsec related configuration, pretty straightforward, and this is the NHRP hub side configuration to make DM VPN work. And if we come on to the spokes, IPsec configuration will remain the same, no change in there, but a slight change on the part of spoke configuration where you have to mention or map the overlay and underlay IP addresses so that the tunnels can work. The one thing that I could not configure over here because of the iOS version that I'm using was to show you that how communication between the spokes go directly through the optimum routing path instead of going through the hub, and that configuration is done by using IP NHRP redirect command on the hub router and IP NHRP shortcut command on the spoke routers.
Hello friends, a lot of students have asked me to produce some lectures regarding ISIS protocol as well, how we can use it on Cisco, and also what I have done for this scenario that you are going to see in a while is that not only that Cisco routers are in there, but also I put in Juniper routers as well, which are very much used in main service providers or ISP networks. This is just one flat network. You can make it complex as much as you want to. You can add multiple routers in different hierarchies or in different methodologies, but the point is that you should understand the underlying concepts, and once you get the hang of that, you will be able to make complex topologies by yourself. Now I can jump right into the configuration portion and just explain to you. I have already, now you can see the topology, but the point is that it would be better for those who may not have a good understanding or they may not be even aware of ISIS protocol. For them, I would like to have a little bit of about ISIS theory so that they understand the underlying principles and what we are really talking about. And based on those foundations, they can then self-study to further improve their level of knowledge. So let me just pull up a whiteboard and give you a couple of tips regarding ISIS protocol. So ISIS stands for Intermediate System to Intermediate System, and this protocol, it was designed by ISO in its standard, which is 10589, which defines the ISIS being the routing protocol for CLNS traffic type or connectionless network services. And ISIS is quite old protocol. It has been around since 1980s, but mostly it is used in large service provider or ISP networks because of the way that it handles the traffic in large service provider environments. And
what I mean by that, comparing it to compare it to OSPF, because IS, this is also a link state protocol, just like OSPF, but OSPF works on layer 3, or if you look at the packet of OSPF, you will see that the OSPF related information is encapsulated in the IP packet. So we need the layer 3 information if we want to communicate using OSPF, but for ISIS does not work on IP layer, rather it interacts directly with the layer 2. So if we have a packet like, or a frame I should say, so these are the, let's say these are the layer 2 fields, then in case of OSPF we would have first the IP header over here and then the OSPF related information. But in case of, so this is OSPF and this is layer 2 information, this is layer 3 information. But in case of ISIS, let's say if we have got this layer 2 information over here, then we have no layer 3, rather instead of layer 3 we directly have ISIS information. And after that we can put in an information like maybe IPv4 or maybe IPv6. So that is also one of the benefits of ISIS, that if large enterprises or large service providers, they want to deploy ISIS in their network, they would not need to have another protocol or maybe change it to another protocol to migrate their networks from IPv4 to IPv6. Like in case of OSPF, we know that OSPF version 2 that is currently being used. So OSPF version 2, we are currently using it for IPv4 routing. But if we need to migrate our network to IPv6 addressing scheme, then OSPF does not have any support for that. We would need to have another protocol, which is of course there, but we would need to run it maybe in parallel to IPv4 till the time our networks are completely shifted to IPv6. So, and the protocol is required. So, and the protocol means further overhead on the CPUs and the resources of the router. And more LSAs will be flooded in the network, because one set of LSAs will be for IPv4 and the set of network will be for IPv6. In case of ISIS, this IS, as I told you about, intermediate system, generally this is known as the router. There is another terminology which is ES, which is end system. This is like the host. Then if we talk about OSPF, we know that there are links. But in case of ISIS, we call those links as circuits. Then there is a concept of designated router and backup designated router in case of OSPF. But in case of ISIS, there is no backup designated router, and the designated router is not called as designated router, rather it is called as DIS, or designated intermediate system. In OSPF, we know that the information regarding the link states and their cost, that is flooded using the LSAs or link state advertisements. In case of ISIS, that information which is carried in packets, those packets are known as link state PDUs. So LS for link state and PDUs. So whenever you see LSP written with respect to ISIS, you will immediately come to know that we are talking about link state PDUs. Then like in OSPF, where we have a concept of database descriptors, which carry the information regarding the database information in a particular router for OSPF databases. In case of ISIS, that is known as partial sequence numbers, PSN, or complete sequence numbers, CSNP. And it's like if a router, let's say this is router over here and this is another router, and this router sends this router with a packet which says that maybe PSN, certain PSN information, then this router will come to know that the router number 1 maybe, and this is 2, then router number 1 does not have the complete database. So it will send the information that has been required or requested by router number 1, which has been missing in this partial sequence number. If it sends the complete sequence number packet, then it would come to know that the router number 1 needs the complete information regarding the databases. It does not hold any information in its database, so whatever information is available with 2, depending upon the packet type that we are just gonna, or the area type that I'm just gonna talk about, it will send that information to router number 1. So just remember that PSN partial sequence numbers and complete sequence numbers are very much part of the packet types that we talk about when we are discussing ISIS protocol. Then just like in OSPF, where we have concept of areas to break the SPF domain, and by breaking means that to curtail the flooding of SPF in certain area, the same concept has been implemented, or I would say that since they were kind of being developed in parallel, so the same concept more or less it lies with ISIS as well. And the concept is that in case of ISIS, the areas are there, but besides areas there is another concept which is layering, and there are only two layers. One is layer number 1, so layer 1 and layer 2, just two layers. And let me just clear this one so that we can start off with a clear slide. Let me just remove this one. And as I was removing this cluttered output, this clutter that was written over here, I just noticed that I have mentioned layer. My apologies for that. This is not layer, this is in fact level. So let's just correct this one. These are level 1 and level 2. Now we know that if we compare this OSPF with ISIS, we know that in case of OSPF, the areas can be either a whole router can be a single area, or maybe one of the link in between the two routers can be in a single area. But in case of ISIS, a complete router has to be in a given area, and the links of the router or maybe routers, they can belong to the levels. They can either be level 1 link, or they can be level 2 link, or they can be both level 1 and level 2. Now you can consider level 2 links as analogous to area 0 of OSPF, and what I mean by that is that level 2 links or routers, if we are talking about level 2 routers, the routers which have got at least one of the interface belonging to level 2, what it would mean is that that router would contain the information about the level 1 as well as level 2. So let me just put it this way. Let me just draw a couple of routers. Let's say these are a bunch of routers, and this is level 1 router, and this one is also level 1 routers, but these are in between, these are level 2 routers. So these level 2 routers, they will not only contain the information which is related to these level 1 routers or the networks connected with within this domain, but also about the level 1. But level 1 routers, they will only contain the information about level 1 networks. So this level 1 network, if it has got, let's say 10 or 20 routers in here, all are in level number 1. I'm not talking about the area, I'm talking about the level at the moment. All of these routers may be in level number 1 or level 2. They could be part of either one area or multiple areas. But let's just say that for the sake of discussion of levels that I'm talking right now, let's just say that they are all part of one area. This one area can be divided into multiple levels that I've just said. So as I was saying, that level number 1 routers, they will only contain the information about level number 1 and not level 2. So we can kind of say that level 2 is like analogous to area 0 of OSPF, and level number 1, it is like stubby network, rather totally stubby area if we are talking about Cisco terms. And it's because in case of all routers in a level 1 area, then not only that information will be stored which might belong to level 2, but also any external routes. So if you remember from OSPF protocol, that OSPF protocol in totally stubby areas, which are in fact Cisco specific term. So in totally stubby area, we know that type LSA 5 as well as LSA type 3. So these two LSAs do not make their way into totally stubby area. So instead of that, only a default route is present. So just like in case of OSPF, the case is the same in ISIS protocol as well. That for level 1 routers, they not have no idea about level 2 routes or the external routes that are connected with level 2 routers. Now you might be wondering then, what is the use of areas? Well, areas, if you have got, let's say, a couple of routers like this one and some more routers, let me just change the color like this one, and maybe put it back to, maybe let's just use green this time. So let's say that this router over here, and first let me say that this is area number 1 and this is area number 2 if you are talking about ISIS. And let's also assume that these two routers, these are level 1 routers. It means that they will have no information about the level 2 routers either within this area or maybe from other area. But if this router, this one, this is level 1 and 2, so it means it will have the information, or it will contain the databases, two databases, one for level 1 routes and the other one for level 2 routes. So level 1 will be within this area and level 2 database will contain the information from another area. Now this router over here, this one, this will not contain the level 1 information coming from other areas like area 2, or maybe if it is connected with other different areas. Rather, it will only contain the information which has been shared with it by the other routers which was available in their level 2 database. So it is important to remember that routers in a single area, they share the level 1 and level 2 database information. But if the routers are in different areas, then only level 2 database information is shared. From implementation point of view, if you know about OSPF, which I know that you must know, you must be knowing. In case of OSPF, we know that we have to have a area 0 or the backbone area that we call about, and the routers that belong to the backbone, they need to have at least one interface connected with the backbone. But in case of ISIS, and this is the beauty of ISIS, that it is so much scalable that we do not have to have a backbone area. Instead of backbone area and then connecting all the routers to that backbone area, what we have is that we could either have L1 or L2 routers or just L2 routers. This router is not connected with any L1 router, so it is only having L2 database. So what would happen is that, let's say if these are the routers connected in this fashion, they are all, say, L2 routers or L1, L2 routers depending upon the topology. Let's say this L2 router again is connected with multiple L1 or L1 and L2 routers both. So what would happen is that all the routers that are interconnected and having their databases at L2, they will automatically form the backbone area. Although individually they will be part of different areas. So it will not be like you have to have one complete area spanned over multiple L2 routers. Rather, L2 routers belonging to multiple areas will automatically share the level 2 database information among one another and hence provide the reachability information for all over the network. Besides the scalability feature that ISIS provides over OSPF, ISIS is also faster in convergence as compared to OSPF because it takes less number of packets to form adjacency and share information. So that pretty much covers all the basic details of ISIS. In fact, I had intended to keep this video short, but you know, it's such a vast topic. Even now, I fear that I might have skipped some of the nitty-gritties regarding ISIS protocols, but let me tell you that all the details that I have mentioned so far, if you have got the hang of that and if you have got some understanding developed regarding ISIS, then you can build upon it. You can study yourself, you can dig into the details of ISIS protocol. At least now you know that what it does. It is an IGP protocol which is uses link states messages to share information about the status of links and the connected routes with other routers, and then it uses the SPF or the Dijkstra algorithm, just like in case of OSPF, to calculate the shortest path to the nodes or the intermediate system or the routers, and then automatically based on that calculates the reachability information for certain networks. I'm just gonna stop the video over here, and in the next video I'll start off with the configuration portions of ISIS on both Cisco and Juniper routers. Alright, so here's the topology that we are gonna use for this scenario. We have got two Cisco routers, R1 and R2, and we also have got three Juniper routers, GNS 1, 2 and 3, and they are connected in this fashion. And these are the IP subnets that belong to those particular links, like we have got 10.110 with .1 IP address assigned to E0 or gigabit Ethernet 0 interface of this GNS 1 router, and .2 over here, and likewise so on and so forth. The IP addresses have been written over here. And what I've also done to save time is that I've given the IP addresses or configured the IP addresses on the respective interfaces of both the Juniper and the Cisco router. So what I'm gonna do is that let's just pull up the Cisco router initially, this R1, and let's do the ISIS related configuration onto that particular router. So this is router number 1, and to start off with the I would say ISIS configuration, first we need to get into the ISIS protocol configuration mode, and over here we just need to define the now the protocol is enabled, but we need to define the area, and we do that by typing in the command which is network entity title, and after that we need to give the address or the ISO address to this particular intermediate system, as we talk about ISO or the router in case of IP. Now the first field, this ID or the address, it usually ranges from 8 to 20 bytes, but most of the time it's of 10 bytes, and I will just tell you that why is that, but it can range from 8 to 20 bytes, pardon me. And the format is that starting off with the very first or the most significant section is the AFI or address field identifier. I have put in 49, which is equivalent to the private IP address classes that are defined by RFC 1918 in case of IPv4 addresses. So this 49 means that we are going to use a private network address type. After that will be the area ID, and this can range depending upon your particular needs and requirements and your own solution. What I'm going to do is that I'm going to just assign one section or 2 bytes for this particular field, area ID. So I'm going to put in that this router number 1 belongs to area 1. And remember that these numbers that I'm putting in, they are all in hexadecimal. After that we have got 6 bytes divided into 3 sections, and they belong to the system ID, and it has to be unique in a particular area. Usually you can put in any number over here, but what we like to do is that we kind of translate the loopback IP addresses into the system ID, and it's very simple to do that. Let me just show you that how we will do that. I have given the loopback IP addresses as well to all of these routers. Loopback 1.1.1 belonging to GNS 1, then 2, then 3, then 4. My mistake, 4 is over here, and 5 is on to router number 2. So loopback IP address of router number 1 is 4.4.4.4. If you convert it into, let's say, like this, because we know that we can put in 3 digits in each octet of IP address, right? So after that, if we want to convert these 12, I would say numbers or 12 digits, partition into 4 sections, and I want to change them into 12 digits but partition into 3 sections, then definitely each will be carrying in 4 digits. So that's the way that we implement or we write down the system ID portion of the net field in ISIS protocol. So I would be writing like 0040, then 0400, and afterwards 4004, and that will become the unique system ID of that particular integrated system or the router for that particular area. So let's just remove this one. I just wanted to explain it to you that how we usually define that. Let's just pull up the router and let's just assign it the system ID. So 0040, then 0.0400, and in the end 4004. Now we have got how many? 6 bytes over here, then 7, and then 9. We are still need to have defined one more portion which is mandatory. I am repeating, to define the network address or the net address, and that is the last field, which is known as network or net selector, I would say. And this is usually of 1 byte long, and it identifies the information that is being carried in that particular system. In this case, we are running the ISIS protocol on an intermediate system, so or the router. So that is why this field will always be 0, since it is identifying that this is the router or this is the device which is running ISIS protocol. So that's it. I press enter over here, and now we have successfully made this particular router part of ISIS system, having an area ID of 1 and system ID of this. Now we also need to enable ISIS protocol onto the interfaces. So I'm gonna enable it on loopback 0 and FA0/1, which is connecting it to the GNS1 router. So let's quickly do that. Let's just go into loopback interface and type in IP router ISIS, and once I do that, the interfaces will belong to the default state of levels, which is level 1 and 2 both for those particular interfaces. I can restrict them to a particular interface by typing in, let's say, ISIS, and then circuit type, and then define the level, that whatever level I want to, but I'm gonna go with the defaults at the moment, and we'll change that afterwards. Similarly, let's go into FA0/1, and over here I also type in IP router ISIS. Now after that, if I do show CLNS and interfaces, and we see that this is the interface that is connected with GNS1. We see that this interface type is level 1 and level 2, and we can also see the ISIS included MTU of this particular packet as that of 1497. This is important to see because once we will be integrating this router with the GNS router, we'll see that there will be a mismatch of the MTU, and because of that, these routers will not become neighbors, or they will not be able to form adjacency for ISIS protocol. By default in ISIS, each link does not matter that what is the bandwidth for that link. The value or the cost for each link is 10. So we can see over here that the metric value is 10 for IPv4 protocol, and it is also 10 for IPv6 protocol. Of course, we can change these values, but by default they are 10. So if you are kind of traversing multiple links, then these 10, 10, 10 will be added as many times as the number of links that you traverse. And similarly, if I bring the output down, we can also see that the same type of parameters that we can see on loopback 0 interface. Now let's head over to the Juniper router, and let's do the basic basic ISIS rated configuration onto that router as well. So here I am on GNS1, and I have just done the initial interface level configuration and nothing else in there. So to configure the ISIS on GNS, I type in set and then protocol, and before that I also need to enable the interfaces for ISO family. By default, Juniper interfaces are not able to listen to or send traffic related to ISO, so we need to enable them, and the way to do that is set interfaces EM0, then unit 0, and then family is ISO. For IPv4 we use INET, and for IPv6 we use INET 6, but for ISO type of services or protocols we will be using family ISO in parallel to INET. So I press enter over here, and after that I need to give in the command set protocols IS and the interfaces that belong to this particular process. So I type in interfaces EM0, which is connecting or EM1. I believe this is EM1 because yeah, this one is connecting with router number 1. So let's enable it on EM1, and since this router is also connected with GNS2, so we need to enable it on EM0 as well. So once we do that, now we also need to assign the network or the net or the address or the identity for this router as well. So to do that, we need to do that in the loopback interface. So I type in or set protocols IS interfaces, or rather I should first start off with that interface. So interface loopback 0, unit 0, family ISO, and then address, and then the address that we want to assign. So I'm gonna go with 49.001 and then 0010.010.11001.001.00, just like we had configured on Cisco router R1, and then press enter. And now we also need to enable the ISIS protocol on this particular interface. We have just enabled the family ISO and given it the address, but not enabled it onto a particular interface like we did using this command. So I'm going to type in set protocols and afterwards ISIS, then the interface, and then loopback 0. And let's do a commit over here. Let's just save the configuration. And once the configuration gets saved, let me show you the command run show ISIS adjacencies, and we see that we have not established any neighbor relationship with router number 1. So what I'm gonna do is that let me also show you one more thing, which is run show ISIS interfaces, and then press enter, and let's just do a detail for, let's say, EM1 or EM0 interface. It should have been EM1. We have enabled it on EM1, right? EM0. Oh, my mistake. So we also need to enable it on EM1 interface as well, which is connected with Cisco router 1. So let's just run that command, enable it on EM1, and do a commit. So once the configuration gets saved, have a look at the output of this command one more time. EM1 is not being shown. Let's have a look at our configuration by typing in show and then display set. So we have given the IP address to okay, so this is the interface EM1, and I have not enabled ISO family on this interface, so let's do that. Let's enable ISO family on this interface as well. So I type in EM1 and save the configuration, and now let us see the output of that command where we see the ISIS interface. So now we have got this EM1 interface, and if I see a detail of this interface EM1.0 or maybe interface EM1.0, then detail, or if I issue the command, let's say run show. In fact, I just want to show you specific information, because you see at the moment we will not be having adjacency or neighbor relationship between these two routers, because that's the difference how Juniper interprets MTU as compared to Cisco. So let me just type in run show interface EM1 and have a look at the output of this information. Now we can see that the type of this link is Ethernet, and I just wanted to show you this thing, that MTU is 1500 and the protocol ISO MTU is 1483. In case of router number 1 on Cisco, if I bring it over here and let me just quickly go into enable mode and do show CLNS interfaces and press enter, and over here we had seen, let me just see where was that information. So this is that I was talking about, that the MTU for ISO is 1497, but in case of Juniper we can see that it's 1483. So these two, since the MTU is mismatch as far as the ISO information is concerned, we can ping the interfaces, we can ping the IP addresses of the interfaces of both these routers, but since the MTU for ISO is different, so that's why they will not form the adjacency. And let me just run the command on Cisco by typing in show ISIS neighbors. We see that no neighbor is up. And if I do a debug on this router by typing in, let's say, debug ISIS and packets or maybe CLNS and events, you will find out that that is exactly the reason that I'm talking about. So the problem with Cisco is that Cisco shows you the MTU of the interface. If I type in, let's say, show interface, then FA0/1, it shows that the MTU for this interface is 1500, but in fact this is not 1500, this is in fact 1514. What Cisco is not showing us is the layer 2 information or the layer 2 encapsulated header information for this particular interface, and it is just showing us the information which is IP based. So I hope you are getting my point, that it is kind of skipping that information that belongs to the Ethernet layer 2, which are 14 bytes. But in case of Juniper is using in fact 1500, and it is exactly showing what it is transmitting, the maximum unit size that it can transfer on the wire. But in case of Cisco, it can go up to 1514 because it is not showing us the correct MTU size. That is one of the, you can say, gotchas with Cisco that you just need to remember, that show that the interface MTU that is shown using the command show interface, that is not the exact or the correct MTU size of the interface, rather it is the IP MTU. So we can correct this one by going into the Juniper, and in Juniper I can type in set interface and then EM1 and then give it the MTU value of 1514 to make it at par with Cisco. So let's do that and do a commit, and then we will have a look at the output of this command one more time. Run show interface EM1, and now we see that the ISO MTU has matched with the Cisco one. So now ideally these two routers should form the adjacency. Now let's run the command show ISIS and neighbors, and indeed we see that since by default level 1 and level 2 both levels are enabled on Juniper as well as on Cisco, so we can see that two adjacencies have been formed with the same system ID, level 1 and level 2. Likewise, if I come on to Juniper router, I can type in run show ISIS and adjacency, and we can see indeed that two adjacencies have been formed with the same router, but one is of level 1 and another one is of level 2. Alright, so continuing from previous video where we had configured router number 1 and Juniper router number 1 for basic level 1 and level 2 connectivity within the same area. What I've done is that I have also configured all the other three routers with the very same configuration that we had done either on Juniper and Cisco. That is, just configured the net address and put the respective interfaces in the ISIS process. So let's just come on to router number 2 and let's see if we have got the information regarding the loopback addresses or the interfaces that are in between the routers in the databases as well as in the routing table of Cisco router R2, which is on the far end of this topology. So this is the router. Let's just quickly go into enable mode, and if I type in, let's say, show, and afterwards, first let's see the neighbor relationship, that whether it has formed the neighbor relationship with router number 3, which is the Juniper router. Let's see if it has formed the neighbor relationship. So I type in show ISIS and neighbors, and we see that indeed it has formed both the level 1 and the level 2 relationship or the neighbor relationship with that particular Juniper router. Now after that, I type in show and IP route, and I press enter, and this is the output that we are gonna see. We see that the loopback address of router number 1, which was GNS 1, then GNS 2 loopback address, Juniper 3 loopback address, and also the Cisco loopback address, all have been learned via the ISIS protocol. And if you look at the metric of these routes that have been learned, we can see that let's have a look at this one. This one is 10. So to reach to the loopback address of GNS number 3, since we need to traverse only one link, so this is 10. For the loopback IP address of Juniper 2, we should be seeing the metric value as 20, so which is over here, and likewise 30 for GNS number 1, and for Cisco router number 1, we can see that the value is 50. We can also see that although the neighbor relationship which was formed between the routers is both of level 1 and level 2, but if we have a look at these routes, they are all learned at level 1 level, although they have been put into the database of level 1 level 2 both, but the entries that have been made their way to the routing table, they are of level 1 only. And this is also a key point to remember, that if in case of ISIS, if routes are learned both via level 1 and level 2 routers, then level 1 routers are preferred, because that would mean that they are in the same level. So by virtue of the protocol, they are the preferred ones. Now let's have a look at the databases. I type in show ISIS database and then press enter, and we see that it has got two databases. One is for level 1. These are the LSP IDs that we talked about, that link state PDUs. So these are the IDs. We can see that this is the GNS 1 router, this is GNS 2 router, then another LSP from GNS 2 router, third one, and then from one LSP from GNS 3 router. And this one, or I should say, yeah, and this one, these are the Cisco routers. And this one over here, this is the level 2 database, which would be sharing the same information as that of level 1, since all the interfaces or the network, we can say, they have been configured as level 1 and level 2 both. Similarly, if you want to see the same thing onto Juniper router, let's head over to Juniper 3 maybe. Let's just bring up over here, and I can type in run show route to see the routes, and we can see that the loopback address of GNS 1, it has been learned via ISIS protocol, having a preference value of 15, and we can also see the metric value of 20. Similarly for all the other routes in the topology. And if I do a run show ISIS database and press enter, we can see that just like in the case of Cisco, we also have two databases. One is of level 1 and another one is of level 2. Now if I try to ping, let's say, or check the reachability connectivity end to end, maybe I come on to Cisco router and try to ping the loopback IP address of router number 1, which is over here, Cisco router, and I am over here at the moment. I should be able to do that successfully. and we can also do a trace route if we want to till 4.4.4.4, and we see that we have got full reachability. So now at the moment what is happening is that all the routers are of and all the links in the routers that are of level 1 and level 2, and resultantly two databases are maintained. Now if any of the link flaps, because this is a single area topology, if any of the link flaps, then the SPF calculation will be calculated not only for this particular area, which is area number 1 at the moment, but also for both the levels, that is level number 1 and level number 2. Now in large networks we do not want to do that. What we want is that SPF calculation should be kept to the minimum. That's the benefit of these protocols, these link state protocols. So what I'm going to do is that let's say that put this router number 1, which is Cisco router, put this one into level number 1, and also put the interface of GNOS connecting onto this router number 1 into level number 1. So let's do that. Let's head over to R1 and let's just quickly go into global configuration mode, and over here I go into protocol mode, and over here I can type in IS type. If I do a question mark to show you the available commands, this is the one that I'm going to use, which is IS type, IS level for this routing process, OSI only. It will affect those, so I'm going to type in as level number 1. So IS type. We can also do the configuration on particular interfaces, so let's do that first. Let's not change this one. Let's head over to, let's say, interface loopback 0, and over here type in ISIS circuit type level 1, and similarly go into the interface which is connecting this router to Juniper router and type in the same command, that is ISIS circuit type level number 1. And now if I do show ISIS neighbors, we see that now we are only forming level 1 type of adjacency with the Juniper router. Also if I do show ISIS database and take it all the way down, we can see that we are still having this level 2 information because this has already been put into the database. So when these entries will age out, these will be removed. Also in parallel to the configuration on Cisco router, we also need to put the link on Juniper router number 1 E1 interface as a level 1 interface. So let's head over to Juniper number 1, which is over here, and let's just type in set protocols, then ISIS, and then interface is EM1, and then level 2, and then the keyword which is disabled, that disable level 2 information to be sent onto this particular interface, and stop forming the adjacency on this interface at level 2 number 10. After that I commit the information, and let's have a look at the database on this router one more time. So still it has not cleared it. Let's just save our time and do a clear ISIS star, so that it should form the adjacency again. And now do a show ISIS database and repeat this command one more time. We can see that it has got all the level 1 information from all the other routers, but for level number 2 it has got only one LSP which belongs to this particular router itself. Now what is happening over here is that since level 1 information is preferred over level number 2, so since all these routers are still in level number 1, I have just disabled level number 2 information from going over to this link. But level 1 database information can still flow between these two routers. So still we can see that all the routes from all the other routers are available in the level 1 database or router number 1. So what I'm going to do now is that I'm going to disable level 1 onto GNS1 E0 interface so that it does not populate its level 1 information that it is connecting, that is getting from these routers. And we will see ultimately that the effect of that would be that router number 1, it will not have any information regarding the networks onto this side, because the information that will be coming onto this GNS1 would be in its level 2 database. But since the two databases, level 1 and level 2, they do not interact as such, so this will not, I would say, leak that information, because that is the proper word, leak, when we are talking about ISIS. So that information will not be leaked into level 1 database, and since it will not get leaked, it will not be passed on to route number 1. So let's do that. Let's head over to Juniper router one more time, and or maybe first Cisco router, and repeat that command one more time to see where we are. So let's just head over to Juniper number 1, and let's type in set, let's say protocol ISIS, then interface, and then EM0, which is, it is connecting with Juniper 2. And over here I type in level number 1 and disable, and do a commit. Once the configuration is committed, and if I come on to route number 1 and do show ISIS database, maybe repeat it one more time, or maybe just clear the process to, make things real quick. Do it one more time. So we can see that eventually the entries from level 2 database have been removed, and only level 1 database entries are in there. Let's just repeat the command one more time, and let's also try to have a look at the routing table of this Cisco router number 1. So we see that only the loopback address of Juniper router 1 is being learned via ISIS protocol, which is the idealistic case that we should have. Now let's also jump on to Juniper router number 1, and let's also have a look at the database of this router. And we should ideally be seeing that I would say that level 1 information, level 1 database will contain the information regarding this segment only, and not these segments, because the link between Juniper 1 and Juniper 2, it is only a level 2 link. So we will see that level 1 database will not contain entries from these routers or networks. So let's head over to Juniper, and let's type in run show ISIS and database. And indeed we can see that we have got LSPs. One is local and the other one is pertaining to the router, which is Cisco, and which is having a system ID of this one that we had just configured. So just 3 LSPs in there. While in case of level 2, we can see that it has got the LSP from Juniper 2 and Juniper 3 as well, and also from second Cisco router, which is this one. So essentially what we are seeing here is that the level 1 database of Juniper 1 and router 1, they will be the same, because we are running link state protocol, and the database has to match to provide consistency in the network and to have consistent view of the network as well. And likewise, the level 2 database for this topology for all these routers, that is Juniper 1, 2, 3 and router number 2, their level 2 database will match exactly the same. So let me just show you this information. Let me just pull up this one as well and put them side by side, and let's do. So this one is Juniper router number 1, and this one is Juniper router number 2. Now let's have a look at the databases side by side. Now we can see that this is local, so this one, and also look at the sequence number 047, and this one, since this is not local, so it will be shown with its complete system ID, and look at the sequence number 047. We are looking into the level 2 database at the moment. Similarly, if we have a look at these entries, these 3 belong to system ID 2, which are over here. Since these are local to this Juniper router, so this router is not appending the system ID. It is just showing the last values of that particular LSP, and we can also see the sequence numbers which are matching exactly with that of Juniper number 1. So what I want to show you over here is that the databases of level number 1 in that particular area and level number 2 are identical, so that the routers or the intermediate systems can have a consistent view of the topology, and based on that they can have a loop-free path to the nodes and resultantly to the connected networks. Okay, so now that we have configured basic IS and we have also seen some of the parameters in its databases, let's do one thing. Let's come on to router number 1. Where is router? So this is router number 1, and if we have a look at its route table, we see that it has got only one route which has been learned via level 1 database. So at the moment, the problem is that this router number 1, this cannot reach out to its own level, although they are all in the same area, but since router number 1 is only level number 1, it is unable to access the networks that are over to this side. So what we can do is that we can leak the routes from Juniper number 1, which are there in its which were learned via level 2 database. We can leak those networks into level number 1, and ultimately, since they will be released or leaked into level 1 database of Juniper 1, they will be advertised to route number 1, and router number 1 will be able to access these networks as well. So let's try to do that. Let's come on to Juniper number 1 and type in the command. Now I'm going to leak the routes from level 2 to level number 1 on the Juniper number 1 router. So I type in set policy options, then policy statement. So I'm going to make a policy where we will do our stuff, and afterwards I can name the policy anything I want to. Let's name it maybe ISIS, and then term number 1 says that from protocol ISIS, so that all the routes that have been learned via ISIS and have been put into the routing table. And then the next criteria that I'm going to select is, let's say, from level 2, and we want them to be going to level number 1, so to level number 1. So these all 3 statements that are I would say that these are kind of match criteria for that particular action to happen, and the particular action is then accept. So what we have configured over here is that if the routes have been learned from ISIS and they are of level number 2, and we want them to be going to level number 1, then that action should be accepted. Now to implement this, we need to type in set protocol ISIS and export, and then the name of the policy that we have just defined, which is ISIS. Now commit the configuration, and once the configuration is saved, we should ideally be seeing that the LSPs or the routes which were available through level 2 in Juniper, they would be available in the level 1 as well. And if I come on to Cisco router, which is over here, and do a show IP route, we can see that now we have got some other routes as well, which are inter-area routes. We can see over here that IA is ISIS inter-area routes. So it has learned about Juniper loopback address 2 and 3 as well, and also it has learned about Cisco loopback addresses and all the intermediary interconnecting networks. So the key point that you need to get from this output that you have just seen is that if the routes are learned in level number 1 database, and they are kind of advertised or exported to a router which is level 1 and level 2 both, then the routes that are learned to that router in its level 1 database will automatically be transferred onto level 2 database, and hence will have the reachability of those particular routes throughout the network in the level 2 database. But by default, the routes that are put into level 2 database, for example, if there's a router and it has learned about the networks using level 2 database from other maybe areas or other area routers or maybe other routers which are of level 2, then those routes will not be advertised or put into level 1 database, and hence all the routers which are having level 1 and are attached to that particular router, they will not have visibility of the network. So just like the case that we have just implemented over here, that router number 1, since it had not got the visibility to these networks, we had to manually leak the level 2 routes into Juniper number 1 in level 1 of Juniper number 1 from level 2 database. Now at the moment what I have done is that I have leaked all the routes, but you can define prefix listed or even the route filters if we are talking about Juniper, but if we are talking about Cisco, we can use route maps to leak specific networks and not all of the networks if you want to. Another important thing that you can do over here is that at the moment what we have done is leaked level 2 routes into level number 1. But what we can do is that we can kind of advertise a default route into our level 1 routers instead of leaking all the level 2 routes into level number 1. So let's see from Juniper perspective how we can do that. If I come on to Juniper 1 and let's just negate the statement, maybe deactivate it or simply negate it. So delete this statement. So once the configuration is saved, now let's implement another policy. Let's say that policy options and then policy statement, and this time let's call it maybe default route and then term number 1. And before we do that, or let's go ahead with it, because I wanted to implement it using prefix list, but it's alright, we can use the route filter which are implemented right then and there in the policy options. So term 1 is from route filter, and the route filter is 0.0.0.0/0, and let's make it exact. Also in term number 1 we want the routes to be going to level number 1, and then we need to define the action. So let me just see. So I come on to term number 1 and then I define the action as accept. Now once that is done, I also need to define a route, and unless that route is available in the routing table of this Juniper router, it will not be advertised. So we can do that by typing in set routing options and then static, afterwards route, and the route is a default one, and let's just discard this one because I'm just showing you the proof of concept that how does it work. It's kind of the same statement that we implement on Cisco, that default route is pointing to null interface. So afterwards I do a commit, and once the changes are saved, and if I come on to router number 1 and have a look at its router table one more time, refresh it, and the route is still not there. Let's see, did I export this one? Alright, so I also need to export this policy just like we had done earlier. So I type in set protocols ISIS and export, and then the name, which was def route, and do a commit. And once the configuration gets saved, let's come on to router number 1 and do a show IP route one more time. And indeed this time we see that a default route is available to this route number 1, and it is pointing to the Juniper router number 1 learned via ISIS, and it was learned through level 1 database. Now we can implement the same thing in Cisco as well. I'm just gonna show you quickly how to do it. But remember that the default routes have to be originated on a router which is of level 1 and level 2, and not on level 1, because of course it makes sense that a level 2 router is the one which is having the connectivity to the other routers. A level 1 router is kind of totally stub network. So remember that if you are talking about Cisco or Juniper, you need to implement this generation of default routes on those routers or intermediate systems which are having level 2 database as well, or having level 2 adjacency with other routers. So if you want to do this configuration, this generation of default route, it's pretty simple. You just need to go into the router configuration mode, and over here you will need to type in default information and originate, and after that you can also put in route map, just like we had done over here. If you want to define certain criteria, you can do that by putting in the route map. You can simply type enter over here, so that it will be accepted for all the adjacencies that have been connected with this particular router, and it will generate the route for those towards those particular routers. But if you want to specifically mention that only those routers, or maybe whatever the criteria that you want to have, you can use that over here in your Cisco environment. Now the next concept that I want to show you and discuss with you is, at the moment what I have done is that all these routers in a single area, right? And I have not changed any or demarked any area. So essentially, if I say that this Juniper 1, it is a level 1 level 2 router, well, of course it is level 1 and level 2 router because it is having maintaining both the databases. But from practical point of view, it is not connecting to different areas, because normally what would you do is that once you have got level 2 routers and level 1 and level 2 routers, those are the routers that will be connecting 2 or more than 2 different areas. But at the moment we have got only one area. So resultantly what is also happening is that if we have got a level 1 and level 2 router, or level 2 router only, in fact this scenario only holds true if we have got level 1 level 2 router, just like the case over here. So what would happen if we have a level 1 and level 2 router, and it is connected to a different level 2 or level 1 and level 2 router? What would happen is that at the moment we needed to have generated a default route to this router number 1, right? That's what we did. We had to manually generate a default route so that router number 1 can get out of this level, and since area is the same, so let's not talk about the area. But if we have got different areas and our level 1 routers need to go out from our areas, then the router which is connecting to different areas level 2 routers or level 1 level 2 routers, then that router will automatically generate a default route towards its level 1 routers. So let's see how we can do that. I'm going to do is that let's change the area ID using the net command on Juniper 2. And before doing that, let's also remove the configuration that we did to generate the default route on Juniper router number 1. So let's quickly head over to Juniper 1, and over here let's simply remove this one where we are exporting the protocol parameters. Let's delete this one. Let's do a commit, and heading over to Cisco router do show IP route, and we see that indeed that static route that we had manually defined has been removed. So let's head over to Juniper 2, which is over here, and now I'm going to change the address or net address for this particular intermediate system or particular router. So let's do that. I'm going to type in set, then interface loopback 0 unit 0, afterwards family or unit 0, then family ISO, and address is 49 because this is the AFI, so it will remain the same, and let's change this one as to 2, and afterwards the system ID, it can remain the same, it does not matter. So I type in 0020.0200.200.00 and enter, and since the earlier value is still there, so I need to remove that one. So let's just delete that value, and if I come over here all the way, just one and tab, and this was the previous value, so that has been removed. And if I do a show, you can see that now the value of this intermediate system as of its net address is this one. So let's do a commit, and this will put this Juniper router number 2 into a different area now. Let's do a commit, and once this has been committed, we should ideally be seeing that router number or Juniper router number 1, Junos 1, it will generate a default route towards Cisco router number 1, and that default route we will not be able to see it in Juniper 1 because that is done by a specific bit which is known as attached or attachment bit, and I'll just show you what I mean by that. Let me just quickly come on to router number 1 and do a repeat of this, and we see that indeed we can find a default route in here. Now let's have a look at the database of this Cisco router. I type in do show ISIS and database, and then append the keyword detail, and if I come over here, we can see that this is the attached bit that I'm talking about. Now at the moment this is set, and also if I bring it down all the way so that we can have all of the output. So what I'm trying to show you over here is that based on this attachment bit, this ATT bit 1, this router number 1, since it is running ISS protocol, it interprets this 1 as of that it needs to generate a default route itself, which will point towards the next hop belonging to the router from where this LSP came from. So just like I had shown you earlier, that if I do a show IP route, we can see that this default route, it is pointing to this interface which belongs to Juniper router number 1. So that is very important concept to remember, that this default route, it gets automatically generated once level 2 routers are connecting to different areas and not in the same areas as we had seen earlier.
Alright, so continuing from previous lectures, we have seen the functionality of ISIS and how we can implement it on Cisco and Juniper, and what are some of the key points that we need to remember, like MTU and route leaking or generation of default routes. Now in this video, what I'm going to show you is that how we can redistribute routes, let's say from Cisco onto Juniper or the other way around. Another important aspect that I want to show you, that topic will just come up. Now let me first come on to router number 1, which is Cisco router over here. Let me just pull up the terminal and execute the commands. Let's get into, let me just show you the routing table of this router at the moment. So I type in show IP route,
and I have configured 3 static routes, which are these one, and they are just pointing to null interface. Now what I want is that I want these routes to be redistributed into ISI's protocol and then be available throughout this topology. So I'm going to go into the router protocol configuration mode, and over here I can type in redistribute static, and then let me just show you the output, that in which level database we want these routes to be redistributed. For example, whether in L1 for L2 or maybe both of these. And also this important point that I was telling you about, this metric type, that what should be the metric type of these routes while they get redistributed into the ISIS domain. So at the moment, let's just say that these should be redistributed into level number 1, and metric type is, let's say, internal. So that would mean that these routes are marked as internal and get redistributed into ISI's protocol. Now let's have a look at, let's say, do show ISIS database and then detail. And once we have a look at that and I bring it all the way down, we see that although these are the entries that I wanted to tell you about, that although we had marked them to be redistributed internal, this command did not take any effect on Cisco routers. So the command got executed, and the routes should have been redistributed internally, like they should not have gotten this entry which is IP external, but essentially that entry is there, and that marks these routes as coming from the external sources. So if I come on to router number or Juniper router number 1, and I type in, let's say, run show, and afterwards ISIS database in detail, now we see that in level number 1, these are the routes, 3 redistributed routes, and they are external. Now since these routes have been put into level 1 database, so essentially they should be transformed or leaked into level 2 database and be available to the other level 2 router as well. So let's head over to Juniper number 2 and let's see that if we have got those routes over here. Let me just come on to Juniper route number 1 and show you the outputs of run show route. So these are the 3 routes that we are interested in because they have been redistributed. So coming back to router number Juniper router 2 and running the command run show route and bringing it all the way, and we see that we do not have those routes, although ideally since they were in the level 1 database of Juniper 1, they should automatically get redistributed into level 2 database and then be sent over to the other level 2 router, but as we see that it has not happened. Now the problem is that by default, and this is another concept that is coming in, the problem is that by default Cisco routers, they use the metric type as of narrow, while Juniper routers support both narrow and wide metric types. Now what is narrow and wide metric type? Let me just quickly pull up a white sheet and tell you what it means. So when we are talking about metric types, we say, and specifically with regard to ISIS protocol, we say that we have got narrow and wide metric type. Now narrow metric types, it essentially means that it's got less number of bits to define the metric value. By default, we know that in ISIS protocol, whether it's Cisco or Juniper or any other vendor, the default value for the link, the default metric value for the link is 10. and we can change this value, let's say from 1 to 63. Essentially it means 6 bits. And the total number of hops or the total number of metrics across all the hops, if we are using narrow style metrics on all the routers interfaces, then the maximum metric value that we can reach is 1023 or 10 bits. Now, when we are operating in a small environment, a small to medium environment of enterprise level organization, this narrow metric style, it's alright. But if we are talking about large ISPs or service providers, or even large enterprise environments where they might want to implement maybe traffic engineering for MPLS. So those kind of requirements, they need, they do not get their due benefits if we are to use narrow metric styles. In those cases, we need to use wide style of metric types, and that provides us 24 bits for just defining the metric value. And the total, I believe let me just recall the exact value. I believe it's 32 bits equivalent to 24 bits is for the definition of the metric of one interface. Like in case of narrow, it is ranging from 1 to 63. By default, it is 10. In case of wide, we can use 24 bits. But the total, I would say the total metric across all the links as compared to 1023 in case of narrow. In case of wide, it is 4.2 billion. So this equates to 32 bits. So essentially, in case of narrow, we are left with this metric value across all the hops. But in case of, and let me just type in or put in billion over here so that you can remember that these are 4.2 billion metric cost that we can accommodate for the total metric value across the path of an ISIS domain. So as I was telling you about earlier, that Cisco by default uses narrow metric style, but Juniper routers, they support both wide and narrow metric types. Now let's go back to our topology, which is over here, and let me just pull up the Juniper 2 interface or terminal, and let's execute the command one more time, which is run show route, and you see that we are not running the redistributed routes. So what we can do in this scenario is that this is again something that I wanted to show you regarding the inter-vendor operability problems. If we had all Cisco environment over here, like these all routers have a Cisco, then the command that we just did, let me just show you that the redistribution command that we just did on Cisco router, that redistribution command would have been just good enough for those external routes to be redistributed onto Cisco routers. But since these are two different vendors, they have got some interoperability, I would say, mismatches. So we are gonna make them communicate with one another. And what I'm gonna do is that I'm gonna make the metric types on Cisco to be that of nature wide. So the command is pretty simple. We just need to type in metric and style and just put in wide. Now as soon as I execute this command, we will see that these externally redistributed routes into ISIS domain, they would be available onto Juniper router number 2 as well, which they were not earlier available, as we can see over here. Now from practical point of view, if you are to implement ISIS in your organization, whether doesn't matter which vendor you are using, either it could be Cisco, Juniper, Lucent, or any other vendor, and if it has got a support for wide range of metrics, metric style as wide or more number of bits as I had just explained to you, then it is recommended from Cisco as well and from Juniper side as well that the engineers, they should tend to use by default the wide matrix style, so that you can truly reap the benefits of this ISIS protocol. Now, like many other protocols, ISIS also does support authentication of its packets. And in this short video, I hope so, I'm going to show you that how we can do that. ISIS protocol on Cisco as well as on Juniper, it does support plain text authentication where password can be sent in plain text, and it also does support MD5, which is a hashed value that is sent over to the authenticator. So let's quickly come on to Cisco router, which is router number 1 over here, and let's try to configure it for authenticating the ISIS packets. So let's just quickly log into it. Get into global configuration mode, and first we need to configure the keychain by typing in keychain and giving it any name. Let's just say I want to name it maybe auth. You can name anything. Now once we have entered into keychain, we need to define the key. Let's just say that I define key number 1, and after that we need to define the value of the key, the value of the key, which is defined by key string. So let's just say that let me just put it ABC. Now once it's done, we need to implement this key on the ISIS protocol, or associated with the ISIS protocol. That's the true word that I wanted to say. So I go into the quickly go into the ISIS protocol mode, and over here I type in, let's say, authentication mode, and these are the two modes, either text or plain text, and then the MD5. So I'm going to choose MD5. And also the other thing, let me just do a question mark, and okay, so after authentication I need to show you that, I just want to show you something, that keychain, or maybe this not the okay. So over here, when I use this question mark, look at this one, this authentication. This says that ISIS authentication for LSPs and not for the hello packets. So that would mean that adjacency will be made if let's say one side of the link has got authentication enabled while the other side is not, or maybe using a different password. So that would mean that the adjacency will be established, but the actual LSPs, until unless they get authenticated, the information will not be shared or will not be put into the databases. By default, what I specifically mentioned this thing over here because you see, in case of Cisco, at the moment I'm on Cisco router does not authenticate the hello packets. It only authenticates the LSP packets. But in Juniper, we have got the option to either authenticate the hello packets, or we can even authenticate the LSP packets, or maybe disable them for our particular needs. So I'm going to implement this command by putting in authentication and then keychain, and then the keychain value, and afterwards what level I want to implement this on. So since router 1 is level number 1, so just put in level number 1. Now once I do that, I press enter, and you see that as soon as I pressed enter, afterwards a new LSP will be sent from Juniper router, since this one is connected with Juniper router number 1, and that LSP failed its authentication. Now let's have a look at maybe do show ISIS and database. So these entries are still there, and you see that it has started its hold down timer, which will be decremented. And once that hold down timer gets decremented to a value of 0, this entry will be flushed out. And it is again giving this message that the LSP is being failed to get authenticated. Now, if I do, let's say, do clear ISIS all, and let's have a look at the database one more time. We see that now there is no more entry. But interestingly, if I do show ISIS neighbors, we see that the neighbor relationship is there, but now these LSPs cannot make their way into the level 1 database of the Cisco router. If I repeat this command one more time, we see that there is no LSP being received from Juniper router because it is failing this authentication. So now let's quickly head over to Juniper router and implement the authentication over there as well. So let's just pop into Juniper router number 1, which is over here. And the commands are pretty simple. We just need to type in set protocol ISIS, and then for which particular level we want that authentication to be enabled. So let's just enable it for level number 1, and then authentication type is, let's say, MD5, and what else we have got? Authentication key maybe. So authentication key is just the key that we want to type in, which was ABC, right? Now if I do a commit over here, and we would assume that everything is going well, still it will not work, because by default, I told you that by default what Juniper does, it's a better security mechanism. I would say that it kind of authenticates all the packets, including the hello packets. So even though we have enabled it, if I come it over here and clear the adjacency, and let's have a look at it one more time, we would see that now these two routers, the Cisco and Juniper router, they will not become the neighbors as well. Initially, when we had enabled authentication only on the Cisco side, the neighbor relationship was getting up because hello packets were not being authenticated by the Cisco router. So let me just repeat this command one more time. But as soon as we configured authentication on Juniper router, since Juniper router authenticates all type of packets, including the hello packets, so now Cisco is not authenticating hello packets, but Juniper is. So the neighbor relationship is not getting up. Now the problem is that we can, I believe we cannot disable it on Cisco router, but we can, thankfully we can disable this feature on Juniper router. So let me show you how we can do that. Let me just put it up, and if I do a question mark, we have these options. We can disable the complete sequence number authentication as well, these types of packets, or we can disable for hello packets, or we can also disable for partial sequence number packets. So we want to disable the authentication for this one because Cisco is not supporting this one. So let's just do that. Let's just disable no hello or hello authentication, and then do a commit. And once we do that, we will see that we would not only have the neighbor relationship up, but also we would have the LSPs being transferred into the respective databases. So let's do a commit, and once the configuration gets saved, let's just quickly come on to Cisco router and do a show neighbor command again, and we see that indeed the neighbor has come up. And if I type in do show ISIS database, we see that we have got the LSP from Juniper router number 1.